Hello, good morning all. We are now celebrating the 4th International Conference on Biodigital Architecture and Genetics this year 2020, and it coincides with the celebration of the 20 years of the foundation of the Genetic Architectures Research Group and Office, and the 20 years of the Biodigital Architecture Master Program, under the shelter of the IBAC Week, the Institute for Biodigital Architecture and Genetics of the Universitat International of Catalonia. And however, this time we arrived to this celebration under a strange pressure of the greatest pandemic in the history of humanity. Okay. Sorry. But in spite of everything, these last times have been revealed as the most solid and productive of the group, something that should be thanked for those who have loyally and sincerely put the talent and effort at the service of the objectives that have been achieved. Some of them have been already published and others are presented at this Congress and its book. I hope you enjoy it. And in short, even the uncertain times that are running another way that remains to be done, there are many reasons to be very happy with what has been achieved, with what is ensured for the future, and with the multitude of appreciates asked from the world. So we must be very grateful for all this, and to all those who find interest in our work, in our teaching, in our research. So thank you, everyone. And I will introduce this conference with a little manifesto that I will read this manifesto because it's something that it's exactly for our times, so that I can explain that here. Okay. So, telling that from one side, if you think about what we are doing, it is, I explained this shortly in the manifesto, biomanufacturing the future, let life grow, natural intelligence and artificial intelligence, biolearning and machine learning, biomanufacturing and digital manufacturing, keywords that shape the globe of biodigital, of the step-by-step fusion of biological and digital, which must provide us with the architecture and design for a better future for our planet, perhaps the only future for living with dignity. The urgency that we have been announcing since 2000, which includes the application of genetics, biological and digital genetics, also to architecture and design, now 20 years later and under the COVID-19 pandemic, is more evident. Due to the consequences of 2 months of confinement of the entire world paralyzed and locked up at home, everyone has finally seen the obvious of this matter. A drastic reduction in air pollution and ozone hole that closes, nature that has resurfaced like never before, simply because of human absence and something as trivial as the fact that no one cuts the grass, proving that nature is the most resilient thing that we have on our hands. And here some images of this action. Let's see if this works now. And okay. Yeah. So now with the images of the action, let life grow, parks, sideways, cracks, places where nature was never allowed to grow so much. For the first time now, a whole series of plants, flowers, and animals appear in areas never seen before. are recognizing nature's capacity for regeneration and how it brings us the solution to our problems. The action Let Life Grow appears as a manifesto, words written on traffic signs forbidding the mower, placed in every corner of the planet. We just have to let nature to do its work for us. Nature is the solution. Natural intelligence as a lighthouse of artificial intelligence. Learn from nature first by learning, then helped by the advantages of machine learning and biomanufacturing, much more effective than digital manufacturing, looking for a perfect symbiosis of both. We should not follow the easy way just for comfort, because at the end, it is much better, faster, and cheaper to discover the secret laws of the universe for biomanufacturing our future. Now it's only a question of will, of funds, of research dedication in disorder in inverse proportion to the time required to achieve results. We can already think about their application in objects of use, wild seeds that grows alone in houses, buildings, cities, parks, and landscapes, entire territories, even planets that emerge, that develop powered by the mere internal force of DNA, entire worlds genetically designed to solve human needs, living or biting around the Earth, or small microcosmos as big as a patio or as an intercity, without the need to go to distant and inhospitable planets with an uncertain future. So I declare, let house grow, let buildings grow, let cities grow, let planets grow, let life grow. In Barcelona, 4th of June 2020. And welcome to the conference. We will now go to the inaugural key speaker, Aldo Solan. So thank you for attending.
Okay, Aldo, so we can prepare to show your presentation. I'm going to put you on the screen and I can tell you when to begin, okay? Okay, so... Aldo, will you share your screen or you will just talk?
I'm gonna share the screen from my laptop.
Okay.
So let me share it.
Okay.
Okay, I'm ready. So, thanks. First of all, thanks to Alberto for this invitation. It's a pleasure to be part of this conference, and it's also interesting to make it so distributed and have the opportunity to connect with all these designers, researchers from all over the world. So let me quickly introduce us. We are Numena, a company that works a lot with data and computational design and digital fabrication. It's a multidisciplinary team. We work specifically in robotic application, additive manufacturing, and fashion tech. I prepared this quick video recap of what we've been doing last year in these three sectors. The real common value, or let's say the fil rouge that connects all the activities that we are developing, as I said before, is data. And now we can transform or extract information from the built environment and start from the physical environment and start to embed this information into planning framework into a design framework that allow us to support decision making, that allow us to understand better the ecosystems where we are working, the characteristics of material properties, as well represent maybe in a more dynamic way our built environment and as well inform fabrication process. I don't know if you can hear me properly while I'm speaking through the audio of the video. I hope so. So in Barcelona, we also have a facility that is fully dedicated to additive manufacturing in collaboration with WASP. And this lecture will actually focus on the activities of 3D printing that we've been developing in the last couple of years here in Barcelona, also in collaboration with WIC and Alberto Estevez and the Master of Biodigital Architecture. Another important part for us is as well how to embed data into materials, as well to understand their material properties, characteristics, and try through these understanding as well to define new aesthetics, fabrication protocol, and as well correlation between, as I said before, material properties and their capacity to respond to external stimuli from the context. Okay, so jumping quickly to a little bit of contextualization. I mean, of course, we are in the fourth industrial revolution. You are full aware of all the transformation that lead us to the challenges of the fourth industrial revolution that are, let's say, specifically connected with the conification of machines, the interconnectivity and the possibility to distribute and as well share data and information between multiple actors are part of the fabrication protocol. When we talk about fabrication and other important contextualization, I would like to underline is what also in IAC, not only, I mean, in IAC, but in the, for sure in the FabCity framework, we've been as well digging about the transformation from a linear line of production and consumption to a circular model that can maybe represent as well a shift between how we transport matter and instead how we can transport data and informations. So we are in a new era where from mass production we are moving to mass customization, which is evidently a transformation of the industrial sector that represents as well important impact and implication regarding also the role of new technologies and the relationship that this technology establish between operators and humans. We are in an important as well moment of maturity of technology where all the solutions that we've been slowly introducing in the industry start to be mature enough to be considered, you know, impactful at the larger scale. No, so the solution that can start really to underline or even shape a new framework for production that is strictly connected materials, design protocol, fabrication system, as well new consumption models. So when you talk about 3D printing, normally, I mean, in every single presentation, someone is shooting big numbers about the impact of this industry in the future, how big will be, how is, I mean, incredibly increasing is economical impact over the market sector. But what I would like to maybe focus on is the possibility of this technology to talk about the future, to project and as well shape transformation, realize and start to mold as well something that it's maybe a promise for the future. So 3D printing started to to be largely used as a technology that can offer quickly prototypes. Prototypes that I mean, if you look at it, are evidently a first shape of something that can become afterwards a product. But we believe that 3D printing can go much beyond the idea of simply a machine that can bridge, you know, an idea to a product. And let's see a little bit the trajectory that together with WASP, this Italian in company that is producing large machinery for 3D printing as well as small one, we've been developing together in Barcelona. So in Barcelona, Numena is part of the WASP network. And we are equipped with a series of machines that now don't even fit any longer in these slides. But this machine, of course, allow you to print from small scale to larger scale, implementing different materials. But the interesting part of having the opportunity to work with these machines as well is the network that it produces and generates around it. So one of the key aspects of all the process of innovation that you're gonna see also today with the papers start with collaboration, start with as well the contamination of knowledge that happened in the moment where different experts start to collaborate together and even blend their expertise, their skills, their capabilities, starting to produce something new. So we started to collaborate with craftsmen working with ceramics, working with different materials, with organic pigments that could also allow us to color and create new patterns and characteristics. We started to collaborate as well with local designers in Barcelona as external reference, working on the definition as well of new furniture that could maybe embed the language and the style of the architect and blend their aesthetics into also the limits and characteristics that the machine is providing. And this is a quick video from the Manglar table that we designed together with the external reference. Here in Barcelona, but as well, I mean, we started to collaborate with Alberto Estevez, Pablo Vaquero, Efimia Giannopoulou from the GenArc office to design organic chairs, organic components that could be part of this new distributed vision as well of urban furniture that Alberto and all the team are picturing for their landmark at the university. We started to work as well with fashion designers, implementing 3D printing in fashion, participating in the Mercedes-Benz Fashion Week in Madrid, or with digital artists that started to implement machine learning in the analytics from social media to shape let's say new sculpture, digital sculpture, and this is one of the artwork from Albert Brack for the Mobile Week of Barcelona. I mean, everything has its own story, everything has its own characteristics. So I'm gonna just quickly show you this slider of information, but as well another interesting collaboration was with Acciona and Lopoli, starting to talk about memory, starting to talk about heritage, and this was the opportunity to reconstruct as well ancient monuments and start to blend also different machine in order to reproduce historical monuments, and as well give the possibility to people to start interacting differently with these objects. As well, on the other side, we started to think about how to produce new architectural component, reconsidering the possibility to implement large-scale fabrication into a series of panels that I would like to describe in a little bit at the end of this call, of this conference, starting from the material characteristics. Talking about architectural scale, I mean, when we talk about 3D printing, I would also like to mention the collaboration that we had with AIAC, the project that we did in 2017 in Fira, in Barcelona, where we set up a series of always collaborating with multiple actors. So my company of Numena from one side with all the robotics and data gathering, on the other side Tecnalia with the Kojiro Technologies, and IAC for the side of materials and the 3D printing extruder. We started to as well understand if we were capable of hacking existing technologies, starting to transform, rethink their application, transforming a machine that Tecnalia was using for pick and place and converting it into a huge 3D printer of 10 meters by 6. And in these 5 days of the fair, we were actually capable of fabricating more than 7.2 kilometers of clay, giving life to, let's say, an interesting scenario, a new interesting paradigm where multiple technologies were brought together. One of these technologies was, as I said before, one of our drones that was actually meant to let's say, detect, extract information from the physical environment, starting also to compare the fabrication process with what the machine was meant to fabricate, comparing the G codes and the actual physical component that was built. And in this first experience, we also started to work on a process of data fusion, embedding not only visible channel, but also infrared and thermal cameras that could allow us not only to describe the physical characteristics of this wall, but as well let's say, is performance, looking at the thermal characteristics of the material that could inform as well how the wall could be built and could also resist to multiple layers over time. And this collaboration that IAC started to explore, of course, was then translated in another collaboration with WASP, and the possibility in the OTF program directed by Alexander Dubor and Edouard Cabey in the translation of new architecture that could also start to embed different components. So not only one material, but as well the interesting integration of multiple components that can start to even be assembled or be introduced in the fabrication protocol. Well, one important aspect that I would like to mention in these last 5 minutes that I have, for sure, is materials. I mean, for us, it's not really all about machine. It's not only about, of course, the implication of design solution into this new fabrication process, but it's also the introduction of material technology. So how can we start to think about material? And as Alberto was saying before, even start maybe to activate a new different ecology around the possibility to program material characteristics. I mean, when we talk about ecology, Timothy Morton is always also talking about factoids. So the typical speech about, you know, the emergency of climate change, etc., etc. I'm not gonna take this discussion, but I would like maybe also maybe just to mention that, I mean, we are living in a moment where there are a series of challenges that we need to face, maybe proposing solution that could also represent an opportunity. When you need to propose something, maybe it's good to look at nature, as Alberto was saying. And in terms of climate change, for sure, we have a very efficient solution in our planet. I mean, trees are one natural solution that are perfect to absorb carbon dioxide from our atmosphere. And we started to look at material characteristics as well to introduce a new innovation. Innovation, evidently, is something that matters, evidently, something that has a wide recognition in terms of impact from society. No? That at the end is who really validates what it is innovation, not us, you know, in our ivory tower speaking about the beauty or the coolness of our new project. And that's why I would like again to underline the impact of material technology in bringing innovation. In Numina, we are developing since 3 years together with PrimeLab a new material that can be implemented in 3D printing that is called VertureTech. Is a material that allows us was to embed, let's say, a new natural compound into polymer. When I speak about this natural compound, is a natural mixture of mineral that allow us to convert carbon dioxide, nitrogen oxide, volatile organic compound from the air and mineralize this compound into a series of non-harmful crystals, minerals. And what we did at the industrial scale was all a work of starting to apply through a process of master batch, which is an industrial process, these mineral characteristics into polymers. And I mean, master batch is a very important and delicate process that allow you not to change the characteristics of the support material, the base material, keeping all the technical and mechanical performance of the material, but also embedding or integrating new opportunity, new characteristics in this new compound. So what we develop is a new plastics, if you want to say, based on PLA that allow us to maybe compare our solution with what a leaf of a tree is doing. And we started to implement and as well associate these material characteristics to different series of solutions that we started to define. Of course, when you develop something new, you always need to validate its impact, and that's why we also started to collaborate with the University of Alicante, which is the university that in Spain is providing all the license and for all patents they are producing here in the Spanish country. And as I said before, we started to collaborate, use this technology to enhance as well a plural, let's say, movement that could start to, through design, embed, let's say, start to engage with the opportunities that this material can offer. So again, we started to design chairs with external reference, with our designers here in the office, like Eugenio Bettucchi, Laura Civetti. And thanks to the really dynamic environment that we have here in Barcelona, and not only we have the opportunity to present them in different exhibitions, like the one of industry that is here in Barcelona. And another interesting part that I would like to mention is the as well contamination. I would like to use this word that we started to make over the fashion industry, which is of course a territory that is not our main one. But it's interesting that we also, with the same purpose, of starting to introduce new protocol that could maybe enhance a different sense of ecology, we had the opportunity to introduce. So we started to think about new textiles, of course, as well, working with fashion designers, think about new fabrics that could allow us through 3D printing to produce thanks also to computational design, a new sense of performance and aesthetics in these garments, and as well connect the possibility that we have through computation of shaping multiple solution, connect potentially these fabrics to body and performance. I'm not gonna explain you here, but as well introduce practice that allow us to digitize pattern making, working with cloth, and as well simulating material performance and behavior. And this is one of the first garments that we produced for the Rome Fashion Week. Was also winner of the first award. And the last comment I would like to say, to speak about is as well the collaboration in the construction industry of this that we started to trigger again with external reference and other architects that started to work with us, and the production, as I said before, of new material components that could allow us, thanks to their characteristics, spread the impact of this material over different habitats where the material itself is introduced. And lastly, happily, I want to also mention the next pavilion of Spain in the Expo Dubai, where we will be introducing in the Spanish pavilion this material to create a new digital and physical forest that will be represented by more than 142 trees that will also produce energy. thanks to bioreactors that will be introduced and will be fabricated with our material, absorbing and neutralizing pollution from the air. So thank you for your attention, and I hope I didn't speak too much.
Thank you, Aldo, for the presentation. We will move on to our next, and we will reserve the questions and discussions at the end of the first session.
Hi everyone, my name is José Pedro Sousa. I'm a professor in the Faculty of Architecture of the University in Porto, where I also coordinate the DFL, a research group on digital fabrication. My present... Can you stop, please? Dragos? I will do myself, okay? From here, I'm sorry, so it's not working well. Okay, can I share my screen? Okay, I'm gonna share very quickly. Okay, I think you are now seeing my PowerPoint, right? Yes, okay. So, good morning, everyone. My name is José Pedro Sousa. I'm a professor at the School of Architecture in Porto. I would like to thank Alberto Esteves for this invitation and also to congratulate him for celebrating the 20 years of research in the field of genetic and biodigital architecture. So as a former student of the Master in Genetic Architecture, it's a great pleasure for me to be part of this event. So my presentation is called Some Thoughts and Experiments on the New Cybernetic Digital Architectural Design. And I'm gonna start and discuss it by showing these two pictures. On your left, you have a hand drawing from the 19th century, and on the right, you have a digital drawing from the beginning of the current century. If we look at both, we realize that despite the architects were using totally different tools, they were still thinking and representing their idea in the same way. So a way that was based on 2D representations like plans, drawings, and sections. What we can learn from this is that it doesn't mean that by using a computer, we are automatically innovating or exploring totally different new conditions to develop our thinking and our design processes. So something regarding the use of computers should be there that could take us to a new level of exploration. And looking for that new level, looking for the specifics of computers, I was impressed when I was graduating in 1999 through this magazine that was featuring the work by Ben van Berkel and Caroline Bos. And inside of this magazine, there was a series of representations like diagrams, complex 3D models that were totally different from the plans and the sections that I used to see doing by using computers. So to know more about this kind of more scientific representations and to know more about these diagrams that I couldn't understand very well, I enrolled in the Master in Genetic Architecture, so back to 2002, which was one of the first programs in the world dealing with these technologies. By then, it was structured through two parallel and complementary routes. The one concerned with the cybernetic digital architectural design, and another one concerned with ecological environmental architectural design. Because regarding this presentation, I'm focusing on this one, because it's very connected with my curiosity regarding those kind of representations that I saw in that magazine. And I would like to recall this piece from an article by Alberto Esteves, where he was envisioning this new cybernetic digital architectural design as a kind of a process where the use of computers were totally different than, or proposing something very different from the use of hand drawing. So for Alberto, computers should provide a support to a new kind of representation that should act not just as a simple graphic representation of an idea that was preconceived in our minds, but instead that kinds of representations should help us to think about our design processes and to help us discovering together with the computer the path and the ideas towards the solutions for our design challenges. So with this framework, we can find that in some masters in the past, some of these roots of this kind of thinking and interest we can find in Dürer, in Alberti, also in artists like Solevit, that were exploring drawings and texts to describe an interest on generative devices to explore and represent form. But we can also find this kind of interest in other masters like Gaudí, Joseph Albers, or Fraiotto, who explored the physical models that could work in a more interactive way to act as tools for thinking and developing design processes. So not just to represent a fixed idea preconceived in our minds. So with these two routes, architects revealed an interest in explore generative devices that could represent their algorithmic kind of thinking. So in the master, I contact with two key technologies. One is the computational design, by then using TopSolid, a mechanical engineering software that works parametrically, and also the digital fabrication technologies that showed how digital information could be extended into reality, into the physical world of atoms. So the combination of two, computational design and digital fabrication, have been reconfiguring totally new conditions for developing architectural projects in the last at least 2 decades. And it's these new conditions, or it's within these new conditions, that I have been developing a series of works in academia and practice and research. And I'm bringing here to this presentation a quick overview of 5 works that in the last 18 years show this exploration of these potentials that computers can offer to architectural design practice. So since we are virtually in Barcelona and celebrating these 20 years of research in genetics and biodigital architecture, I found it that was interesting and funny to bring the work that I did in the masters. So this was a first work exploring computational design in a more comprehensive way. So I took the challenge of mass housing that usually is solved using repetitive kinds of solutions, sometimes combinatorial, but let's say the customization of the solutions is very limited. And one of the reasons is because of the systems of representation that are not sufficiently flexible. So here, I started by exploring using physical models, the idea of a housing typology that could adapt. And this typology was structured in 3 different spaces: private, common, and the access in between. and I defined a series of rules for each one to grow or to adapt, to change their condition. This thinking, these rules were implemented in a parametric model using TopSolid. And so by playing with these parameters, we could change interactively the solution. TopSolid also allowed to connect to Excel file, and this could offer a different interface to relate to the model and to relate to the exploration of the design solutions. In short, those parameters were from three different types, one from the context, like the size and the shape of the site. Other parameters are architectural decisions, things that we don't want nobody to change because they keep our design intention intact. And other parameters we allow client to change, for instance, like areas or sizes of some spaces. So this we allow clients to change. I think these kind of parameters are happening in every kind of project, but here using computation we can embed it in our model, and we can start exploring different solutions in a more efficient way. So this is an animated GIF that show a little bit how changing the parameters produce automatically different solutions for the house and for the organization of those three spaces. Moving forward, and this is a final picture that also unveils a little bit the materiality that I was thinking by then for this house. So this kind of organic model was very different, was very difficult to let's say experience using analogic means. So this was a first demonstration about the potential of computation to inform an exploration of customized housing solutions. Another project is from practice a few years later. This was done together with my colleague, Marta Malea-Limain, with whom we run the office called Red Research and Design. So this project also had the assistance of Teddy Slowick. This project was done inside of the Kunsthaus in Graz, where we were commissioned to develop an installation to support an art exhibition on the topic of medium-sized cities. So this building has 2 floors. I'm going to focus on the first floor, where we were intrigued by this monotonous grid of lights in the ceiling. So we decided that we could do something starting from that infrastructure. And looking into this plan, we can see that the exhibition consists in several works of art disposed in the ground and organized in topics, these colored areas. So our idea was to suspend from each light in the ceiling a piece of folded fabric with different lengths in order to create a kind of inverted topography on top of each area. To do that, we couldn't design each flag one by one. So we did a script with AutoLisp that could run in AutoCAD. And this script was assigning a specific length for each flag, depending on its distance to the center of the thematic areas. So if something changed in the shape of the thematic areas, the center would change and everything would adapt to that new condition. Using this script, we could see the 3D model of every solution that we were testing. And we could also introduce or work with an extra information like the labeling of each flag and the area of material of each flag. So at the same time we were looking from the aesthetic point of view, we could know a little bit about the cost and the amount of material that each solution would take. The script also generated automatically the 2D contours for the CNC laser cut of those flags, which happened in Germany. These are the only printed documents that we did because each flag has a specific light to be fixed on. So using these maps, the solution was installed in the Kunsthaus. This is a little bit the effect. So you can see here this subtle topography that suggests the transition from one area to another area without a physical barrier. These are a few more pictures of it. And just for curiosity, This is what we did in the second floor. Another project is different. So here we are not working with hundreds of different elements. We are working with cork, a material that I've been very close since my PhD in 2004, which is a natural material that when you remove from the tree, you don't kill the tree. The tree regenerates and creates a new bark that could be removed after 9 years again. And this cork gives origin to different products. One is an agglomerate that is used as an insulation material. But in 2000, Álvaro Cis and Souto de Moura explored its application as an external cladding material in the Portuguese pavilion. So this opened a new application for cork and a new interest in this natural material. And the company Amorim Isolamentos challenged me and my colleague Alexandra Paio from Isqueté to design their stand for the construction fair in Porto in 2013. And we were running a postgraduate course on digital technologies by then as a partnership between the two schools. And we defied our students, Pedro Varela, Maria João Oliveira, and Manuel Novo, to design that stand. To do that, we started from this concept of the catenary curve, a curve that assures a shape that if it's materialized with a rigid material, it can work perfectly under compressive forces. So because cork is very good in compression, very bad in tension, we use this kind of geometry to drive the generation of a series of arches with which we model the shape of the pavilion. So this is a very organic shape, very fluid one that follows a specific geometry that assures the right structural behavior of this material. So everything was laid out and prepared for the fabrication through parametric design. And here you see at Isqueté in Lisbon the CNC cutting and assembly of some arches. The work was installed then in Porto at Exponor construction fair, and these are some pictures of the final result. So it's a very organic shape, irregular, which geometry was facilitated by using computational design and digital fabrication. So it's a 100% natural material, what you see here in these images. We also did other works with cork, other pavilions, facades, and also the experimentation by combining it with other materials. Another work is a student work that was done this year. I'm going to present the work done by Tiago Rosa and Vasco Calheiro. And in this work, we are still concerned with the performance of the solution, not only from the structural point of view, but also from the solar and daylight point of view. So the students were asked to imagine a kind of a free-form shell in the school. To do that, they explore Kangaroo, where they simply have to define the places where their solution should be fixed in the ground or in existing infrastructures. So there's a mix of intuition and economy of means, because we just specify this, and then the computer, let me just, and then the computer generates the solution. I don't know, it's not running. Then the computer generates the solution automatically for us. Just 1 second, because, okay, I think I'm having here a slight small problem with it. 1 second. I think the computer just, okay. Okay, let me see. No, I cannot show the video. Okay, sorry. Yes, just, yeah, I'm gonna move forward, but this just blocked. Just 1 second. Second. I don't know why it's blocked in this slide. I'm sorry. Okay, so I'm gonna try to move forward. So the students, after generating the solution, they also develop a series of solar studies to test the light without the solution and with the solution in space, and also a shadow analysis to see the impact in the ground. So with these two informations regarding the performance of the project, they could go back to the generation of the solution and refine it. We also exposed them to Galapagos, so they could put the computer using a genetic algorithm to optimize the shape to reach a specific goal in one of these parameters. And this is a picture that renders this solution in the end, simulates it. I'm gonna conclude with a final work very quickly. So this is a work using robots to build brick structures. I'm not gonna run this video because I'm afraid that it can block again. But everyone that is familiar with the robotic processes knows that this is a very common application of robots. So to use it to sorry, I was afraid and it really blocked again. Okay, to use it. Okay, I think you are seeing, right? Okay, so to use it to assemble brick structures. So we did a series of works like this, and over this experience, what looks for us is that this was a very deterministic process. You have a fixed 3D model, you send to the robot all these coordinates of the bricks, and then the robot builds what was predefined before. So together with the colleagues from engineering, we tried a different way of connecting with the robot. So we started by having a paper, and everyone could draw a line in that paper. And the robot, through a sensor, could read this curve and vectorize it. And then the computer could automatically, without any intervention, generate a brick structure out of this curve. The only thing that we specify in this program is the tectonics of the bricks, how we want them to connect and to fix together that will assure a certain look, a certain aesthetics of the structure. So by embedding that logic, the computer generates any kind of brick wall starting from any kind of drawing. And so we just simply draw this line and we see the robot building this structure. So this is a different way of connecting with the robot. So a different way of connecting a cyber system with a physical system, a different way of connecting drawing with physical construction. And with this different relation between human and the robot, I will finish this presentation. My apologies for the problems that happened through this presentation. And I hope these 5 projects somehow framed a little bit what could be and what have been these emerging opportunities that we as architects can take advantage from engaging with digital technologies to address some of the challenges of our contemporary world. Thank you very much.
Thank you very much, Jose. We will continue with Jorge. I will post directly his video, and then we will have the discussions at the end. So give me a little minute.
Yeah, hi there. I just want to say hi, so you know I'm here.
Okay. Hello. Welcome.
Hi.
So I need to take this away from here. Share my screen.
title of
Okay. So.
Hello everyone. The title of this presentation and paper for Biodigital 2020 at the UIC Barcelona is Building for Complexity, Insight into Growth, Self-Organization and Adjustment. Authors of this paper are myself, George Stojanovic, and Milica Vujovic. I am a senior lecturer in architectural design at University of Melbourne in Australia, while Milica is a PhD candidate at the Department of Information Communication Technologies at UPF. Our emails are listed below. Starting point of our study is an ongoing project and specifically a prototype which we have presented in the format of a poster at Cadria conference a couple of years ago. We would like now to show the development since then and talk more about the continuing efforts in this study. We are interested to explore the use of bio-inspired algorithms to study complex spatial systems. And by complexity, we mean growth, self-organization, and adjustment. And we are interested to study complex spatial systems as something built and constructed, which is material and physical. And therefore, this paper outlines the algorithmic design framework for the making of an experimental branching structure, enabling correlation between geometric features, structural behavior, and assembly constraints. Before we move on with the presentation, we would like to acknowledge contribution from architect Milan Katic and his role in the design and construction documentation development, and artist Branko Pavic for his contribution in the concept development. In Tehran. Tried to build the structure using a set of oral instructions and a rule-based approach. A group of 10 students were working together, but without conventional architectural drawings, and the entire coordination of that group was based on following few simple rules, which have resulted in a structure of this sort in the end. to 6 or 7 meters. Again, using a similar elastic material and similar rule-based approach. Again, this is produced at University of Belgrade and presented at ECAD conference some time ago. While working on this iteration, we have made an important step forward by moving into a digital environment and developing a bespoke tool to control material properties along with a geometric modeling. This is a plugin developed for Rhinoceros platform, which is available for a free download, which has its own command toolbar and way of controlling material properties, namely elasticity of the material, which was essential for making the structure. Was presented, we have worked in the structure. We have worked on the project which was presented at the Acadia conference, which essentially was a continuation of the previous one, except that we have reduced the elasticity of the material. I have moved on to work with more stable materials, and therefore we have encountered a different set of challenges. A lot of challenges, but also it was something that gave us a lot of ideas how the project could move forward, and we've realized that by replacing elastic material with a more solid material, we will have an entirely different set of challenges to work with. Instead of wood, we have made a decision to work with flat steel plates, and the intention was to end up with a structure looking this way. This is one of the outcomes of this study, a flowchart capturing the design process and showing three main stages, and gives an overview of the tools that we've been both developing and employing throughout the design process. Three stages can be seen on this slide. At the top is the wireframe model. It's the first step of the process. We've used a set of rules to simulate branching geometry observed in trees. We've ended up with approximately 3,000 edges, while their lengths and angles were only provisional at this stage. We've moved on to produce a solid model, where we used finite element method to establish sectional dimensions. The entire structure was divided into several cantilevering systems, and according to the analysis, elements at the top and the outer perimeter of the structure were assigned with smaller sectional properties because they were carrying less structural load. However, we've ended up with a structure measuring 3.4 tons in weight. And in the final, or the third image here, we can see the 3D model with individual element labels. This is the segment of the design process dealing with the assembly procedure, whereby the sheer number of elements proved to be a challenge to keep track of all of them, and also working with building tolerances proved to be another big challenge and issue in this project. So roughly looking at these three different stages, we would like to draw a parallel with the properties of living systems, which we recognize in growth, self-organization, and adjustment. This slide shows the way information is extracted from the 3D model to provide a table of quantities. On one side, we can see 8 columns responding to different sectional types. We have consciously limited the number of sections to ease up the manufacturing process. And on the other hand, information is extracted to provide a cutting template for a water jet. Importantly, we have devised a system of interlocking joints, and incisions on each of the elements were there to provide elements coming at each other at a certain angle, and this was essential for the assembly procedure. We have produced a prototype at the scale of 1 to 2 of some 20 or 30 elements. We've tested the interlocking system and have found a certain degree, but not overly convincing way of putting them together. We have noticed that issue of building tolerances is going to be a big challenge when we move to produce larger sections of the model composed of more elements. And if we look at the final image of the presentation, this is where we would like to show algorithmic design framework once again, and rehearse the 3 main stages and the role of bio-inspired algorithms in this process, where we've used a rule-based approach to generate a wire model, focusing on the number of edges and their length. Then we would move to structural properties, and we would utilize the finite element analysis to produce a solid model. If analysis would show that sectional dimensions were extending a threshold of 160 millimeters by 15 millimeters, we would then change the geometry. This is how we would close the first feedback loop. And in the third stage, where we would focus on the assembly properties, and we would deal with the issue of sectional orientation, and this is where genetic algorithm is applied to evaluate a number of possible solutions before we would settle for the most optimal one. The system was working under the premise that angle below 20 or about 100 or more than 130 degrees is unsuitable for the system of interlocking joints that we were proposing, and should that condition materialize, we would go back to structural properties and geometric properties, and then we would change the entire model in an automated sequence to avoid unfavorable angles and improve the entire structure of the model. This diagram is one of the main outcomes of this study at this stage. Shows the flow of information and also sets the grounding for future research. This is it. Thank you very much.
Good morning, everyone. My name is Alexandros Stafiadis, and I'm a PhD candidate at the Department of Architecture at the University of Thessaloniki, Greece, under the supervision of Professor Ioanna Simeonidou. The title of this presentation is High Performance Biological Structures, and it's part of my ongoing PhD research on biomimetic design. High-performance biological structures and materials have evolved through billions of years of natural evolution. The present research focuses on protected biological structures that demonstrate exceptional mechanical properties while providing impressive toughness, damage tolerance, and impact resistance. A wide variety of organisms have been selected in order to identify diverse natural design solutions. 5 of these structures will be presented, and their structure, properties, and potential applications will be examined. The first of the organisms is the mollusk Chrysomalus commiferum, which was recently discovered in the Indian Ocean. Its shell is a tri-layer composite structure. More specifically, the mineralized outer layer consists of the iron sulfide greigite in a microgranular structure with a wave-like cross-sectional geometry. Next, an organic middle layer composed of conchiolin can be found. The calcified inner layer consists of the carbonate mineral aragonite arranged in a typical cross-lameral layer microstructure. Mechanical tests performed on the shell verify this hard, ductile hard pattern. The result of this structure is a damage-tolerant shell that employs several safety mechanisms like localized branching microfractures and mineralized layers, propagating cracks captured by the organic middle layer, convex shape dissipating energy and increasing stiffness. Lessons learned from this geometry can be implemented in construction applications, the automobile industry, athletic equipment, and synthetic armor. The second organism is the beetle Phliodis diabolicus, which can be found on the west coast of North America. Its exoskeleton consists of 3 distinct areas: the elytra, the lateral supports, and the ventral cuticle. They are connected by interdigitated layers of alpha-chitin fibers that prevent fracture through controlled localized delamination. The beetle's elytra is one of the toughest among insects, with an estimated lasting modulus of 20 gigapascals. It consists of the exocuticle and the endocuticle, which are connected by trabecula. Scanning electron microscopy reveals that they are composed of layers of non-mineralized alpha-chitin fibers in a Bulligan arrangement which augments the toughness of the cuticle. Furthermore, perpendicular strands of fiber protect against shear forces. Such structure can find application in construction, the aerospace industry, in medical implants, and in 3D printing technologies. The stomatopod Odontodactylus chilarus is native to the Indo-Pacific and is characterized by its hammer-like dactyl club that it uses to deliver high-energy strikes and fracture the hard outer shells of its prey. 3 discrete areas can be distinguished: the impact periodic and striated regions. The periodic region is composed of mineralized alpha-chitin fibers in a Bulligan arrangement, a design found in many other natural armors. The impact region, however, consists of a modified Bulligan design, where rotating layers are compacted at certain areas, creating a herringbone pattern. Chitin fibers extend perpendicularly through the layers for improved shear resistance. Nanoindentation mapping of the impact region reports a maximum hardness value of 3 gigapascals and a max elastic modulus of 60 gigapascals, with modulus variations corresponding to the wave-like pattern. Like other multifunctional biocomposites, the dactyl club possesses several safety mechanisms like localized tortuous cracking and propagating crack arresting between different region interfaces. It can prove useful in biomimetic designs in the aerospace and automotive industries, armor applications, as well as 3D printing applications. The fish, Morones saxatilis, can be found primarily along the Atlantic coast of North America. It is covered by tough and flexible teleost fish scales, which can be found on most modern fish. Each scale is composed of collagen fibers, partially mineralized with hydroxyapatite. 2 distinct areas exist, the bony layer and the basal layer, with the former being considerably more mineralized than the latter. They are structured by fiber plies that alternately follow a radial and circular pattern, thus creating a 90 degrees rotation from one layer to the next. Max elastic modulus of the scales is 850 megapascals and max tensile strength 50 megapascals. What is more, they demonstrate higher puncture resistance than modern artificial polymers like polystyrene and polycarbonate, which are characterized by their stiffness, lightweightness, and translucency. As a result, the hierarchical structure can find use in applications like translucent packaging, biomedical equipment, and protective gear. Citrus maxima, native to the Southeast Asia, is the largest fruit of the genus Citrus, while its tree can reach a height of 15 meters. Its pericarp consists of three areas: the exocarp, the mesocarp, and the endocarp. It is composed of cell material that creates a porous three-dimensional structure that resembles a foam. Its porosity gradually increases from 0% at the exocarp up to 80% at the mesocarp. This gradual transition also serves as a safety mechanism against delamination. The pericarp's tensile strength is 0.11 megapascals and its elastic modulus is 0.39 megapascals, which are rather low values. However, the protective mechanism of the fruit wall derives from its porous structure, which acts as a compressible foam. Compression tests at 50% strain reveal a 70% energy dissipation, while it subsequently restores 75 to 95% of its original height. The fruit structure can be applied in the aerospace and automotive industries, in protective gear, and even in the transportation of hazardous substances. By this point, it becomes obvious that a common trend emerges. All the described structures are multi-layer hierarchical biological composites. At the same time, however, their designs present a great diversity. A single metric or attribute isn't enough for an accurate comparison of such complex biological structures. Instead, an analytical matrix of properties and individual characteristics can be created, which may serve as a pool of potential design solutions and a design decision support tool for a methodological approach towards a biomimetic design process. You can see on this table all the important features and characteristics of the structures along with their potential applications. Each of the organisms seen here displays a different design strategy with regards to creating a protective cell. In some cases, high performance derives from the material, in other cases the microstructure or the geometry of the cell, as well as in the combination of the above. It is to be further enriched with biological organisms to form a database of protective cell features and characteristics that will be used in the next stage of this research, which is to design, manufacture, and test protective cells that are biomimetically inspired. In conclusion, nature has developed a diverse range of tough, impact-resistant, damage-tolerant, lightweight structures and materials. They achieve their exceptional mechanical properties through the use of multi-layered, hierarchical biological composites. All these design solutions were categorized in an analytical property matrix that could serve as a source of inspiration in the fields of architecture, engineering, and design. Possible applications can be found in construction, aerospace and automotive industries, synthetic armor, packaging, protective and biomedical equipment, and additive manufacturing. More details on this research and all the relevant bibliographical references may be found in the full paper within the conference proceedings. Thank you very much for your attention.
Good day, everyone. My name is Dragoș Brescan, and thank you for being here. My article is titled Energy Efficient Generative Design Through Information Prototyping, and it is the essential piece of a bigger puzzle that defines the ability of adaptivity and interactivity as well as energy efficiency within architecture. These characteristics are always dependent on information and the ability to gather it. If we presume the source of information is wrong, we can freely assume that whatever the output, it will be neither efficient nor properly adaptive. Thus, the main subject addressed here is the lack of information, which would determine an adaptive type of architecture that would perform at higher energy efficiency standards. We focused on this research in order to achieve environmentally supported and supportful edifices. Our starting point is based on a set of energy efficient strategies and certification standards. They are Passive House, Active House, NZEB, which is abbreviation for Nearly Zero Energy Building, and LEED, which is Leadership in Energy Efficiency Design. The Passive House standard is one of the most renowned. The standard aims to establish performance requirements in order to bring the overall energy consumption to a performance of nearly zero or even negative. It is based on 5 principles, one of which is the focus on insulation, glazing, which depends on the orientation and shading, thermal bridging, air tightness, and heat recovery ventilation systems. Moving on to the Active House standard, the concept is mainly focusing on residential buildings and its interior comfort. The whole concept revolves around energy efficiency strategies that are combined with specific attention to the inhabitants' health and comfort, as well as the environment and climate. It's based on 3 main principles that focus on integrating energy, comfort, and the environment into a whole, implementation of interactive systems, and high architectural quality as and inhabitant well-being. Now, moving to the certification standards, we have Leadership in Energy Environmental Design. That includes a set of rating systems for the design, construction, and maintenance of green buildings that aims to help building owners be more environmentally responsible. Also, we have the NZEB, which is Near Zero Energy Building, which is a movement of a standard which aims to evaluate and support energy performative buildings. The whole concept started as an approach towards a more suitable environment at a larger scale and has a lot of traction being adopted by the EU for future developments. Within energy efficient strategies, the main issue that we face is that of environmental change. It is imperative to suit the edifice to its environment in a manner that would generate the best indoor comfort with minimum resources to sustain it. We will categorize these strategies as being informational applications. So, environmental efficiency optimization can be achieved through understanding the site's constraints and its interaction with the development, derive a climate-responsive design, integrate high-performance technologies in order to diminish the resource consumptions, and add competency in green certification standards. But if we have all this information, what is the issue? I will try to give you a small hint. If we love doing this, all we can do right now is this. And the way 2020 is going, I'm scared that this will end up looking like this. And all joking aside, the big elephant in the room that most people got sick about talking is global warming. And the main problem with this is that it brings climate anomalies. And those climate anomalies are basically what affects our informational applications. This means that we have a lack of consistent database regarding meteorological information. Now, there are various ways to attain climate data, one of which might be a weather station, the World Meteorological Organization, Energy Plus database, which is an online site where you can find it for free, or Meteornorm, which is a software application that's been certified by the Passive House Institute. The thing with these sources is that the information they offer either needs to be managed in a valid weather format, has to be paid for, is either really old, or it can be received incomplete. The most frustrating factor is that it is at a general scale or a relative position. As an example, if we try to get weather data for Barcelona, if we go on energyplus.net, we can observe that on their interactive map, Barcelona is a little bit further away from the point where the data was recovered. It's an approximate 15 kilometers away. So the problem is that it's also dated from 1999. So let's see how we can collect the data. Now, in this case, our approach is based on informational prototyping. The term of informational prototyping resumes the practices of robotics implementation within the concentrated area of sensors and data collection that would be especially used in relation with interactive architectural design development. For this development, we have used the Arduino microcontroller alongside the Firefly plugin for Grasshopper that enables us to close the gap between computational and physical mediums. So we have envisioned this, the EDIS, or the Environmental Data Indexing System, which is a conglomerate of sensors that, similar to a weather station, collects environmental data at an hourly rate, but offers a direct connection with the procedural environment through specific communication devices, such as wireless Ethernet or GSM modules. The core of the device is based on an Arduino and a mount shield that allows us to easily connect the sensors with not too much soldering. And the whole device has 4 general sections, one of which is the connectivity modules, where you'll find a GPS module, a real-time clock, and a GSM GPRS module that connects the device to the internet. We also have onboard sensors, which are an atmospheric sensor for barometric pressure, humidity, and so on, a temperature sensor, and a lux sensor for light intensity. We also have some peripherals, which account for an anemometer, which gives us the wind speed and wind direction, and it is alongside an optical rain sensor. The last category consists in 2 solar panels for diffuse solar radiation and direct solar radiation, alongside a DC to DC converter that powers up the whole system. The main intention of the prototype is to be used in an assembly system scattered through various sectors of a city. This would generate a complete urban environmental map that would offer exact on-site climate, geographic, and air quality data in the file format that we needed. So the question is, how do we process it? Well, algorithmically, using Rhino and Grasshopper through what we like to call computational environmental evaluation, which is a way of evaluating the environment through computational supported applications such as Ladybug tools. The Ladybug tools represent a collection of free computer applications that support environmental design and education. These components are called Ladybug, Honeybee, Butterfly, and Dragonfly. For these experiments, we only use Ladybug in order to process the data collected. Now, Ladybug is a basic collection of tools that help us create 3D charts, sound paths, shadow range analysis, wind roses that shows us the direction of the wind and its intensity, outdoor radiation analysis on certain surfaces, as well as orientation optimizations. But the most important is one that is using the output data for computational 3D modeling. And this brings us to actual adaptive architecture. Now, adaptive and interactive architecture takes many forms. It can be a kinetic adaptation through which buildings are designed to allow parts of the structure to move. It can be material adaptation that refers to smart materials that shift their state in order to suit certain needs. Or we can have climatic adaptations, such as the interior of a building being heated up if outside is very cold. Now, in order to achieve true adaptations instead of simply responsiveness, there shouldn't be a one-way interaction between architecture and the environment, but it should be a constant communication between the 2 mediums, through which our systems can learn and change their way of reaction depending on the overall current situations. And only then we would have a true form of adaptive architecture. Now, about those systems, is there a single solution to all necessities? Surely there can be a lot of cases where we can have a certain system that can be applied in any situation, but that doesn't mean it is the best suited. So for this case, we envisioned the IBEL, short for Interactive Building Envelope Library. This is basically an open source library that contains interactive envelopes that are based on Ladybug computational evaluations, and that can be applied in a variety of cases. This will basically result in a collection of envelopes that can be fitted and parametrically adapted to whatever site. I would like to give credit to this year's generation of Biodigital Master students for the design and representations of the presented facades. Thank you.
Hello, hola, namaste. My name is Angad Barang, and I'm here to talk about the research paper, Architecture of Computational Ecosystems, which involves synthesizing autonomous design algorithms based on cellular automata. Well, the presentation is divided into 5 parts. I'll first talk about the abstract or the relevance of the project. I'll then talk about cellular automata and the key aspects of cellular automata that we have used in the project. Then we'll move on to computational ecosystems, which is a concept that is derived from the cellular automata. Then we'll see and demonstrate one of the computational ecosystems that we have generated, we have theorized, and we have iterated and prototyped. Then we'll talk about some of the results and the possible future directions for one of the computational ecosystems. Well, rapid urbanization and urban sprawl in particular has an enduring and deep impact on its neighboring ecosystems. And this is quite peculiar about architecture, because architecture, which is one of the biggest contributor of this particular infrastructure and this impact on ecosystem, does not sit well within its neighboring ecosystems. Nature and biological systems, on the other hand, reuse and repurpose existing operational systems which are symbiotic to neighboring systems. Architecture and architectural design in particular fails to do this because architectural design is institutionally segregated into design, analysis, and fabrication. And these aspects all work in isolation. Biological systems, on the other hand, perform design, analysis, and fabrication in symbiosis and at the same time, simultaneously. Learning from these aspects of nature and biological systems, the research proposes to theorize, iterate, and prototype operational ecosystems in computational environments. To start with recursive algorithms and to see how algorithms could generate, could have a generative impact and not just an iterative impact, we learned from late Professor John Conway's cellular automata, which is famously called as Conway's game of life. As you can see here in the demonstration, this is a typical result of Conway's game of life, which is populated by a typical cell in a 3x3 grid with 8 neighbors, and it follows certain rules which are designed anthropomorphically. Stephen Wolfram, on the other hand, developed lots of computational, lots of cellular automata to find patterns that could be seen in nature or natural and biological systems. The key binding thread that we find in both these researches is the existence of an ecosystem, or let's say a computational system, which is populated by certain cells or certain elements, and they are governed by a certain economy, a certain rule. But one of the key drawbacks of a cellular automata is the halting problem. An automaton does not know when to stop, and it keeps on repeating its algorithm without any time frame in mind. And this problem actually could be solved quite easily, could be attempted to solve easily by combining the forces of growth and decay at the same time while they are in a reciprocal structural coupling. But to understand these concepts more, let's see some of the semantics of the ecosystem, element, and economy, where an ecosystem could be a cuisine, a game, and the elements could be the key ingredients of this particular system, which are governed by some rules or some recipes or some tactics. Which then gives us the idea that an ecosystem is actually something that is populated by biotic and abiotic elements and is governed by some nutrient cycles and energy flows. Whereas elements, these are key things which have precise meaning or precise semantics, and they could just be forms, agents, or systems. An economy would be the rule that governs them all by means of growth and decay. And the stability in an economy would equate to survival, whereas excess would lead to insufficiency and decay. After understanding these key aspects of the element and economy, it naturally gives us four possibilities of ecosystems, and we would go ahead with a single element, single economy ecosystem for this particular research paper. The methodology followed here is to first theorize, to understand how a computational ecosystem would work, starting off with the ideas of a cellular automata. Then we would iterate to see how many possibilities could be achieved, and we would be prototyping. And this entire process wouldn't go in a linear fashion, but it would be cyclic in nature, and it would keep on amplifying as a recursive loop. But to understand more, let's dive deep into the single element, single economy computational ecosystem. Here, the element would be a cube, which would be governed by the economy of structural stability, where we would just consider axial loads and no shear or bending forces would be taken into consideration. So if we start the algorithm in this way, and we initiate it by spawning some elements, and we run it through a stock SESE economy, rules of structural stability, we would have some surviving elements after the first run. But then we would run it through a fabrication analysis to see if a fabrication strategy could be viable. Like in this case, a robotic stacking was taken into consideration, and a structural analysis to see if axial loads are acting in the same way and if the ecosystem is still viable. The surviving elements would then be subjected to cyclic redundancy check and chaotic behavior check. This is to solve the halting problem and to see if the algorithm is getting absolutely redundant, repetitive after a certain point, or if it is getting chaotic and beyond measures of the initial intended ecosystem. And this entire system would be in a recursive loop. Computationally speaking, it would be a while loop, and while this recursion is running, it would test for the redundancy and chaotic behavior. And the moment it detects it, the algorithm would leave this state and would it would reach its final state, which would be considered as the equilibrium state. So let's see some examples. As examples, we have some computational ecosystems with two elements, and as you can see, there are so many, only so many variations possible. But the moment we increase the number of elements, we have many more variations possible. And as you can see, some of the variations or some of the generations don't go beyond 2 floors, while some of them go up to 4 floors, and then they become highly repetitive, and then they leave the loop and they reach their equilibrium state. But these ideas are still computational. So we tested them with a test group in the form of a workshop, and we got them. We got these same rules built by people with small blocks which were glued together, and the idea was tested. And here the tests actually gave us deep insights into how the algorithm could be changed, and the tweaking led us to having a lot more iterations and a lot more generations. Here we can see 6 of the generations with 10 elements in the initial stage. And as you can see, if we consider a robotic stacking method as for fabrication, we see these different generations with the same element and the same economy, but with different initial states. If we consider a fabrication method that is based upon an FDM printing method, then we would get results which look something like this. As you can see, this would be printed without any extra structural supports, and the basis becomes slightly wider to accommodate the different printing, the different fabrication style. This algorithm was again obviously tested in different various conditions, and as you can see here, the animation shows if we increase the number of initial points, as in this case we have 20, the ecosystem goes much taller, as in this case it goes for 26 floors. So as a natural progression for this research, we would be diving deeper into fabrication in terms of FDM machines printed with a robotic arm, and that would lead our research into a direction of fabrication. Well, thank you for listening, and we will be looking forward to your questions in the Q&A session. Thank you.
Okay, Yomna, you're up.
Okay, hello. This is Yomna Abdallah. I am a lecturer at Helwan University, Department of Architecture and Interior Design, and as well an assistant professor at the Biodigital Architecture Master for this year. This presented work is a part of a research project that is for my PhD thesis about utilizing a lacase-producing filamentous fungi that is non-pathogenic for electricity generation and utilizing it in a self-sufficient system for achieving architectural sustainability. The presented work is a collaborative work between Cairo University, Helwan University, and WIC, as well as Arab Academy of Maritime Science and Transport. The work is about coupling the form and function of the utilized fungal strain that is able to produce lacase. Lacase is an enzyme that is an indicator and facilitator of an oxidation reduction reaction that is utilized inside a microbial fuel cell, which is this device. This device uses the fungal strain, which we identified in the NCBI bank, gene bank, as Aspergillus sidoi. It's able to oxidate the organic substrate in the medium and produce electrons that create the electric current. And to in an attempt of us to couple this kind of complex biological intelligence function with its form, we applied a kind of biological imagery study and a mathematical modeling analysis of this filamentous fungi. Yes, so this is the scanning electron microscopy imagery of the filamentous fungi Aspergillus sidoi. And this is extracted from the biofilm formed inside the microbial fuel cell, which is the device that we use to create this oxidation reduction reaction. And then in our attempt to understand this kind of oxidation reduction reaction, we analyzed it into two steps. And main two steps that are summarizing this reaction, which is the motion of the fungal cells inside the medium in search of their nutrient, which is the carbon source molecules in the optimum concentration, which is 15.1 gram per liter of carbon source. In this case was used a banana peel to achieve more sustainability. And these results are actually from a previous published work in the Journal of Microbiology and Biotechnology of the Korean Society of Microbiology. So to analyze this kind of reaction, we have created a model that combines agent-based modeling and cellular automata in order to create a biased random walk, which is the kind of movement that the fungal cells perform inside the medium. As presented in this slide is the code that we created, and it's summarizing the kind of motion from a freely wandering or a freely random walk of fungal cells inside the medium. Yes, inside the medium in search of the nutrients. And then when they start to sense the optimum concentration of the carbon source, which is the 15.1 gram per liter of banana peel inside the liquid medium, they start to bias the random walk in a phenomenon that is called chemotaxis. So we have now a freely random motion that is around 360 degree in the medium, and then a kind of adhesion or a kind of bias of this motion towards the optimum concentration of the carbon source molecules. And here we found that that we are our parameters are the agents which resemble the fungal cells. In this case, we limited the fungal cells population into only 10 agents in order to perform the study in a record history mode that we can picture to a somehow realistic way the motion of the fungal cells in a non-stop recorded path. So it was not advisory that we increase the number of the agents, because this was unrelevant to reality, as fungal cells are wandering freely inside the medium, and it's not logic that they can exist all fungal cells in one place. So we only limited the number to 10. And then we started to put the main constraint, which is the carbon source molecule concentration, to 15.1 gram per liter, which is the optimum concentration. And then we produced a kind of free motion around 360 domain of searching, and this is the domain that fungal cell starts to random freely inside the medium. And then we added an adhesion component that these fungal cells can adhere to the carbon source molecule to as an active site to start the reaction. As produced from the algorithm used, we have inserted only a kind of leading curves. These curves were inserted from Rhino, and these curves are to relate our simulation or our mathematical analysis of the reaction to spatial coordinates that we can adjust by ourselves. So we started with 7 curves that we initiated in Rhino and referenced in Grasshopper. And along these curves were the active sites or the different points that the carbon source molecule optimum concentration can be located on. And as exhibited here, we found that these resulting knots of random walking, biased random walking, record the total path of a fungal cell towards an active site. So each of these nodes or knots are the active site of the oxidation reduction reaction that summarizes 2 kinds of motions that resemble 2 kinds of biological phenomena, which is the chemotaxis and the free searching of the nutrients. In this case, we have produced a form that is identical or similar to the scanning electron microscopy image that we were presenting at the beginning. And to add also more of the function and form coupling, these pavilion or these forms that were utilized in an outdoor pavilion can be embedded with this genetically modified filamentous fungi to also perform bioluminescence activity, so that it could be increasing the surface area for incubation of these fungal strain, non-pathogenic fungal strain, for also performing bioluminescence, along with its ability to produce the lacase enzyme, the main indicator and facilitator of the oxidation reduction reaction, to produce bioelectricity from biological substrates. And in this final slide, we can see that the formal similarity between the scanning electron microscopy image and the final note, which resemble the recorded path of the biased random walk, and also the bioluminescence activity that we can insert in this pavilion. Thank you.
Thank you, Yamna, for the presentation. We will move on with Gabriel Fernandez.
Hello, this is Gabriel Fernandez Borsot, and I'm going to present a communication on complexity theories as a foundation for a sustainable biodigital architecture. The term complexity theories refers to a quite diverse set of conceptual and mathematical tools, such as general systems theory, theory of information, cybernetics, networks theory, nonlinear mathematics, dissipative structures, chaos theory, fractal theory, self-organization theory, complex adaptive systems, and transdisciplinary epistemologies. Despite this diversity, they all point to a common objective: to provide a new approach to a range of problems that, in virtue of the complexity of the involved systems, could not be successfully approached using previous methods. Remarkable examples of complex systems are living systems and social systems. Because the tools and models that complexity theories provide represent a conceptual leap compared to previous approaches, and because the interpretations they enable reflect a deeper understanding of the approach phenomena, Morin proposed complexity theories constitute a new paradigm. I propose biodigital architecture should be understood as part of this new paradigm or this new impulse. Accordingly, I suggest that complexity theories serve as a foundation for biodigital architecture in three ways. First, because many of the conceptual and mathematical tools used by biodigital architects derive from complexity theories. Second, because using the lens of complexity theories, one can justify the radically distinct approach to architecture of biodigital architecture. And third, because the evolution of complexity theories throughout its three generations provide relevant insights which can orient the evolution of biodigital architecture in the coming future. Let's see next each of these 3 points in more detail. For the first point, we can consider that basic conceptual elements such as feedback loops and complex models such as cellular automatas and L systems, to name just a few, were incepted in the context of complexity theories or found their more relevant applications in that context. At the same time, the most popular software packages used in biodigital architecture as Rhinos 3D, Grasshopper, 3ds Max and Maya, or processing, employ mathematical concepts and models situated within the scope of complexity theories, at least in its branch of nonlinear mathematics. Nonetheless, if this was the only contribution of complexity theories to biodigital architecture, one would not speak of theoretical foundation, but only of instrumental contribution. In order to see how complexity theories provide theoretical foundation, let's consider the difference between a mechanical artifact and a living organism. At first sight, one can notice significant phenomenological differences between the mechanical artifact and the living organism. The mechanical artifact is built or assembled, while the living organism is conceived, it is born and grows. The mechanical artifact is organized by an external maintainer, and it needs fixes and repairs, while the living organism is self-organized and self-regenerates. The mechanical artifact does not reproduce and it does not evolve, while the living organism reproduces and participates in the evolutionary process. Using the lens of complexity theories, one can trace back the origin of all these phenomenological differences to one systemic structural difference, which is that the mechanical artifact is made of pieces, while the living organism is constituted by cells. Pieces and cells are conceptually completely different entities, because pieces in mechanical artifacts contain information only about the function that they develop, which means that if I take a piece from a mechanical artifact, I will know nothing about the rest of the artifact. But cells contain a full map of the whole organism, which means that if I take any cell of an organism, I will have information about the overall being, right? If someone takes a cell from my skin, they will know my eye's color, and if someone takes a cell from my eye, they will know my skin color, because each cell contains a map of the totality of the whole being. This is what we call the holographic principle. This holographic principle makes mechanical artifacts and living beings a conceptually completely different entities. The conclusion is then clear. With the logic we use to design mechanical artifacts, we would never obtain something like a living organism. And again, the reason is that while in living organisms each cell contains this overall unified pattern of the whole being, in mechanical artifacts there is no any single specific place which contains such a pattern. Now let's use these ideas to build an analogy on the logic design. On the side of the mechanical artifact, we would find conventional architecture, in the sense that in conventional architecture there is no any specific place of the building that contains this unified overall pattern. In contrast, in biodigital architecture, and specifically in its genetic approach, buildings are designed in such a way that they are based in this conceptually unified overall pattern. In conclusion then, biodigital architecture is a radically different approach to architecture, based on the fundamental difference between a mechanical artifact and a living organism, and complexity theories help elicit this question. Let's proceed now with the third point: how complexity theories can provide orientation for the coming future of biodigital architecture. According to several authors, there are three generations of complexity theories. The first generation was focused on modeling phenomena for computation, and the second incorporated the notion of system with the generalized use of patterns. The third generation constituted a leap by incorporating the notion of subjectivity and transdisciplinarity, the need for multiplicity of perspectives. I suggest that biodigital architecture corresponds mainly to the first two generations of complexity theories by using these sophisticated digital tools to compute systemic patterns. And I suggest that biodigital architecture would take profit of incorporating the lessons of the third generation. How can this be done? First, by acknowledging that architectural spaces are not only functional spaces, but they enact ways of being in the world. Architecture, therefore, contains a subjective, cultural, symbolic, and narrative dimension. This is what the third generation of complexity theories refer to. This can be synthesized in the idea that the basic question of a society, where are we heading toward, is answered also through architecture. Then, in virtue of its privileged relationship with the world of life, biodigital architecture must play an inspirational role to address current sustainability challenge, not only by creating optimal buildings, but also by envisioning a new narrative, telling the tale of a better future for humanity, a future in which the relationship between humans and other species is that of conviviality instead of separation. And this can be done by emphasizing the value of the symbolic narrative that inspires the project. Most biodigital projects emerge from a starting seminal idea, which very often has a strong symbolic component. This needs to be highlighted. Thus, in addition to create a computational model which condensates an overall unified pattern for the project, the symbolic narrative would condensate the overall unified cultural vision, a particular narrative of the path to a more sustainable and harmonic world. Thanks for your attention. You will find all the details in the full text of my communication, and feel free to contact me at gavi@uic.s. Thank you.
So everyone, we were going to have a break for 10 minutes and then we are going to return with the next session. Thank you.
Going. Wow, that's amazing. Excellent. Okay, so I think we are ready too. Maybe we can share the screen. So tell me if you can see the presentation.
1 second. So, hi, nice to see you all. Most of you might know to just introduce ourselves a little bit. And as we have 20 minutes, we wanted also to introduce a new project we are developing in this period with UNDP. So the title of the presentation is Deep Green, Green Architecture in the Age of Artificial Intelligence. So Ecology Studio has been founded by Marco Poletto, who is here, and myself, and has got tight connection with academia. We direct a lab at the Bartlett UCL and one at Innsbruck University, where I hold a professorship in landscape architecture. And we have been having also a long collaboration with the IAC in Barcelona. So our work concentrates on the relationship between biology, computation, and design. One of the main stream of research has been the one investigating microalgae. We built the first urban algae canopy in Milan in 2015, so a bit of history, and the first permanent biotechnological dwelling in Astana in 2017. Lately, we expanded the morphological investigation, and with the Ortus XL that was presented at the Centre Pompidou in 2019, we started to work on a new form of bioreactor and a new material system. This is currently exhibited in Tokyo. Due to the current pandemic, this has been 3D scanned and is a virtual exhibition that you can all visit. In 2018, late 2019, we started the Photosynthetica venture, which is a consortium between the Bartlett, Innsbruck University, and Ecology Studio, which investigate the integration of photosynthetic organisms of various kind and color into architectural schemes. The first project was developed for the Climate Kick in Dublin. So the green ideology in architecture hides a nagging paradox. It proposes a sanitized version of urban nature that renders it ineffective towards establishing a new circular economy of matter, information, and energy. So we inherited from modernity, in our opinion, a linear vision of the city where resources go in and waste go out, but things are not recycled, not ecologically nor economically. Many of us, as we know, live in city, and urban population is growing continuously. But the urban is not simply the city, it's also the whole system of infrastructure that we call the urban sphere, quoting Marco Poletto PhD thesis, that sustain the city metabolism. How can we rethink this city metabolism? How can we reconnect with that, overcoming the current paradigm of zoning and proposing a new role for some of the byproducts, such as waste, but also bacteria and ultimately viruses, in rethinking the way we live city? One of the main organisms we have been tracing a relationship with are microalgae. These are some of the oldest organisms on the planet and absorb 50% of the world's CO2. They are also a consequence of climate change, as they are blooming as a consequence of the variation in nutrients that are present in the water of the planet. So, in that sense, photosynthetica enable us to design artificial habitats to grow algae within urban realm. Marco, do you want to join in?
Yeah, sure. So, I mean, this project essentially it's very much sort of design innovation project, if you want. But in that sense, I think that the significance of it is to be able to test in the real world some of the theories and experiments we have done in the past years. And this application It was the largest one we've done so far in Dublin. And it's really a kind of retrofitting application to an existing building, which essentially covers it or wraps it with a soft membrane, and which is very light and translucent, but nevertheless incorporates more than 1,000 liters of living cultures, which essentially function through, of course, the power of the sun and photosynthesis. That's what drives the system. And CO2 when polluted air is introduced from the bottom and naturally rises through the snaky algae tubes until it reaches the top of the membrane, and it's released back in the atmosphere. So the convoluted journey is designed on purpose so that the exchange between the air molecules and the cells of the algae is maximized. And algae have this ability to essentially eat everything that comes their way. They're very voracious organisms. And what is interesting and fascinating is that this process is extremely efficient if in terms of let's say its spatial implications. So if we compare it to the performance of a large tree, you can see that there is a quite extreme advantage in deploying these microorganisms whose entire body is photosynthetic. So 50 kilograms of those absorb the same amount of CO2 as 5 tons worth of tree. And the other interesting element is that the pollutants, if you want, or the let's say particles of air pollution are not just simply stored or filtered out like in traditional with traditional technology. So then you are left with a filter to somehow landfill. Whereas in this case, there is a real remetabolization process. The algae essentially use these the minerals in the pollutants to build up biomass. So essentially, that's where we can create a true circular economy of information, matter, and energy, which is ultimately the goal of the project. On one side, pollution, CO2 goes in, the outputs, the emissions of the city become nutrients for the system that in turn generates oxygen, biomass, and data. And biomass, algal biomass, as we know, is already feeding several emerging industries in the food, biofuels, and bioplastic sectors. So here is another application we have done more recently in Helsinki, and it was an interesting scenario because it was very much connected to sort of transitionary condition of these buildings, which was being refurbished. So it kind of illustrates also how this system could be used and deployed in a quite opportunistic way in situations where its benefits can be multiplied. Maybe Claudia, you want to continue a little bit on this?
So for us, the microalgae structure and infrastructure is very much connected with the morphology of the system, as you can see here in the urban algae arrows. The urban algae in itself was not conceived simply as an object and connect to the second part of this brief talk, because was part of the project Aarhus with City, which look at mapping the overall city of Aarhus and the effect that different element of green could have on the city itself.
I think it also recognizes the fact that the urban microbiome is a fundamental layer of cities and of urban ecology. So we kind of tend to forget its existence, but microalgae and other microorganisms are a part of the urban landscape already. And you know, essentially the design and the exploring this layer, it's a fundamental to urban ecology and to essentially developing an effective and resilient biocity.
So from there, we looked also at the integration of the material system. So in this case, we look at how there is not an infrastructure that supports the biological growth, but rather there is a material that integrates both biological growth and substratum. This has been carried forward in Ortus, but we are also developing at the moment a set of new prototypes that look at how these could be scaled up at the architectural scale. So how this unit could become effectively unit of co-living. This is a project that we developed for the city of Linz, which is a post-industrial city, and integrate, apart from microalgae, also a set of other organisms that contribute to the microbiota, such as birds and fungi. These are some of the special quality that emerge from the design of the space and the integration of microalgae, in this case on the internal part in a liquid medium.
Yeah, I mean, the scaling up, it's obviously not something that happens kind of linearly from an artifacts like Ortus to a building sites, but some of the operations can be scaled, like for instance the idea of filtering and extracting pollutants from the air actually becomes more significant when we operate at the urban scale, and the building morphology itself becomes a driver for this kind of urban filtering effect. And again, the kind of circular economies at the heart or at the core of the system and powered by these organisms, living organisms, they become essentially a way of reprogramming architecture. So the byproduct, the algal biomass that grows within the system at the scale of a larger architectural organism can become effectively the input to a whole series of activities that may take place within that architectural system. So that's where, let's say, the kind of spatial dimension or domestic dimension is kind of essentially expanded and blurred with other activities such as research and gardening and growing new fabrics, new products. So the idea is really to begin to imagine a kind of possibility for these functions to be integrated much more deeply in our daily life, whether it's working life or studying research life or leisure life and etc.
So this is what we have been exploring in a project that will be presented at the Venice Biennale 2021, when one of the hexagonal cell of Ortus become a living unit as part of the building proposal that we just see now. So this will be investigated as a one-to-one prototype or cohabitation between form of human and non-human inhabitation.
I think this issue of cohabitation, of course, is very let's say actual, because as we shall see in the last few months, there has been a complete awakening, I would say, from our side, the side of our civilization, in terms of the danger of ignoring the microbiome, and essentially also the possibility of imagining a kind of future of urban life without including the micro scale, in this case all the way down to viruses. It's now unthinkable. So essentially this project, and in particular the Biotech Hut, it's the first permanent projects of this kind in Expo Astana, and now it's part of the Museum of Future Energy there. It was really about that. It was kind of about imagining a prototypical dwelling where humans and integrated microbiome would coexist, would co-live, and essentially would also somehow symbiotically feed each other. And again, the project was organized through the lenses of science, which of course is our main tool to rationally understand and comprehend a world that we cannot see and perceive with our naked eye, but also through the lenses of art and experience. So again, this was another of the sculptures we created specifically for this project, and it was very much about creating the possibility for a direct immersion of the visitors in this kind of cloud of microalgae oxygenating their space. And again, this intuitive artistic comprehension is not just simply an appendix of the scientific work. We believe it's a necessary extension of the rational side of our way of comprehending the world. I think without this more intuitive, immersive understanding, we cannot grasp the full complexity of living dynamical systems and the way they operate within the urban realm. So, of course, this element was very much a critical aspects of it. And then the third zone was somehow bringing these two aspects together in a kind of a craft production way. We call it the garden. It was really the part where most of the living cultures would grow and would be harvested and therefore become available for use within the space of the hut. And again, these systems, the digital technologies that we today can use and can design, become an extension of these operations in such a way that the comprehension of what's going on at this microscopic scale become more and more visible to all, even non-expert or non-scientist. Yeah, here are some of the drawings that show the material system and how effectively the circulation of algae was directly embedded in the architecture.
So in itself, this data become an expression of the materiality of the biotech art, whereas for us, it's a shift from architecture as a machine for living to architecture as a form of living machine or living organism. This brings us to see data at a different scale. So as I said, in the case of the urban algae Horus, for us, this prototype are not isolated architectural component or isolated sculpture. In other case, they are part of a network or part of we imagine them as part of a network or part of a system that could have a territorial, if not global, impact, which is what we explore in a series of projects that led to the recent Deep Green project. In particular, here we see Tallinn. I had directed 2 years ago the Tallinn Architectural Biennale, which was called BioTallinn. And in particular, with Ecologic Studio, we investigated the water system of Tallinn, mapping its distribution and reimagine it as something that from being centralized get decentralized as much as possible. First, through a computational system that maps its potential, and then through the development of local prototypes.
What was interesting, actually, from the analysis of this, of the reality of the wastewater system of Tallinn, was that, in fact, we learned that up to 60% of the wastewater essentially was leaking through the network before even reaching the wastewater treatment plant. So, in a way, we could argue that although the diagram that we commonly share in terms of the wastewater network is this one, very much centralized, going from households to water treatment plant, the reality is much more similar to this kind of a simulated scenario of distributed intelligence, where essentially many particles escape the network and already permeate the ground of the city in a way that is much more distributed. And therefore, we can begin to understand the terrain of Tallinn as already part of an extended ecology or microbiome, very much unique of that city. So, part of the project was really to somehow bring that to life and visualize and materialize and these elements, but then also kind of take it as a direction for reimagining a future scenario in which these distributed logics effectively redefine the way the networks of the city operate. And therefore, in a scenario where buildings, park, public realms all become producers as well as consumers of energy and biomass. Here's some of the visions that we have created. So recently, with this collaboration with UNDP, we have been trying to sort of package these set of techniques and drawing logics that we have developed in the years in order to make them available not just to a selected pool of cities, but really to turn them into a tool for urban regreening or redesign. And this is a kind of let's say diagram of the basic workflow of that tool, which very much works from a set of inputs from digital elevation models, GIS, satellite mainly as a source. Of course, specific cities may have data sets that are richer than others, but pretty much everywhere it is now possible to extract this basic level of information to then develop a series of density maps that allow us to scan and understand the biotic and abiotic layers of the city. So this then leads to a kind of analysis of networks and path systems through the city, which can be related to different aspects of the urban infrastructure, and eventually to a redefinition of the urban morphology, so what we call scenario modeling, which these days benefits from the integration of algorithms of artificial intelligence, especially GAN, which we have been experimenting with. Here are some case studies. We don't go too much in detail because obviously the time is short, but in some case studies, especially these ones from the Synthetic Landscape Lab in the University of Innsbruck. And I think the interest of this is kind of showing how we can use these techniques to, on one side, analyze the particular conditions of certain landscapes, but also to fast forward or accelerate their transformation, their modifications, which in some cases really lead to a redefinition of what we understand as a kind of natural landscapes, or the let's say fusion between these elements of infrastructure and the element of the biotic substratum it redefines. And this is a case study of it's an alpine landscape actually near Innsbruck itself, where the whole idea of water retention and dams is a kind of redefined, redistributed through the valley. And this is actually a case in Africa, where in Accra, I think, where students is looking at landfills, and in this particular case is e-waste, which is particularly polluting kind of waste, which is now unfortunately shipped here from many parts of the world, including Europe. And again, ideas of how this heavily contaminated anthropic landscapes may be reimagined and redefined through these kind of techniques.
Maybe we can go to the UNDP project.
Yeah, maybe
we are a bit over time.
We are late. Yeah, okay. Yeah. So a few other examples I think very compelling.
From the synthetic landscape.
Yeah, this is from Innsbruck students and researchers. This is also a thesis project, very successful, showing Kathmandu's landscapes being redeveloped to kind of bring back its ability to retain and filter water coming down from the mountain ranges, which today it's unfortunately canalized and contaminated when it reaches the city.
So this brought us to the project that we start now 1 year ago with UNDP, United Nations Development Program. We look mainly at 3 cities across the planet in developing countries. Here we will show some of the research developed in Guatemala City. Guatemala City has a very peculiar topography with problem of erosion that are strengthened by the fact of from the waste disruption of the waste management system.
So essentially what happens is that the city right now is being eroded from beneath this little crust of built environments. It's a very spread out city, but very much like a one layer city. And so these kind of conditions happen because of the erosion of the subsoil, and therefore in unexpected ways these huge holes appear in the middle of the city, and then obviously this is extremely worrying for the city itself. So essentially the project was looking very much at this territory from at the infrastructural point of view, and how the management of these processes of construction, and especially of waste collection and recycling, could be activated at the level of the local community, local neighborhood, and then this local level could lead to larger strategies being implemented at the municipal level, with the kind of main key collection points for the city to be located in strategic areas, which effectively we have identified through this type of analysis.
At the moment, we are expanding this analytical tool through an algorithm to translate these in effectively design proposal or prototypical proposal that the municipality could start imagine as form of architectural intervention in the city.
Yeah, here, for instance, we imagine a scenario in which this natural erosion that is occurring, it's almost fast forward and essentially used as a tool to create several dimensions in the urban landscape of Guatemala City. So if on one side key infrastructural routes and built areas are preserved and even reinforced and increased in height, other areas are essentially eroded, and the erosion is almost accelerated to reform a kind of a deep landscape, which then can be regreened and can absorb functions that the natural landscape used to have in terms of retaining water, filtering water, and creating a more stable structure in the subsoil of the city itself. I think this is it for today.
Thank you.
Hello, I'm Dilan from Newcastle University, and I'll be presenting the early work of my PhD. Today, in biointegrated design, living organisms like mycelium, algae, bacteria, or moss are being used as a material, and they all differ from one another. They have different qualities, nature, so the methods of producing them differs. So in this presentation, I will focus on mycelium. What is mycelium? So the mycelium is the roots of mushroom. It composes from hyphae, and hyphae is tube-like fibers and forms a random network-like structure. These are some examples. What can you do with mycelium? These are some examples of how mycelium is used in industrial design as furniture, in fashion as fabric, and in architecture as bulk material. All of these objects are produced in a form-determining mold. So molding is seen as necessary to control the growth of the mycelium. So currently, designers are guiding the growth of mycelium simply by defining the shape into which the organism will grow. So within current architectural practice, molding is the most popular parameter that is embraced for incorporating mycelium to biointegrated design. And how are they producing these mycelium composite materials? So the first step is mixing mycelium spawn in a mold with sterilized coffee ground sawdust and cardboard, or you can use any kind of cellulosic substrate. And in 2 weeks, they cover the whole substrate. To stop the growth, we need to expose them to heat over 90 degrees and dry them. Otherwise, they will continue to stay alive and keep showing metabolic reactions. So within the initiation of light, fruiting bodies or mushrooms forms. The process proceeds with a regular light-dark cycle that leads to cellular differentiation. So in short, fungus strain, growth conditions, and nutrients are the key factors that influence the characteristics of mycelium materials. Of course, besides the post-processing operation. So molding is an example of top-down fabrication methods. So the organism cells fill the negative space in a confined setting. But using a traditional molding technique reduces the degrees of freedom that the living creatures have. So they lose their inherent potentials, and neglecting that they have a metabolism and ability to grow and adapt autonomously in response to their environment. So these unique properties enable them to progress in many ways. How to guide a living material that has its own tendencies and grow it with minimum intervention. So within this research, I will try to use mycelium as an active material instead of an obedient one. And I hope this process will demonstrate a material making principle. So I approached forming fungus in 2 steps. The first is the mycelium and then the mushroom farming. So my initial experiment started with mycelium forming through its nutrients. Is the most basic one. So as an architect with zero biology background, I tried to understand how to inoculate seeds for future tests. The goal is to measure which way of seeding is the best growth and maximum surface coverage. So in this experiment, agar types, amount, they're all the same in every petri dish, but the seeding methods are different. So in total, I used 14 different ways of seeding. So the first variable is the layout of the seeds. So seeds are inoculated in varying numbers of groups of 12, 6, 4, and 1. And the second variable is the depth of the seeds in agar plates. So they can be above agar, half buried, fully buried, or floating in agar. Half buried with single seeding gives the best mycelial surface coverage over the agar plate. So for the all upcoming experiments, I use this technique. Another basic experiment was to see if agar amount changes growth in the short term and long term. So I measured the thickness of growth in day 8, 16, and 30. So the seeds were inoculated evenly, and everything was same on the agar. And the results show that the first 8 days there was no difference in mycelium thickness. But after 2 weeks, the amount of agar had a positive effect and increased the growth. And in another experiment, the aim of this experiment was to understand the oyster mushroom's preferred habitat. So I changed the nutrient medium and looked for the best volumetric growth. So there were 13 different combinations of dextrose, fructose, malt extract, and yeast extract. The results show that the ratio of 2 malts, 1 yeast, and 4 dextrose in MEDI 11 gave the best mycelial growth for oyster mushrooms. But keep in mind that it may not give the same results for other types of After understanding that what oyster mushroom likes, I tried to find a way to block the growth sharply through the agar culture. So the purpose was to manipulate the organism negatively in degrowth as well as expansion. So I saw acetic acid, salts, white vinegar, sodium bicarbonate could be used for this purpose. And there wasn't any growth in any of the media. So the results gave me the idea of maybe stress sources can be used to carve mycelium biomass or block the development at some, at certain points. So I tried to merge the information from my previous test, and my goal this time was to generate different paths with high to low nutrient levels for the mycelium to follow and grow. So I built a mini waffle structure with 25 cubicles. Then I filled 3 different mediums from the agar culture and growth halting experiment. So I inoculated each cubicle with seeds, and I assume that mycelium will grow more in its favorite mediums and less in its less preferred ones. So my dream was to develop a reproducible system. You can imagine the growth through deposition of nutrient like an inverted 3D printer. Inverted 3D printer. It worked, but after a while, the growth stopped and mycelium began to wilt away due to dryness and decreased nutritional value. So I realized that, I need an irrigation system to prevent this decline. So as a result, I understood that controlling the growth by feeding mycelium from specific points continuously can be used as a method to form it. Each cubicle can be imagined as pixels generating the whole geometry. So the nutrients needs to be pumped to the cubicles for the further growth. By receiving more food, mycelium will start to rise from the plane. So the more fed regions will grow more and help in forming the overall geometry. However, after a time, the increasing number of cells in favorable nutrients cubicles may reach to a point that, they cannot show any more growth because of crowding. Besides the seeds in the cubicles with less favorable nutrients will grow more due to the space around them. At that point, there is a need to have a scaffold, for mycelium to cling on. Otherwise the system will reach to a point where there is a flip in favorable cells are growing to give worse growing results due to overcrowding. And another problem with this mechanism is that it only feeds mycelium in one direction. So mycelium will only be extruded from the horizontal plane. That's why it will be limited generating any changes in section plane. Given these limitations, I found that growing mycelium in a bottom-up approach is difficult, but fruiting bodies can give more complex 3D structures that allows more obvious morphological difference. So in the future, I will continue my work with trying to form the mushrooms. That's all. Thank you for listening.
Currently enrolled in the doctoral program of Tokyo University of the Arts under the supervision of Professor Mitsuhiro Kanada. The paper presentation before you today is part of my PhD investigations that aim to study the ornament in our contemporary age of post-digital architecture, especially how this discourse has made its striking return in both practice through completed buildings and academia through published material. I would like to introduce a theory that reconciles and reconnects ornament to object to architecture, and prove that they can come together under the same narrative, leading to a redefined neo-modern era addressing the function of the sculptural object matter, aesthetics and society, spatial quality, simplicity and democratic accessible to all mass customization. Up to now, practice-based investigations has helped me to crystallize the following personal statement. Post-digital ornamented architecture is not ornamented. This statement is based on two main arguments. First, I rely on the hypothesis raised by Alina Payne on the genealogies of architectural modernism, where she asks what if in fact there has never been an ornament crisis, but only a shift, and the object as ornament was the underbelly of modernism. Second, I will argue on the importance and the power of ornament and patterns to create a bond between users and their environment when well codified in society. Within this framework, I consider Japan as a terrain of action and rely on the incommensurable creativity held in its Katagami patterns in order to translate them into architectures. This research aims not only to redefine the meaning of ornament, but also to explore new design approaches differentiated from the systemic usual space configurations. While many designers are diving in the algorithmic design world by developing new personal methods, I recycle the existing production of Katagami patterns into three-dimensional objects, perpetuating the artist's work and making their design go beyond time, borders, and scope of applicability. All the more, the current digital shift has given us new fabrication strategies and new methods to explore, produce, and stock geometry and data. Before diving in the topic, I would like to briefly introduce what these patterns are. Katagami are the stencil tools that Japanese artisans and artists use in the process of dyeing patterns on fabrics of kimonos and yukatas. Japanese minowashi paper is then sculpted by material removal through carving techniques as shown in the picture. Paper is glued together using persimmon tannin, then dyed using the katazome method that consists of applying a resistant paste developed during the Kamakura period. At the end of his career, an artist reaches a level of accomplishment as he, she, or they spend a whole lifetime mastering one technique and making his own tools. The Japanese have long been inspired by nature, but Japanese ornament is not a faithful transcription of the original shape. It is only a symbol of the vegetal and is often an exaggeration of reality and is assimilated by impulse and presentiment. The later we translate the pattern into its totality. Soichi Yanagi describes the transformation into beauty and the transformation into pattern and ornament as having great relationship. Therefore, to value the meaning of the ornament is to understand beauty. The later being a mystery, it cannot be palpated by the intellect. In a monocultural and metropolitan society like Japan, symbolic communication will be easy to incorporate. All the more symbols, iconographies, and patterns have been codified through various consensus. Other than architecture, daily use ceramic objects and textile ornaments, the 1926 Noboru Ofuji's official debut work and the first Japanese silent black and white animated film, Bagdaju no Tozoku, proves how ornamental patterns are a major cultural element. As we can perceive in the movie screenshot, both various characters and their environment being highly ornamented. In my exploratory method, I decided to work with bottom-up agent-based algorithms rather than a top-down parametric one. The advantage of programming lies in its ability to codify the design of the pattern through an agent-based behavior, allowing high precision in the generation of the form and a high-speed exploration of the different shapes. And despite the fact that all the properties of the pattern are not assimilated at the beginning, the process of trial and error will discover new generative aspirations. This diagram, for example, illustrates the famous swarm behavior as described by Craig Reynolds in 1999, based on cohesion, separation, and alignment distances and forces. In my work, I imagine the Katagami pattern points as a society made of many agents to which I apply a behavior to give them the ability of locomotion and self-organization, the three dimensions, while I store each particle coordinate at each time frame update and build geometry on it in order to get a spatial structure that emerges as a consequence of the system's behavior. The cases 1 and 2 investigate potential application as a wall surface and bring another agent class to interact with the floating class. A branching behavior was added to create branches between each particle current position and other particles' previous position within a distance threshold in order to control the density of the geometry and therefore the porosity of the facade thanks to the branching threshold and the frames count. It is important to point out that each pattern needed different parameters and number of frames. Let me share with you a short film illustrating the simulation behavior. This is a personal drawing of a speculative architecture after the formal line geometry has been taken into a mesh, and that could be 3D printed, for example, in concrete. Another pattern turned in another architecture. Despite being my personal production, I think that up to now explorations are somehow linked to the affect aesthetics linked to a Deleuzian conception. Jacques Rancière, in conversation with Mark Foster Cage in Aesthetics Equal Politics, tells us on the new superficial condition of architecture, echoing a propensity to live and perform at the surface of things. Frederick Jameson as well has observed how in many postmodern productions, depth is replaced by surface or by multiple surfaces. The contemporary subject similarly displays a marked tendency to recognize textures and patterns rather than forms and structures. I believe post-digital ornaments can perform in a different way than just a monolithic surface. Back to my rhetorical discourse and main argument, the ornament as a host for architectural function and user activity, ornament from optic to haptic, from surface to depth, from small to monolith. Alina Payne demonstrates how modernism was clearly about objects. She brings a new understanding of the early 20th century movement. She invites us to understand and read differently the well-known modernism radical aesthetics made of technology, mass production, clean lines, and unadorned surfaces that broke decisively with history by making the infamous Adolf Loos statement, "Ornament is a crime." One of her key arguments was that ornament has been detached from surfaces and was relocated in the objects that populated architecture space. 1925's Le Corbusier and Amédée aux Enfants, Pavillon de l'Esprit Nouveau, is what epitomizes her contention best. In that pavilion, there was no ornament, but what was remarkable were the pavilion's furnishings. Paraphrasing Alois Riegel, Payne wonders if this move from ornament to object was a move from optic to haptic. For modernists, ornament was always designated as a surface add-on, and the fact that it was associated to sculpture was a problem. Alina Payne provides the most direct summary by saying that the fact that ornament cut across scales and mediated between architecture and sculpture placed it even further outside the mainstream. Ornament and architecture was a topic, albeit a negative one, and objects and architecture was another one, but no questions connected the three. In this research, Japanese katagami patterns geometrical topology becomes a host for human activity and organizes the spatial. This is based on the Latin word ornamentum, and that has a common etymological origin with the verb ordino. The latest means to organize and to order. The following diagrams are speculative drawings of different functions and programs held inside the pattern. I imagine the katagami pattern as a scale topology delimiting space and receiving user activity. For instance, the first one being a cultural center hosting hosting activities such as art performances, fashion catwalks, or even a tribute to Hideyuki Nakayama's solo exhibition at the Tokyo Gallery MA under the form of a cinema. The second speculative diagram hosts, for instance, an office program, a reception desk, a waiting room, a meeting room, and co-working spaces. The third one consists of a private house made of a living room, private rooms, and so on. In order to transform the previous speculative diagram into architectures, the previous agent-based algorithm has been modified to create enclosures and control the height of the different spaces as shown in the two figures. The following film shows the behavioral simulation. Again, the generated geometry is taken into a mesh. When translated to a tri-dimensional object and scaled up, this ornament achieves both a structural and an architectural function. Through this framework, the human body engages directly and haptically with the new monolithic, large mass architectural object. The ornament becomes architecture volume, not a mere multi-layered surface outer shell at the periphery of the building. On a speculative level, one can imagine a tower in an urban context, here Shinjuku district, made of different floors originating from different patterns, and that can host different architectural programs at each floor. A stage where ornamented architecture would populate the city. In conclusion, the methodology and the morphogenetic experiments adopted in this research have demonstrated being able to generate a wide variety of spatial morphologies through the translation of traditional Japanese ornament and show relevant potential for applications on architectural configurations. By contrast to standard architectural process where an architectural planning and design are made following a design brief and constraints, blending ornament and swarm intelligence offers new possibilities to explore forms of design and architectural composition. The goal is not to produce clean geometries, but to nurture our imagination for early esquisse phases by generating basic data before starting to sculpt form, creating architecture that offers a new interest in space and forces the user to question his practice and curiosity. In this surrealist method of exploration, I abandon the search for the best solution and disrupt rationality, operation, and predomination of existing design methods. Prone in soberness, I reject ornament meant to produce a continuous stream of sensations and affects. Architecture should not be a monument for consumerism, especially how the contemporary world only value how fast we can absorb new information. For this, I would like to argue for a return to the roots of space experiment and aesthetics, making architecture deliberately difficult, inefficient experience, forcing the visitor to slow down and think, avoiding instantly consumable spatiality. In this theory, ornament is taking over the mediation role, inviting the user to reconnect with cultural heritage, reflection, and knowledge. Here, through the discrete materialization, the three-dimensional translated ornament is abstracted, distancing the ornament architectural object from the shock of the new base experiences, far from the superficial condition offered by postmodern architecture replacing depth by surface. Contemporary architects can achieve this goal through functional ornament, brought to architectural scale, and through aesthetics, far from a Kantian aestheticism revolving around beauty, but an aesthetic as defined by Jacques Rancière, the sensible experience. Thank you very much for your attention.
Sorry.
So hello everybody.
Welcome.
There is
So if you want to add anything, feel free to do so.
No, it's all right. Thank you very much. You can proceed.
Thank you. We will continue right now with Christine in just a second. Oh, no, actually, sorry, we're going to continue with David. Or I am a bit confused right now. Please excuse me for a second.
Okay, I have a problem with the video and the presentation. Wait a few more minutes. Yes, perfect. Good, so you can put me online. Okay, so hello everybody. Here is David from Architecture Studio 3 from the Academy of Arts, Architecture and Design in Prague. I will present you today a project which is called Granular Vibrations. It's a part of ongoing research project at our university, and this project is especially what we're interested in is especially material patterns and their behaviors in nature. And basically what it is, if you have some design and digital technology that is somehow nature inspired, we most commonly follow certain way how to approach this. And this is mainly focused on the way of how to digitalize material behavior, how to translate the material behavior into computer, and then how to actually work with this system that we have translated. What is our specific interest in our project, in our research project, is actually the relationship between this digital computational model and the material itself. So basically, if you have a look at the first image that is there now, it is a photo of one of our experiments, but you can achieve very similar image by a digital simulation. And what we are interested in is to compare these two models and to see what happens. So in a very traditional way, or let's say in a normal way, how we also approach the project is that we have some interesting pattern in the nature. In this case, it's a pattern of granular segregation. I will return to this topic a bit later. And we create a digital model. And with this model, we multiply, we somehow work with this model digitally, and we modify it digitally. And at the end, we have some object that resembles the original model and maybe even extends the original model from the nature. But what is very interesting is that if you compare the original and the digital, there is they look different, and they never have the same qualities. Actually, they have different qualities, and this is due to the fact of how we work with natural systems, because we, due to the fact that we have to translate this natural behavior into numerical values and into parameters that we apply either to a parametric design like as such, or to programming single, for example, particles. All this process undergoes loss of information. So we are losing information in digital model if we relate it to the original model from the nature. The particular interest of this project was actually what happens if we revert this project. What does it mean if a material is in a way inspired by a natural system? What happens if if natural system is inspired by a digital system that we construct, and how does do these objects look like? And the crucial question is, can we hack somehow the intelligence of a material to form an object, or how to do this? I think that to achieve such object, we have to see digital qualities in materials. We have to perceive materials as pre-programmed and intelligent matter. And I will now show you one such approach. So this is the process of granular segregation that I described at the very beginning. It's a process where a heterogeneous mixture of two granular materials at the very beginning, mixed in all together, are, due to the external energy source, start to separate into their original homogenic parts, which means at the very beginning we have a mixture of two materials. At the end, we have two materials which are separated. But it's very interesting that this process itself generates very interesting patterns. And these are the patterns that we first try to simulate to a digital, and then revert and try to create objects that are related to this pattern. So to add additional energy source for our mixture, we created a very simple machine. It's a vibrating machine which consisted of tray. You can see the tray on the right side, and the setup of the machine on the left side of the screen. The motor had some basic controlled functions like speed and rotations, and basically if we put the material in the tray, the whole system started to vibrate, and basically the video that you could see in the previous slide appeared, and this process appeared. Through the process of granular segregation, 3 different phases normally appear, and this is the first picture on the left side. You can this is the stable phase, where actually nothing happens, where only this is actually before starting with the vibration. On the picture number 2, you can, and number 3, you can see kind of movement towards a stable state phase, stable state of the mixture. And this happens through this through the exchange of the energies in between the particles. The interesting thing on this is that after certain time of vibration, it depends on the which mixture we have right now in, the whole system starts to tends to be in a kind of stable dynamic phase, which means that there is a stable pattern that stays and remains. What was particularly interesting is to trace the the path of a single grain through the mixture. Because as it's for us, it was at the very beginning a very random movement, but when we started to trace the mixture, trace the single grains, we could see that they form a certain pattern. So the video that you see right now is not a simulation of a particle system. It's actually a tracing of one particle through the mixture. So this is the movement of one grain, and what it showed is that there are also similar patterns that this movement of a grain actually very much follows certain path, and that very likely one single grain can in certain time in the future reach a specific point in the mixture. We can see that all the particles can speed up through the mixture, and they can actually almost stop in the mixture. This is all due to the reaction of the material with its with the tray and with its environment that it's placed in. This is one of the objects that we acquired from this mixture. This object, actually, how we got to this object is that we used thermoplastic granules, and after actually this pattern appeared, we stopped the vibrations, we took out the tray, and we heated up the mixture so that the pattern the grains can melt and the pattern can stay. What is interesting and what we didn't count on is that there is a second material, marks, let's say, and this is what you can see also a bit on this image. But maybe even more is that what we found out that there is a huge amount of options that we can set up and that we can kind of control or at least predict a bit, but we can never say how the mixture looks like. So actually every experiment in every experiment appeared very similar pattern, but in kind of different articulation. And this is something that is kind of unpredictable, and it is something that we more or less don't know from the simulations, because the simulation is programmed and we kind of can expect the result, but in this way the material actually really surprises us what it can do. And as we are getting to the end of the presentation, I would like to maybe compare the digital detail of a simulation and the detail of one of our experiments. I think that what we can see is that both images are kind of same, but that the image on the material has some extra quality or extra layer that is not included in the simulations. And I think that it is very hard to come to such an experiment, to such a result just by simulating the process. So there is every time since we've been doing these experiments, there's been every time something extra in the material that showed us that that there are some unpredictable situations that we have to or don't have to consider in our designs. And I recently read a really nice quotation by Mario Carpo, who said that playing with the material or working with material is like playing with a curious cat, that the cat actually kind of we can attract the attention of the cat and we can play with it, but we don't know if the cat will actually respond accordingly or how we expect. And I think that this is an interesting part, because this is something that we right now, I think, don't consider so much in digital architecture, and it's also in fabrication, that there are some aspects of materials and that through the programming translation are getting lost. And this is maybe such a comparison, this project, that can show that there is definitely something extra in the materials that we don't see, and yeah, that we should maybe consider in the future in our designs also, because it's part of the architectural expression and it can truly change the way how we see actually and how we work with materials. So thank you for your attention and have a good day. Bye.
Good afternoon. I'm Christine Yogiaman from Singapore University of Technology and Design, presenting the paper Cultivating Knitted Mycelium Composite Assembly. The paper outlined a digital design adjustment workflow that has been developed while working on knitted textile mycelium composite. The aim of our research project is to cultivate a new material textile mycelium composite that has the capability to augment final material composite properties and provide formal freedom to designers. Our work operates within the emerging material design practice that has increasingly been defined as growing design. We identify with the premise that this emerging material practice opens up novel opportunity for designers to innovate the functional possibilities of the design output through variations in fabrication processes. In the published development process of mycelium composite, we are most interested in the synergy and integration of the growing and shaping procedure, and speculate that textile as a sacrificial permeable mold would be able to augment final material composite properties and provide formal freedom to designers. The typical shaping method in the cultivation of the composite is the use of impermeable plastic molds that contain the substrate. In the middle of the cultivation process, the mycelium is demolded and flipped in the mold in order to ensure even exposure of all sides to air and extend the growth of the hypa on the side that was previously in contact with the mold. The permeability of the knitted textile would allow constant air exposure of all sides of the formed mycelium composite during cultivation period and hypothetically increase the density and extension of the hypergrowth into the substrate. The material composition of the knitted textile has the potential to be calibrated to increase growth of hypa at the surface through the incorporation of nutrient-saturated yarns. This is an early experiment we did to test if cotton and acrylic yarns will make an impact on the final mycelium composite properties. Preliminary data shows a correlation between an increased Young's modulus figure for mycelium composite cultivated with cotton compared to acrylic yarn. SEM imaging at the surface of the knitted textile mycelium composite provide evidence that the hypa is forming an interlocking network with the knitted textile, supporting the idea that textile mold has the potential to augment final composite properties. In the developing of the unit blocks for a prototypical knitted textile mycelium composite structure, the research team leverages the increased stiffness properties of textile when tensioned. This stiffness allows for the permeable knitted textile mold to be an effective mold container to resist the weight of the substrate when it's compacted into the mold during cultivation setup. The figure on the right visualizes the fixture that would be needed to tension a tubular knit textile to form the mold. To the left is our first 1 meter tall prototype test for this molding process. The resultant tubular mycelium composite units can be joined by a customized 3D printer connector. Within this formal typology, there is a wide range of design freedom that allows for the formation of branching or aggregated structure that is enabled by the unitization of the tensioned textile tube mold. Referencing the published development process of mycelium composite diagram, we gained an understanding of the cultivation and post-processing procedure from working with our collaborator and grower, Mycotech in Indonesia, and input our own digital design procedure prior to the cultivation setup. Through testing, we identify a critical mismatch within this transition of digital design to fabrication and the production of knitted textile mycelium composite that would need to be addressed to allow designers a degree of control in the dynamic nature of cultivating knit textile mycelium composite. We call this digital design adjustment workflow. In this workflow, the aim is to achieve minimal geometrical discrepancy between modeled geometry and final geometry. The digital design adjustment workflow does this by accounting for 2 types of distortion. The first distortion is caused by post-processing procedure. To terminate the mycelium growth, the specimen is dried through heating from an oven, evaporating much of the water content in the substrate, causing volume shrinking. The second distortion is caused during the textile mold assembly setup. The stretching and tensioning of the textile mold results in a Poisson effect, where the fabric mold shrinks in a horizontal plane perpendicular to the direction of the stretch. This is most visibly detected in the mid-length of the tubular mold. An ASTM C39 standard size cylinder of single diameter tube 72.5 mm and 122 mm height is used as an effective measure to calibrate distortions in order to control discrepancies between modeled geometry and final geometry. From testing, the drawing procedure caused shrinkage of the target geometry by about 10% uniformly in volume. To account for this distortion, the molded geometry is increased by the volume of 10%. To account for the distortion due to Poisson effect, the modeled geometry is widened in a manner that matches the shrinkage of the textile mold. Iterative physical calibration is done to establish the amount of widening at each course of the knit pattern to correctively identify the extent of knit mold geometry distortion. Here are the images of the testing and calibration process showing mold assembly, cultivation setup, and post-processing. 5 specimens of the final geometry aimed to be at 72.5 mm diameter and 120 mm height were prepared based on a previous outlined workflow. The final geometry of the unit test is then assessed for its geometrical conformance to the model geometry from the start of the digital design adjustment workflow. From the 5 specimens output, 4 closely conform to the model geometry with maximum deviation of 1 mm in diameter in specimen 1, 2, 3, and 5. This showcases the effectiveness of the workflow. The prototypical tubular textile mycelium composite unit presents 2 possible continuing development of the formal typology. The figure A diagram a formal structure type with hexagonal cells forming valence 3 joints interface that are connected by 3D printed joints. Figure B showcases an alternate structure of diamond cells forming valence 4 joints. The decision to locate joining plates in the middle span of the tubular struts reduces the complexity of 3D printed joints. This is a 3 meter tall column structure that is planned to be the continuation of this work, showcasing the effectiveness of the calibrated workflow to scale up the cultivation of knit textile mycelium composite assembly and the ongoing modeling of units of assembly. I'd like to thank SUTD International Design Center who funds this pilot research project, and special mention to everyone in the Dynamics Assembly Lab for their dedication, and our collaborator Microtech in Indonesia for their continued interest. Thank you.
Everyone, I'm happy to be part of this conference. Unfortunately, we're not together in Barcelona, but we're being separated here. I'm doing this presentation from Sarajevo, and I hope it adds to the big pool of information regarding biodigital design and biodigital architecture. As you know by now, my presentation is labeled Bioorganic Design Sources of Inspiration from the Mediterranean. And basically it looks back at our shared common history to draw information on how we can use historical design element in today's design, not only for today, but also for the future. I did a lot of research on Mamluk architecture and Mamluk design, and I'm not sure how many of you have heard of the Mamluks and have known where they were and where they lived, but mainly the Mamluks were in control of Egypt and Syria and greater areas of what is now Jordan and other coastal cities. They came from many different parts of Central Europe, but as you can see here, the Mamluks controlled Egypt and Syria from the capital Cairo from 1250 to 1570. This was a very short period, which was less than 300 years. But despite this, their art and architecture were considered the most exuberant, and that's why I'm very interested in their architecture and design. So there were battalions of Turkomans, Mongols, Circassians, Kurds, Armenians, Greeks, Slavs, Slovenes, Albanians, and Serbs. Their architecture was based on Fatimid, Ayyubid, Andalusian, and other sources that evolved into an indigenous local style. I'm not going to get into a lot of the details of all of these terms because we really have just a short time. But to give you an idea of who they were and what they did, a couple of images, one by Goya. This was the attack on Madrid in 1814. Of course, the date here is way past. They lost control of Egypt and Syria to the Ottomans. And basically what happened here is that Napoleon recruited them to attack Spain, and you can see him here being defeated by the Madrileños. But it's important to try to imagine and visualize what they looked like. Okay, we will start with one of the most important buildings. This is a complex of Qalawun. He was a great sultan of Egypt and Syria. And what's important about this building is that it really culminated everything that preceded it, all the design elements, all the concept, all the work that was done by previous architects and artists and craftsmen. I'm very much interested in the interior of the building, especially the entrance to his mausoleum. This complex has a mausoleum, has a school. It had basically a school for 4 sects of the religion. And it, believe it or not, it still has a still functioning hospital. But anyways, let's make a long story short and Look at the entrance to his mausoleum. Here you can see the stucco facade. It's full of detailed materials. These are coming from the west. The west of Egypt is considered Morocco, it's considered Spain, it's considered Tunisia. So this is what we call the Western influence. And I'm going to zoom here. And as you've seen from the introduction, that the Mamluks were mainly battalions that came from many countries, and there were many Christians among them. So you see a lot of Christian symbolism mixed with local styles. The fleur-de-lis, for example, is a symbol of the Trinity, and you will see it all over their Mamluk buildings. Okay, I'm interested here basically in looking at this fine detailing, fine stucco detailing, which I'm zooming in on in this image. As you can see again, it's a combination of fleur-de-lis. It's inverted, it's placed sideways, it's placed within other smaller motifs. So it repeats on and on and on and on. What's important here is these designs were basically based on organic vegetable designs. And these organic designs, or if you want to call them bioorganic designs, were not used in contemporary architecture. Mainly, they were not favored. Other geometric designs were favored. Okay, here is just a small attempt. Something I tried for this conference is what happens if we try to maybe abstract these motifs more and try to create something more viable, something that could be applied and used today. So this could be digitized and then manipulated parametrically to develop new design and do some more three-dimensional exploration. This is another image of the same complex. This is what I call the basilica. It's basically the mosque of the complex, but it was designed as a basilica. It has a main aisle, it has side aisles, and instead of an apse, you have a mihrab, which is the focus of the mosque. And I also found this image from the Orientalist period that was basically a fantasy of the interior of this mosque slash basilica. It's very close to the original, but it has a little bit of fantasy here. So I have to move quickly since we're tight on time. Basically, what's important about the designs, the Mamluk designs in general, and the previous designs as well, is that they were based on original classical concepts. So they were based on concepts that were developed by the Greeks, Aristotle, Plato, and basically through the research I did, I had them basically summarized into 4 elements: harmony, variety, balance, and proportion. And these will be used over and over and over again. It's important to look at this mosque. Actually, it was designed by Nasser Muhammad ibn Qalawun, which is he's the son of the Qalawun, which we saw his building earlier, his complex. But what's important here is this building was built using actually I should say pre-purposed or repurposed columns that came from everywhere. You have columns here from all over. But what's important for us in this conference is what's happening here with the Cosmatesco designs, where basically you have a lot of marble pieces that are being used in a geometric pattern that's curved to follow the half dome of the mihrab area. And again, if we zoom in closely and start looking at these designs, they were based on earlier Byzantine Cosmatesco and Roman patterns, but they were reapplied and readjusted here. And they're just infinitely expandable. Again, this in my opinion, could be digitized and reused to generate new design motifs in biodigital design. Very quickly, Ibn Rushd, he's a famous philosopher who again adopted Greek philosophy and did a lot of translations, and he was credited for exporting many of the Greek studies that were burned actually earlier, and he had them translated and saved into Arabic, and then they were translated into Latin and exported all over Europe from Spain to prompt the Renaissance. Okay, which takes us to Granada, which was the source of inspiration for many designs and many cultures. And you look at these star patterns, they have 8-pointed, 10-pointed, 11-pointed, 12-pointed, 16-pointed stars. They are in progression to basically infinity. And I borrowed a design by Dr. Estevez that he did earlier in 2009, where he adopted some of these designs to design the Hoya Park and Archaeological Museum in Almeria. Basically, starting with this looks like a 12 pattern or a 12-pointed star that was readjusted to fit this new design. You can see it here. It was made into the shell of the building. And to sum up, this is the basic motif that's being repeated and used over and over again. Thank you very much. I tried to stick to the 10-point limit, 10-minute limit. I'm now at 11 points, 30 seconds.
If you can to play the video, I prefer. Okay. Okay. Thank you. Okay. Right. Thank you. Hello, everyone. I hope everything is fine with you. My name is Ricardo Macenagago, and the title of my presentation is Biomorphological Signature, Bioinspired Design versus Bio-Design. It is a research in the bio-inspired design field that deals with the geometrical qualities that characterize the identity of the biological morphology. The bio-inspired design strategies could be divided into two main groups. On the one hand, the strategies that use biological structures as the material itself, or this ability to generate a certain kind of material. Strategies as living, genetic, and metabolic architectures stands out. On the other hand, the attempt to copy the biological generative process, highlighting the function-shape relation. Strategies as biomimetics and digital morphogenesis stands out. However, the geometry levels achieved by their solutions are different. The main problem of the biodesign is basically concerned with compatibility. They not follow the same rules and process, so something is missing. The biological geometry has been studied by several authors. However, only the research developed by Christopher Alexander focused the identity gaps through a relevant perspective. The author argues that the biosignature issue does not lie entirely in the geometrical characteristics. It also requires the process that generates them, which in his opinion is growth. It has been a quality almost denied in the human design process. Nevertheless, some applications exist. The concept of growth has been used essentially through the synthetic biology. However, in geometrical terms, related concepts has a relative balance has also been tested. Despite this shape diversity, biological structures reveal the same geometry degree. However, this degree could be divided in two. On the one hand, a main geometry completely independent of functional and metabolic issues. On the other hand, a secondary geometry that works simultaneously above the main one and where the cognitive entity inputs its functional and metabolic requirements. The bio-inspired design focus essentially in the secondary geometry, avoiding the essence of the shape. If the main geometry is part of the product, it cannot be denied. It is where the identity and compatibility works. So the growth signature follows at least three generative keys. Recursion, which is related with geometry and proportion. Transformation, which is related with reproduction. And dissipation, which is related with structural organization. The recursion process operates at two distant levels, geometry and proportion. Building blocks or cells follow geometrical rules. They are shapes of triangular derivation, and the set of building blocks generate a distinct shape that continues to reveal the same qualities. The building blocks also follow specific proportion rules. They follow the golden ratio and a centrifugal pattern of 9 degrees sector. This proportion ratio also spread throughout the structural mesh, establishing proportional relations between shape elements, growth expansion levels, textural patterns, and the shape itself. Growth is a process of mass increase based on elements addition. It uses reproductive mechanisms of self-replication by error that follows a step-by-step transformation process. The cell's division process follows a crossed and inverted reflection pattern. So the reproductive process requires a set of geometrical elements. A reflection line, a reflection point, maximum point, transfer line, proportional relations, and shape center. The transformation process follows an organization balance based on symmetry. The reproduction mechanism achieves it by following a centroidal patterns distribution. Biological shapes have the ability of being noticed and unnoticed at the same time. They do not generate any kind of disturbance because they work as a mass of force transfer. The energy flows through the shape. To generate that fluidity, three qualities are required. First, an expansion pattern characterized by a dynamic center. Second, an interior organization based on gradients in order to highlight the shape center. And third, boundaries with concave and convex configuration able to generate tension in the surroundings and push that forces into the shape. Assuming the main challenge that the bio-inspired design face is basically concerned with compatibility. To be participative, it is necessary to share the same rules and process. In other words, they have to share a signature. The introduction of growth qualities as recursion, transformation, and dissipation will take the morphology pattern to a new level of organization by adding concepts such as evolutive balance, structural fluidity, elements dependency, and integration ability. Growth also forces the design process to be interpreted through a reproductive mechanism. As a future challenge, this research aims the generation of a computational design tool able to introduce these qualities. The tool will be based on a digital interpreter following a generative and a parametric design. So it's all. I hope you enjoy and see you soon. Bye.
Thank you very much for the presentation. Right now, this concludes our second session of presentations, and we have some time to discuss, and we have some time to talk about. If not, we're going to have a 7-minute break, and we will continue afterwards with Alessio Arioli.
Sorry, do you hear me? Hello?
Yes, we're here.
Sorry, I do have a question, if you don't mind.
Sure, go ahead.
Actually, it is for Tarek about the patterns in history.
Okay. Tarek, are you here?
Can you hear me or not?
It seems that we have no response from Tarek.
Okay.
Unfortunately. But you can ask anyway, maybe he'll see it later.
But basically, I was just wondering if he sees himself like as someone who is practicing architecture or as an arts or architecture historian, because at the end of his presentation, he was talking about like 4 parameters of aesthetics, like harmony, variety, balance, and proportion according to Aristotle and Platon, right? So I was just wondering what does he think about like, shall we keep going with this historical way of looking at aesthetics, or we can like reinvent our own definition? I think this is also an open question for the participants today, because like we're using elements from the past to actually invent the future. So thank you.
Well, I see that Tarek is in the comments on YouTube, so maybe he will respond there.
All right.
Give me order and time, and I will give you design. Daniel Dennett elegantly summarizes in his quote the creative engine at work in Darwin's theory of evolution. The core process of design in human-involved disciplines implicates an extra factor, intentionality. In both, a process of production and reproduction takes place through the exchange of encoded information. While in biological systems such information is embedded and embodied, shape and organization are information, in human-based practices, the encoding requires an external, explicit and abstract notation system. We owe to Leon Battista Alberti's obsession for identical reproduction the concept of a notationally stable artifact, the original, the final version of a work. A set of codified abstract information, the sublimated sum total of intentional decision, ready for exact serial reproduction. A means becomes a goal, notation takes command, design divorces making, thus incidentally sanctioning also the figure of the author as the subject associated with it. Codification, the act of producing a notation artifact, implies a system of mediation, and all forms of mediation involve modes of storage, manipulation, and transmission. Friedrich Kittler points out that the mutual relations among these modes are critical in order to comprehend the entire system of mediation, also remarking that the computer is the first technology of mediation that automatically combines them into a single system. Differently from a sketch on paper, geometric data in a computer is truly three-dimensional, which can be generalized to n-dimensional, this is a crucial detail for the development of artificial intelligence. The possibility to build a relational architecture in the code means also that digital technology can process and manipulate information in such ways that difference and variation can become programmed design features of a unique process. For architecture, this shakes the foundation of mechanical standardization and, with the simultaneous possibility to inclusively mobilize materiality and machines, of the Albertian design-making authorial divide. Technology has always defined the operational boundaries of the design space, shaping the features of the realm of possibilities that it simultaneously opens. Its advancement pushed those boundaries and widened that space in a movement that is not one of endless improvement and substitution, but one of continuous restructuring, enabling paradigm shifts. For one, photography did not replace painting. Technology's outcomes enable also cultural changes. A brilliant example of this symbiotic relation is the invention of collapsible tin paint tubes for pigment conservation. This tiny invention, patented in 1841, allowed painters to finally work en plein air, when before that invention they were forced to stay in their studio, otherwise their pigment would fail and decay. This, as a matter of fact, enabled the painters to watch and observe nature, and in turn enabled the birth of Impressionism. Technology has also a bias, showing preferences that reinforce certain possibilities while obfuscating others, thus altering our worldview as we operate through its lens. The tools we make in turn reshape our mindset and our action. Think about the sentence, just Google it. Environment and technology also mutually reveal their shape from their reciprocal interaction, disclosing operational possibilities and boundaries. We cannot escape technology, and any way of improving our human condition is through it and not without. It is an inevitable source of both opportunities and problems, but the former will outweigh the latter only when coupled with apt theoretical paradigms and open-ended design approaches. What is advocated here is a speculative stance that does not thrive on narrative alone, but one that deals also with processes and dynamics through computation, nonlinearity, and complexity. But technological propagation and paradigm renovation progress at different paces, thereby causing a rift. Computation acts as a catalyzer that accelerates processes and exposes this rift. Computation itself can be defined as information processing. It tries to compress infinite quantities of data in finite sets of operations. It is a process that predates and transcends the modern digital computer and can operate on a variety of instantiations, whether based on a material or abstract system. The introduction of an explicit mathematical model, which requires layers of abstraction and a notation system, exposes the limit of computability as compressibility/reduction. Algorithms themselves emerged from material and rhetoric practices. Modern computation gradually evolved from concrete towards the increasingly abstract forms. But purely descriptive or linear algorithms, such as those governing CAD systems, are not good enough to manage complexity. For instance, a linear algorithm for all the possible moves in chess, in a game of chess, is theoretically possible, but in order to build a calculator to account for all possibilities, the mass of the universe would not suffice, while biological systems elegantly attain similar complexity with only 4 elements, the nucleotides A, C, T, G. It is the von Neumann's model of a self-reproducing machine that was the key to overcome the purely descriptive model and open the way for emergence-capable systems, which develop in algorithmic paradigms like multi-agent systems, polyautomata, and so on. Computational methods are sought in the effort to tap into the complexity that Dennett alluded to, while retaining the ability to steer in order to meet specific goals. But we must come to terms with 2 important aspects of intentionality. First of all, it can be distributed, and machines have also their own bias or intentionality. By machine, here I refer to the concept of abstract machine, which is, in general, a finite sequence of operation. Sol Levitt is a key figure in this regard. In 1967, he wrote the sentence, "The idea becomes a machine that makes the art," a theoretical model for his wall drawing series, sequences of operation or algorithms to produce site-specific installations. Levitt is fascinated by the creative possibilities of a relentless machine and wants to question the figure of the author, the art piece, and the cut between the acting subject and the object of attention. The temporal dimension also enters the process through the concept of iteration. The decisional process disaggregates and it is redistributed at a granular level. The myth-laden moment of conception is no more, as representation gives way to simulation. The process is as important as the object, because it captures the dynamics that generate the object itself as a result of interacting relation over time. Likewise, the true creative power of computation in design lies in its pervasive incorporation in the decisional process, from thinking to making, unfolding in time iteratively. And that can truly happen by giving into its way of thinking like an abstract machine. Computational design, then, is a matter of methodology rather than the adoption of a specific tool set. I should introduce, for the sake of clarity, the distinction that Matías del Campo makes between computational and computerized. The difference can be better explained in the comparison between Antoni Gaudí and Frank Gehry. Gaudí makes use of intellectual models, mobilizing material through mathematical and geometrical understanding as probes to navigate a design space for the generation of form, not only in the famous hanging catenary model of the Sagrada Familia, but also in the transition to the catenate surfaces and the Boolean construction of the rose windows. He thus relies on computational methods. Machines are an active part in his process of creation. Their inevitability is a means to resist easy figuration and immediate implementation, expanding beyond human limitation. Gehry, on the other hand, relegates computer to accessories for digital reproduction around a traditional human-centric understanding of intuition, talent, and sensibility. He still relies on the typical tropes of creation as the irreplaceable intuitive moment, whereas the computers are just accessories to rectify and rationalize. In a computational approach, the decisional process is distributed within the system at the metabolical level, producing a causality network with multiple possible branching at each step. An action can trigger multiple effects and consequences. Conversely, single effects can be the result of multiple causes. Authoriality metabolically binds itself to the decision that propagates at each iteration. In the words of John Fraser, the minute you start encoding things, you put intentionality into things. In simulations, one defines the rules of engagement for a system that unfolds over time. When employed for the study of a phenomenon, they act as a map to an existing territory. But when used in a speculative stance, the map precedes and engenders the territory itself. Once the simulation apparatus is built, it needs to be explored to see what sort of territory is engendered. Baudrillard refers to this reversal as precession of simulacra, and to the engendered territory as hyperreality. Computation itself is thus to be considered as a design medium, in the twofold meaning of means and territory. In computational design, computation is at the same time material, territory, and means for open-ended exploration. A simulation/machine/algorithm and their enactment are not one and the same thing, and they do not compute for themselves. The questions of intentionality, authoriality, and their implied politics, intended as distribution of power and resources, now translates as who computes. Algorithms are themselves not mere tools. They incorporate intentionality and distribute it across the process with their enactment, causing effects that can be experienced at the aesthetic level, because the experience involves the totality of our interconnected senses. They are modes of thought in their own right, and their embedded logic becomes an aesthetic operation. In order to instrumentalize self-organization and emergence to harness higher forms of complexity, their generative engines must be coupled with a selection activity, a continuous exploration, refinement, and channeling by means of interacting with one or more decision-making personae. It is in this articulated and distributed web of decision, both encoded and as a result of assessment of the outcomes, that intentionality and authoriality have moved. In the elegant words of Stephen Shaviro, what we need is an aesthetic of decisions in a frame of emergence and self-organization. The adoption of computation in the design process requires thus a constant activity, involving the exertion of a certain sensibility in order to gain fluency and the potential for expression. The concept of craft, the exercise and discipline of sensibility, the free flow of ideas through the hand of the artisan, according to Ruskin, can be applied to computation if emancipated from an exclusively human-centered perspective. Craft can be redefined as an accumulation of knowledge that sublimates into sensibility. It is then neither tied to the exclusive use of hands, although it is haptic. It requires a sensory and enactment apparatuses as one thinks by acting, and thus involves, again, aesthetics. Nor it is a unique human trait. Machines can also learn and refine their own kind of sensibility, they can develop their own kind of craft. This distribution of decision across the design process in the computational scenario leaves the question of authoriality as open as it was when Sol Levitt first raised it with his wall drawings, possibly even more. Even if someone writes an algorithm, the outcome generally exceeds the individual's capacity to conceive that, and thus the authoriality is at least partially shared. The rise, or better the resurgence and pervasive diffusion of artificial intelligence with machines and systems capable of ever-increasing degrees of human and non-human intelligence and sensibility, presses the matter even further, with radical possible landscapes of change in the design process. It is thus appropriate to speculate on the potential for novelty that AI might bring in shaping potential rising cultural changes, in the same way in which collapsible thin tubes enabled Impressionism. For instance, one interesting aspect of AI is the fact that it engenders a computational space or self-computing space as its training progresses. This dimension adds to the time dimension introduced by simulation and iteration. Another important aspect exposed by the attempts and difficulties on the road to fully automated driving is that labor is an inherently logical activity, thought and action intertwine. The automation of human labor in its pervasive and granular distribution of interconnected microtasks transcends the modern age division of intellectual versus manual labor, with analog repercussions to the design-making divide. Any computational thinking machine capable of agency and decision can suddenly face the problem of percolation of simple decisions into ethical dilemmas, from steering a wheel left or right to the updated version of the trolley problem, where a car in a switch must quickly decide whether to go across a single person or a group of people. Meanwhile, what's not unseen is the trend of progressive expansion of machines, robots, and algorithms alike in what were considered exclusively human domains, including creativity. See, for instance, AlphaGo and the famous or infamous Move 37. This impending tide presses us humans to constantly rethink our species' identity and role in a larger ecological perspective. If a machine can do it, then it's not our defining exclusive trait. The processes of design should become more and more a conversation with ever-increasing intelligent entities and acknowledge the symbiotic nature of our relation with it and the fact that it exceeds our attempts to control it. Thank you.
Alessio, it's very nice to have you here anytime. We will continue with, sorry, I need a moment. We have Evelyn Nunez right now that's going to present. We will either put a video or go live. And we will take her presentation now.
Hi, I am Eveline, and then I am a professor in University of State of Mato Grosso and PhD student from University of Brasília, Brazil, oriented by Professor José Santos. I have been studying the relationship between architecture and engineering since my master's degree. And now I research this relationship with the inclusion of technology. For this, I have been making bibliography review of some material, including the proceeding of the International Conference Structure and Architecture, IKISA, which I approached in this work. My goal in this bibliography review is to understand if and how technology is strengthening the relationship and integration between architecture and engineering. The initial hypothesis is that technology enables information sharing that was previously impossible, making the dialogue between different disciplines more effective and the design process more efficient. Since I want to know how the subject was approached in the international scenario, the IKSA procedures were adequate, considering the event aims to stimulate the inventive and creative design of architectural structures and to persuade architects and structural engineers to collaborate with this process, exploring new concepts, applications, and challenges. In its 4 editions, the technical contributions were divided in several lines of research that address the different nuances of the relationship between architecture and the engineer. My review concentrates on 3 lines: interdisciplinary work between architects and structural engineers, 2, complex forms and for finding, and 3, computer and digital tools. The choice of the words reviewed was made by abstract reading, considering as requirement for choice works that deal with the application of technological resources in the integration of structural and architectural design. After analysis of the papers, I listed some points that summarize the main discussions. The first is related to the linearity of projects in opposition to the idea of a joint project developed from a series of goals. The project in this configuration develops in an interactive way, works in the selection of forms that are not rigid but flexible, in which the various conditions of a project are accommodated through its conception. In the second point, it is stated that technology favors this interaction by allowing the construction of a digital parameter model, in which the project is defined by the set of rules, structures, or parameters initially configured. The design process is iterative as the designer goes through a process of generating the project according to the parameters chosen. Parametric design and visualization environments provide a flexible tool for the definition and manipulation of complex geometries, allowing users to express the structural idea in an algorithmic way, without the need for knowledge of formal programming languages. In addition, because they are modeled with parameters, the geometry defined algorithmically can be easily changed, allowing a combination with optimization mechanisms. An example of this application of this methodology was the Spanish Pavilion for Expo 2010 in Shanghai, presented by Calzón Jiménez at first event edition. The double curvature of the pavilion was developed in rhinoceros by the architects, and from this, the structural model was generated, manipulated, and analyzed, giving structural feedback to the architects in real time in an interactive process. The nonlinear analysis of the structures were performed by the finished element method using dense software. The third point was about a project experiments with genetic algorithms associated with parametric models. The work of some authors showed that large and complex structural systems can be optimized for basic parameters, such as height and number of components, combining genetic algorithm with finite element analysis software and parametric modeling. These genetic algorithms are generally associated with a for-find method in a process called the generative design system. With the use of generative system, it is possible to systematically generate a large number of alternatives. Thus, digital methodology of parameter design can be a generative design system, in which the designer is no longer concerned with the solution of a particular problem, but defines a method for solving similar problems in different contexts. This allows more than one answer to the same problem or for similar ones in different disciplines. In conclusion, the digital technologies expanded the possibilities for exploring architectural solutions. This made possible the matter sharing of information in real time, making the dialogue between different disciplines more effective and the design process more efficient. When modeling of complex forms and simulations of structural behaviors are integrated in the design process, obtaining information gets easier, allowing better design solutions to be realized. However, it's important to fortify the relationship between architecture and engineering as dependent and iterative rather than linear and coexistent. This process of implementing digital design among professional architects and engineers could be the result of the work of integration that universities have been doing with students from different courses, inserting them in the reality of the project developed, different from the traditional one, shared with simulations in the preliminary study and no longer linear, but iterative. That was my presentation. Thanks, everyone.
Hello, everyone.
Okay, everyone. Next, we will have Nelson Montas. Nelson, if you are here. Let me try to...
Hello, guys.
Okay, perfect. We can see you. You can share your screen.
Yeah, can I share my screen now?
Sure, go ahead.
Okay, great. Just give me a second. I don't have the option to share the screen.
Let me... Oh, wait, I need to close my...
Yeah, exactly. You need to let me do it.
Okay, so here we go. Try now.
Okay, great. That's weird. All right, okay, so just give me a second. Do y'all see it?
Almost. Start sharing screen. Perfect, we can see it now.
Yes? Okay. Right, so just give me a second to time myself. It's Nelson Montas. I'm an alumni of the Universidad Internacional de Catalunya, and I have an architecture degree, but I mostly navigate in material science nowadays in what's called programmable matter. I'm here to present my paper called Programmable Biomimetics. Let me just get rid of this. That tries to weave biomimetic design and programmable matter in one coherent sort of like theoretical and methodological framework. I'm going to sift quickly through the theoretical part so we can concentrate on the projects at the end, because there's a lot to unpack here. Okay, so basically my work has been sort of framed in trying to answer this question posed by Von Busch and Palmas in 2006. That had to do with the way that humans think and sort of produce conceptual machines or conceptual tools. And they questioned the way in which the world was shaped by the steam engine and motors in the modern era, and how in the contemporary one they're being shaped by the abstract mechanisms of computers, which basically meant computation. So let me take you a while back. I mean, my personal journey starts, I mean, computation exists well before Alan Turing, but I sort of positioned myself with Turing and Alonzo Church and their theory of universal computation, which began in the, strangely enough, practically, in terms of practice, it began with the Enigma code-breaking machine during the Second World War. Turing is very much responsible for the two most significant developments in computation in the last century, which is computer science as we know it in the contemporary sense, and what we call artificial intelligence. Writing the two papers that actually sort of initiated both revolutions. So the Turing machine is basically, it's a concept that he developed trying to work on the computable and non-computable program, which was his way of reframing Kurt Gödel's question about mathematics more broadly. Gödel's question was about what can mathematics prove and what it can it not prove. So basically, Turing thought it was more worthwhile and more practical and actually answerable to ask what could be computed and what could be and what can't be computed, and that way you would have a sort of a coherent answer. This is rendering an artistic rendering of what a Turing machine would look like, and the Turing machine basically. Turing influenced a lot of mathematicians and a lot of computer scientists, and one of them was Stephen Wolfram, which in his A New Kind of Science book, he has a whole host of principles that he says that govern sort of like the computation hidden behind most of, or if not all, the natural phenomena. But for the purpose of this paper, I want to focus on the computational equivalence one, which basically equates processes in nature and also artificial, like every process you can think of as computations. And spring from there, Ed Friedkin and actually Wolfram too, but Friedkin coined the term digital physics, which basically posits that if you're giving a set of initial conditions and a computational system to process it, and a universal Turing machine to actually carry it out, you can actually design a world or as a universe. What you're seeing now is a formalization by a philosopher named Terence Tomkow in 2013. So translating it to architecture and design, basically what I infer is that buildings are artificial, but are still controlled by the same laws that govern natural objects, and therefore are an extension of them. This is in consonance with the Dennis Dahlen's theory about extended phenotypes, which he borrowed from another author, but he uses it a lot to frame his biomimetics approach. And the gist of it is basically that architectural design is congruent with software design or computation. Software design is not computation necessarily. No, computation is not necessarily software design, but software design is necessarily computation. So that brings us to programmable matter. So programmable matter is sort of a leap that there are basically people at DARPA that were trying to build like molecular-sized robots, and they didn't manage to do that, but they actually had some happy accidents, and they figured out how to actually control matter from the molecular and atomic scale. This has existed before that, but it was a very narrow area of expertise in material science known as shape memory alloys that were discovered in the 1940s and developed in the 1960s by NASA and the Navy. And basically, programmable matter, in a gist, is just the science of engineering and design of physical matter with the ability to change or function. You can basically make the material do certain things given certain sorts of stimuli. Okay, so biomimetics is basically, it's a pretty straightforward, in a sense, method of abstracting, researching nature strategies, abstraction of those strategies and morphology characteristics, and then implementing them in the design setting. So the use here, biomimetics is actually, well, you can take two approaches. Like one is it's called a solution-based, which that's sort of when you're inspired by something you see, much like Gaudi did for certain ornamental aspects of his design. And then there's the problem-based one, which is the one that I'm more interested in, which seeks a solution from nature, just looking at an engineering problem or an architectural problem. So you basically are looking for a solution in nature, but you're focusing on the problem itself. It's not just like that you like the shape, it's that if the question is, does this shape work? Or does this property work? Because biomimetics is also a very frequently confused with just like copying natural forms, and that's not exactly how it works. It's more concerned with property and function. So the central idea is basically, weaving programmable matter with biomimetic design to prove biomimetic design's fertility, to sort of embed the logic of computation within the reasoning behind role model selection and implementation strategies. So we basically used in the project, I'm going to show afterwards, programmable matter, material science knowledge, analytical and systemic abstraction computational methods, and we implemented abstracted strategies from nature. So all this, you put all this together. I'm still figuring this out. This is the first paper I write on this, as what I call programmable biomimetics. Okay, so role model. An interesting part and an important one of biomimetics is how do you select the natural models you're going to focus on. Rather than doing it randomly, you can, we advise, me and my co-authors, just basically pinpoint possible natural role models. You can either select one directly or use a function selection matrix. I'll show you what that is just in a second. Then, second step is ponder the geometrical capacities. What I talked about before regarding morphology, how is it scalable? And the third one is you introduce physical considerations, and I should add chemical to these. So you start asking questions about what materials exist that have the desired properties. Those desired properties match the natural system's material properties. Is it equatable? So, or can you approximate it? That sort of stuff. And one thing that we discovered is that applying this sort of like way of approaching it, I would actually call it a methodology. We actually came across, Dan Raviv says that the process to implement programmable matter normally is design, fabrication, and simulation. And we actually discovered that we could change simulation and fabrication. We can change the order. So the case studies here are 3 projects. One's called HydroNet, the other is a kinetic shading solar device, and the other is another kinetic shading solar device done with an architecture practice. So the first one is located in Riyadh, but it could be done in desert climates. It's called HydroNet, and it was conceived as a product for facades. Like this is something that you install as a second skin or on top like a cladding system. And what we did is we built this matrix here, where you have the properties here and the animal skins in this case that we selected, and based on performance, you select which ones you're gonna analyze. Once you do that, then you basically abstract the functions, reframe the solution, and emulate design principles to achieve the desired goals. The project here, we settled on a combination of 2 materials, polyacrylonitrile, 3 actually, HPAN, and shape memory polymers, shape memory alloys. And basically, this is a simulation of the functionality of each cell, which are 50 by 50. And basically, what this did is that it collected water from evaporated water in the ambience, in the especially in the morning and or fog or something like that in the morning or evening. The second project is located in Seville, Spain, and these 2 were conceived like sort of thought processes of what it would look like to implement this methodology. And this one was basically a curtain that was supposed to go either as second skin or as an in-between skin between glazing and for tall structures like skyscrapers and stuff like that. And what it did is that basically it retreated on its own, it's thought of as passive just by heating, collecting temperature from the sun. This was done by abstracting a mechanism from a plant called Mimosa pudica, which has this property. Here you can see the comparison between shape memory Alice here and the Mimosa pudica. And this is basically how it was going to look like and how it's going to work. You know, this is the interior and exterior glazings and all that. And with this curtain, we can actually control the inner temperature and comfort of the building. These were analyses just to see if it could collect enough heat to work, and indeed it does. The last project, it's an ongoing project. I'm not going to show a lot of this because we haven't built it yet. This was done in conjunction with the In Situ Architecture with Nicolas Vernutello, and this is located in Paris. What we did is basically apply in a real setting what I just showed you with the curtain. We were set out to design a second skin for a renovation project for an office building in the center of Paris. And we started looking at two possible role models. One was the Caprinus Caroleana, and the other one, the Daturus Carnionum. And you could see basically the way we abstracted. This one was pretty direct, and we abstracted two models and then tested them with using physical simulations. This is the result. This is the one we picked. We picked the Caprinus Caroleana because it worked better. Covered less space when it contracted and all that. So the basic idea is here, this facade catches up and stores heat, and then that heat makes the facade open and close without any electrical device intervening. So as a conclusion, the challenges faced by programmable biomimetics to determine how macro and macroscopic structure function in the relationships between organisms in their environments, basically how to mimic that, the phenomenology of it. Synthetic biology is an interesting avenue, relatively unexplored, to see how we could actually add growth into these kinds of systems, because these systems are fabricated, and we want to change that. Anyway, this simulations at least strongly suggest that you can have significantly accurate working proficiencies once you try to model these kinds of systems and actually build them. And the good thing is that you can simulate before you make the prototypes. Therefore, you need less prototypes, and it's less costly. Okay, so thanks. In the future, we'll be using Askeladd Designer to do molecular modeling concerning this. And thanks for letting me present, and congratulations to all the rest of the presenters. Thanks.
We will continue with Justina Moravas. So,
Hello everybody. The title of my presentation is When Architecture Follows Nature, Some Reflection about the Inspiration-Object Relationship. After my genetic architecture's master and after several years of architectural practice, I turn to philosophy and its relation to the architectural process. What I want to explain in this short presentation is precisely this link between the concepts worked by philosophers and the ways in which we, architects, are solving certain design problems. Today, I would like to highlight the thought of American philosopher Nelson Goodman and the reasons why his concepts seems particularly appropriated within questions about biodigital architecture. The term biodigital refers to entities which can be seen as a fusion of two natures. Its first part, bio, refers to something fluctuating, difficult to capture because of its richness and diversity. Its second part, digital, refers to the way we try to tame this elusiveness. It refers to some methods allowing articulation and manipulation of forms. We could try to grasp this difference using the terms introduced by Nelson Goodman. The forms of nature would be characterized by a repleteness or saturation, and the digital forms would be marked by an attenuation or articulation. We can perceive this transition as moving from a dense system to a notational system. I would like to put forward the following hypothesis. The core idea underlying the biodigital process is the transition from the first system to the second one. In this context, the concept of biolearning takes on a particular meaning. This meaning can be seen through interpretation of the concept of learning. Learning is accomplished by highlighting some essential characteristics of object, by formulating rules, by clarifying terms. So, learning, in particular learning from nature, would be marked by this transition from vague and dense to limpid and articulated. The principle of learning and of this transition is selectivity. A cycle of photos, Architecture Follows Nature by German photographer Thorsten Andreas Hoffmann seems to capture some characteristics that I am trying to highlight here of this transition from nature to architecture. Those photos make obvious the contrast between the blur of nature and the neatness of architectural forms. At the same time, they make obvious and incontestable the correspondence between them. What is the essence of such correspondence? I will focus here on the question of isomorphy, which appears as one of essential issues in the study of such a relationship. According to the classical definition, an isomorphy is a bijective mapping connecting the elements of two sets, A and B, one by one. Isomorphy understood in this way implies an identical number of elements in A and B. In other words, each point of A finds a mirror point in B. This point-by-point correspondence would be a real problem for a transition from a dense to a notational system, because this transition supposes the reduction of points. A similar reason, but rooted in the study of language, is the basis for Goodman to reject the traditional definition of isomorphy. The philosopher studies the relationship between a term and its definition. Goodman observes that even this relationship, where the perfect match is the foundation, cannot arise from identity, because there is many definitions or synonyms perfectly right for one
term. He proposes a new concept of isomorphy, which he calls extensional isomorphism. In the Goodman's isomorphy, the requirement of identity is replaced by the requirement of correlation. This is indeed a significant shift in the approach. We no longer look at the object with all its complexity and characteristics. We look at its adequacy with a stated criterion. To give a specific example of such an isomorphy, we can look at the shape of a shell and the Le Corbusier's modular. The criterion of the isomorphy of these two objects can be the Fibonacci sequence. This means that we can consider the shape of the shell and the modular as isomorphic if the relationships of numbers in this sequence are the criterion. I think we can look in a similar way at many methods and practices related to nature-inspired architecture. The book Tooling by Benjamin Aranda and Chris Lash, for example, seems to enter into a dialogue with the concept of the nature-architecture correspondence that I am trying to sketch here. Already the way to organize method of work, labeled with single words, spiraling, packing, waving, blending, cracking, flocking, tiling, is marked by high selectivity. Among all the characteristics of the natural organism, only one is chosen as a basis for form generation. Let's consider, for example, the operation tiling. This operation is inspired by two objects, a system of bubbles and a system of cells. Note that they are two different objects with inspired one operation. That are, in fact, only certain characteristics of the element's organization which constitute the link between these two examples of forms. The definition of these characteristics is also marked by selectivity and approximation. It does not take into account all geometrical aspects. You can see how simple is the formulation of the rule provided by Aranda and Lash. This work seems in fact to be an illustration of the principal hypothesis of my speech. Architecture which follows nature is a question of transition from a dense to a notational system. The way in which the link between elements is established can be taught in terms of isomorphy I have presented here. In this way, an interesting field of study between architecture and philosophy takes shape. What I wanted to highlight in this short presentation is what is for me the primary value of biodigital practices in architecture: the shifting of the focus from the result to the process. Here, the analytical philosophy shows up as an active tool, not only for analysis, but especially for the establishment and clarification of practices and methods applied in architecture. That was the aim of this presentation, to sketch the potential of philosophy to think about the architectural processes, and in a particular way, the processes inspired by nature. Thank you very much.
Thank you very much. We will continue with Diogo Henriquez, and I think he will present over here directly on Zoom. So, wait, Diogo, you have a small issue with the microphone. Can you try turning it down a little bit? Wait, I'll try to turn down our sound as well. Let's see how it goes. Okay. Sound is good. Okay, it is better. Can you hear me? Yep. I will stop my sharing so that you can share your screen. Okay. You are free to share your screen.
Okay, can you see it?
Yes, we can see it perfectly.
Okay. So I'll do a short presentation also because we are on time already. And my presentation is called Towards Shared Urban Visions. And I'm coming from the UK, Northumberland University at Newcastle. And thank you very much for this opportunity, Alberto and Dragos, for all your patience with me. At any critical moment, we can choose to co-create and share our visions for a better future. And we can also choose to contribute to solutions for existing social and economical inequalities and climate crisis. For centuries, cities have been the most relevant forms of social media, and the global awareness seems to be rising. Particularly now at this time, I was not thinking that this was going to happen in the world. So in this paper, we'll selectively review existing definitions of urban visions, particularly highlighting the movement from individual visionaries to shared visions. And with this unprecedented biodigital development, like the protests that we are seeing all over the world, and also how we are closed in our own homes using digital devices, a new definition of urban visions will be one that includes both humans and non-humans on planet Earth, collectively sharing our past, present, and future alongside new advances in human-computer interaction and algorithms. So I've been studying urban visions for some time, and there were many urban visionaries in the past, in the 19th and 20th centuries more, that wrote books, plans, and many sources. And I'm going to highlight one that was Ebenezer Howard, that developed this vision of the garden cities of tomorrow. And of course, this book, when he first published it, it was paid by him for the publisher, so no one wanted to publish it. And then in the end, it turned very popular. There are garden cities all over the world, and there are several particularities of this vision that have been implemented, for example, in policy, the green belts that many cities have around the world, and also the clusters of cities that in the beginning of this 20th century were not so much thought of, and now they are very common. Of course, from these individual visionaries, we are in the 20th century and much more now in the end of the 20th century and beginning of 21st century, we are moving more to these collective visions. And one of the examples of these collective visions that I wanted to highlight is the New Urban Agenda, organized by UN Habitat. And in this document, they enshrine their vision referred to as the right to the city. So they are passing much more from a vision that is a definition of a form of a city, that was the garden city, like a diagram, as you can see here, to a much more a process that is negotiation with all the agents, with all the populations, and especially with people that don't have rights. So, of course, this is started in the 60s and in the 70s. This participatory movement has started here in the UK, and then it developed internationally. And there are several authors, Ostrom, Arnstein, Healy, most notably a lot of women that are involved in these participatory processes in the start, and now it's general, I would say, but this is to note. And so we are passing from a form, so this is a diagram of the garden cities vision, that was this network of clusters of cities, to a much more a process. So on your right, you'll see a diagram that is about the process of negotiations of new and habitat, also between city and country, like Garden City of Ebenezer Howard, but more a process to enhance collaboration in cities as complex systems. And of course, now with all these protests that we are seeing because of the death of George Floyd, And because we are in a conference of biodigital, definitely humans are bio in the part, not only humans but non-humans. And I wanted to take this opportunity to remember all that we are living in an unprecedented time with not only the COVID pandemic that is completely changing our behaviors, but also these protests where people should be staying at home, but they aren't. They are coming into the street to protest their rights. And how it is important to look for a new definition of urban visions. And here I also present an image that for me was very telling of this Blade Runner 2049, this last movie of the Blade Runner. And of course, science fiction in movies and in books has also been a promoter of future visions. The first Blade Runner was a movie that definitely is in the minds and in the dreams of most architects, I would say, and also common people. And in here, this is the girl that makes the memories, the woman that makes the memories. And she's enclosed in a bubble because she cannot have contact with the external world, a little bit like we are now. And she, with the machine, I don't know if you remember this movie, she creates the memories that then are implanted in the people around, and especially in the replicants. So she was born from a union of a human and a replicant. So instead of the corporations of Tyrell, that was the first movie, that were the Tyrell Corporation were defining the world. Here it was a grassroots, so it was people from the grass, from the ground, that really were implementing the visions and the dreams of other people. So I would finish saying that a new definition of urban visions will be one that includes both humans and non-humans on planet Earth. And here all biological developments that are engineered, non-engineered, and some that we might not know yet. And here the work that is being done at UIC with Professor Alberto is really amazing and innovative for decades, and it's inspiring the entire community, and collectively sharing our past, present, and future alongside new advances in human-computer interaction and algorithms. And I think in here we are going to see very soon a lot of developments. So not only in the smart cities movement, but with artificial intelligence and all these mixed developments of protests and corporations of data like Google and Amazon. And these will change the emergency design strategy, cities, and even our lives. So we as architects, we should be aware not only of the populations that are living in our cities, in our buildings, but also of these technological developments that are happening and will influence our profession. Thank you very much.
Thank you very much, Diogo, for the presentation. It's lovely to have you here. And now we will continue with Maria Jo. And I'll make a small transition here. I'll be right there with you. So I will take this. Diogo, can you please stop the sharing?
I did already?
Yeah. Oh, okay, you did. Sorry. Thank you.
I will unmute me also, okay?
Okay, thank you. All right. And is that session 3? No, it's not. 1420. Oh, actually, it's Guillermo. Okay, we have a small question. Is Maria around here, or should we continue with Guillermo?
Yes.
Okay, perfect. Wait, let me take away this, and you can share your screen so we can start the presentation. Okay. All right.
Can you see my presentation?
Maria, can you go closer to the microphone, please?
Can you see my presentation and hear me?
Yes,
Hello?
we can hear you. Yeah, okay.
Okay.
Go ahead.
Is it too loud? Hello? Okay, so sorry. Okay, so I will start presenting my part of my PhD work. My PhD work it's based on the design methodology that it was developed, and it calls Bioshading System Design Methodology, which is acronym for the BSTM. And I'm going to show you a short experience that we have done during my research to prove the effectiveness and the proof of concept of the design methodologies. So for the past 3.6 billion years, nature has been solving many of the same problems that designers face today. That's the fact that we could not resemble. So designing biological inspired components into man-made products is called biomimetics. Some of the world's most famous inventors have used it in their designs. For instance, when we remember Leonardo da Vinci and their notebooks about flying machines and engines, this was a marvelous work documented that still it's patent in our days. Or 500 years after the first flight machine by the Wright brothers over the Kitty Hawk, based also on the flying birds and the wings. And much close to us, on 2005, the Daimler Chrysler drew the bionic car for the Mercedes-Benz based on the fish. The yellow box fish. So sorry, didn't remember the name of the fish. So this car was amazing because it was based not only on the shape of the fish, but also on the characteristics of their bones and the lightness that it could, that it was patent on the structure of the car. And this car could achieve 7 miles per gallon fuel, very economic, and reach 140 kilometers per hour, which is amazing for a concept, kind of the concept of this car. After and earlier today, we are not just looking into the shape and the macro scale of the objects or the animals or our environment, but we are looking into the microscopic properties of our environment and our surrounding world. And this is leading us to amazing structures like this, which is the nanotubes, the carbon nanotubes that that have an amazing hardness of it's a structural. It's a structure that is so hard and so strong that it's being inspired not only architects but also engineers. So, and then we look to architecture and what it's been doing and what we have doing around the world. And we could see this classic project, it's almost a classic in our area, which is the Eden project from the Grimshaw architects, which looks to the bubbles, the bubble structures, which is an amazing form that remembers the cells of a biological shape, or a much more closer, a much more smaller scale and installation scale, which is the musical morphogenesis project, which was a kind of mixed. Well, it was a didactic project that want to teach science to children. So it replicates the Arabidopsis thaliana flower and shows her growth through movement and through elements, colored elements, and it has some lights and music to the children. Or the amazing series of installations of the Allozoic project from Philip Beasley that interacts with human beings and explore the smart materials and shape memory alloys. So this POC project, which is the base of my PhD thesis, it's based on this diagram, which combine 3 big areas, which is architecture, nature, and artifact. This process, it's a cyclic process, and each domain, it's divided in 3 phases, different phases. This is the stratification of the diagram. So the first the first core, which is architecture. It's the kickoff of the diagram and the work. It analyzes and identify in a context area what we are going to do. So we start to identify our problem. Which is the problem that we architects want to solve, and then we diagnose it. Which are the strengths, the potential, the constraints, the generative analysis of the project, and we decompose all the initial problem. After, with nature, we start doing discover and explore phases. These discover and explore phases look into terrestrial vascular plants, which is the core of the investigation, and try to interpret and explore their adaptations, their biological adaptations, which are categorized in three main categories, which is morphological, behavior, and physiological. And then we conceptualize, and here is the abstract component in our creativity and our imagination, which is how we could look into these adaptations and transform it into an idea and an image, and then interpret it and explore it in a way that we could later reproduce it, not only in digital, but also physical. And the artifact domain, which is the culmination of the whole process. And the culmination of the process, it looks into the architectural initial phase, try to extract from the initial SWOT, the problems, and to analyze it now after the inputs of the nature, and how we could integrate how we could interpret, and how we could solve it. And after this, we are going to analyze, digitally analyze and physically analyze, which is the validation simulation prototype. So to this experience, this was very, very short. It was 2 modules of 4 hours with 10 participants grouped in pairs. And in the first 4 sessions, which is the right column, your left column, we had devoted the first session to the architecture and nature domain. So participants were invited to identify, analyze, diagnose, and define the challenge, which was provided to them some basis. I'm going to explain, and after that, they engage into the nature domain. The last session, which was 4 hours also, they had to generate and to produce the project that they proposed to solve the initial architectural problem. So to them, it was given a territory, a specific physical and real space, which was very near of our university. And it was given also a program, which was a university campus house students to build house students into this terrain. And it was given to them a 3D model, also with identification with the surroundings, with terrain, etc. And it was given also to them that they did not have to do this. We give to them a package of all the analysis from climate consultant, and we provide them the radiation data, illumination, the physiometric diagrams, etc. All the data that it could be extracted from the Lisbon EPW. And also we provided to them the ladybug analysis from the surrounding space and to the building that they were to explore. After that, it was briefly introduced to them the shading systems. They were all architects, but they didn't have no background on biomimetics. They didn't explore that team, and they do not have bibliography on it. And so it was given to them not only the site and also the concept of the shading system, which was kind of an initial brainstorming to provide to them some basis to biomimetics. And after that, we provided to them the sequential thinking of the process, which was to identify the functions that we wanted to imprint on the facade, the building facade, and then the actions that could perform it, and in the end, the agents that will enable all the actions. So it's kind of a sequences project. They had this identification of the functions and then the actions. It was given to them some base diagrams, but they produced their own diagrams and their own actions, attributes to actions and functions. And the way that they related them, it was independent to the group. After that, they had to relate the actions with the agents. And so extracting this function actions relationship, they had to extract the action agents relationship. And from here, they had to extract the fundamental agents and actions that will serve basis for the construction of their facade. After that, and along with it, we will provide them some valuable information about adaptations of terrestrial vascular plants. We gave it to them an introduction of the general organism, and then we provided to them some major concepts and also some basic lists that had some of the fundamental morphological, physiological, and behavioral adaptation of terrestrial plants. So after this, they had to fill and cross with the architectural domain all the adaptations that they extract and that they associate to their project. So this was kind of the construction of the MEMs that will serve to them as base, the conceptual base for the project. And of course, it was provided some platforms for them to explore concepts and also to extract some other ideas. After that, each group fill the construction of the biomimetic MEM, which is a fictional MEM. It doesn't really exist on nature, but it's extracted from the real ones. So they had to fill this table, and in the end, they had found the biomimetic MEM that would sustain the project. It would also give it to them some ideas about the types of structure that it was possible to build and to represent the structure. And it was also given to them some type of actuations that they could consider for the project. After that, each group developed the facade as they wanted. Well, it's not that they wanted, because they were kind of guided through a methodology, and also they had their personal biomimetic MEM, which was the foundation of the project. So for this group specifically, they considered bioluminescence, epidermis, nitinastic movements, and vernation, which was the fundamental MEMs, and then the biomimetic MEM, the fictional MEM, was kind of privileging permeability, scale, dynamic. They could be dynamic or static in this group case. Behavior adaptation. So they wanted a facade that really moves, that people could see movement in real time, and some pattern features characteristics will be multi-layered and perforated, and material features as they choose porous, performative, and it could be an open close motion. So from this, they developed this kind of winged flowers that open and close through movement. I remember you. This was a very short experience. They had only close to 3 hours to develop their projects, which was kind of amazing thing. And the second group, these were the plant selected events, the trichomes, the nitinastic movements also, and the diallotropism, and the construction of the biomimetic MEM. In here, the idea was a vertical structure that worked also in a vertical way that could compress and decompress, and in the way that they do this, the material will have several two different types of transparency and permeability, and when it was closed, they enable entering the light, and when it's open, it kind of closes, blockaded the light. And the next project, it was very ambitious. Their idea passed to a water storage extra deposit. They wanted to be a facade that could not only the facade but also improve the capacity and the water cycle inside the building. And so they developed this diagram, which was very interesting at this stage of this project stage, and they wanted that the facade work like a system that captured not only the water, but it could canalize it and transform it and distribute it through the building, and heat it. It could be heated or not, depending on the situation. And so this would be the look like the aspect of the facade, their facade. It's kind of very interesting facade if we imagine it in real time. And the D group developed these opening structures into a static facade with different scales and different orientations depending on the analysis of the facade that they have produced using Ladybug. Each triangle, each color opens in different directions. So the blue ones opens on top, the green ones opens on one of the sides. This was conditioned by not only by the orientation, but also by the different levels of the building. And the last one, which was composed by these triangular shapes also, but it was the intention that the real material that it could fold or unfold. So also based on deciduous plants, bark trees, zootropism, and enigmatic movements, the construction of their biomimetic MEM considered that could be a behavioral structure with random, apparently random movements, and aiming for a flexible material feature. So in the end of this experience, which was very rich for me, the participants were also asked about the experience and how they feel and which was the strongest point and the weakest point of the experience. So every aspect, the overall, the identification and diagnose, the discover and explore, these are the various states of the process, were positive, being that the diagnosis phase was kind of difficult for them. They consider that the diagnosis was really short. With a real short time, it's very difficult to produce in that environment. So it was a problem located on the architectural domain. And during the POC section, evaluating the session itself, the negative points were going to the short time of the experience. And we consider that medium percentage are going to the overall methodology. They consider that the supplied material was too much for the analysis, and also could be more synthesized. So this was improvements that were made to the research. So during the architectural domain diagnosis phase, more than provide lists with primary functions, action, and agents, it is mandatory to explain those items and to show them by exemplifying their possible correlation. This was one of the points that was really talked between the participants with us on the end of the sessions. In order to exemplify the correlation between the different elements, an illustrative diagram should be presented. So they asked for a more synthetic diagram that could relate the different parts and to present to them. Regarding nature domain, a diagram that links the MAM events table from the exploration phase. And this was very, very, very funny to find out, because when we provide so much freedom of creation to architects, some of them find really lost, and they had no kind of feeling that without any grade they were not able to fly. I don't know if it's clear, but it was very curious, this fact. At the end, the artifact domain requires the box function initially aimed to achieve the simulation phase. So this was one of the initial aims, but it's revealed to be impossible to do it, because once the participants engage into the studio part of the experience and to draw and to generate all the projects, they were always saying, no, 2 hours, it's very, very few. We could not produce anything. But they can. Okay, so, but we could not achieve the simulation and the essays of the efficiency of the facades. That was due, but that was done after, and it was us tutors that produced the evaluation of the projects. And I think it's all. This was our little environment in our groups. Thank you all, and so sorry if I just passed the time. Thank you.
Thank you very much, Maria, for your presentation. I'm fairly interested in your way of developing facades, so maybe we can talk about that a little bit later. Right now, we will continue with Guillermo. If he's present, we will play his video. So, Maria, if it's possible to stop the screen sharing, please. Can I? Okay, perfect. Thank you. We will continue. And just in a while. Okay, and let me share my screen. Wait. Sorry, we have a small drawback. Where is that?
Hello everyone, my name is Biodigital2020 and today I'm going to present my paper Wandering Column, a morphogenetic application on structural optimization by autonomous agents, which is part of the master's dissertation I developed under Gabriela Celani's supervision at the University of Campinas in Brazil. So we know that living organisms are systems that acquire complex forms and behavioral patterns through the interaction of their genetic characteristics with external physical forces and environmental pressures in a development-based evolutionary process. These systems are self-maintained by genetic adaptations and behavioral changes, so form and behavior are intrinsically linked. The morphological features of an organism are subject of its behaviors in a given environment, thus different behaviors can generate different forms. As in the image, a flock of birds is an example of behavioral-based self-organization swarm system in nature. Formation processes by natural agents can emerge from individual or collective behaviors. Collective behaviors relate to the role of agents as part of an emergent behavior pattern, as when a group of ants self-organizes to form a kind of bridge, and show the indirect coordination mechanism of stigmergy. These agents actively mediate the processes of formation in nature when they simultaneously react to environmental stimuli and interact with other agents, triggering the emergence of behavioral patterns and therefore constituting a natural morphogenetic process based on behavioral systems. The agent-based computational model is a collection of autonomous decision-making entities that act as processing devices capable of computing the artificial environment and are used to process and synthesize data according to natural phenomenologics. The agent's behaviors are a result from a set of rules that define their strategies at recurrently new situations, and this set of rules also guide the decision-making processes. The agents can modify this initial set of rules with feedback information from the environmental context and thus generate new rules, creating dynamic adaptations. In this video by Ignacio Lucenti, we can check an example of artificial agents which collective behavior is controlled by changes in speed and force. And based on that, I developed an experimental design application in Rhino with Grasshopper and some analysis et al. It is a morphogenetic design application that takes behavior-based tools and structural analysis methods to conceive a performance-based experimental column. First, geometric boundary conditions were defined, such as position, base dimensions, and height. In order to control the direction of the experiment growth, vertical curves were defined out of the bounding box to serve as tracking path for the agents. A Calibra add-on for Grasshopper was used to model the movement of 20 artificial agents by parametrically controlling their collective behavior. The most suitable behavior algorithm to deploy in this process would have been strict stigmergy, but the available library in Calibra doesn't allow to associate it with a tracking path in order to have the vertical direction control. So an alternative to have this level of control was merging two other behavior algorithms together, tracking behavior, which makes the agents follow a path, and wandering behavior, which control their movement and interaction. Computed in 265 iterations, this behavioral system resulted in 20 trail curves that were then rebuilt and simplified to be used as a bar system for structural analysis using Caramba 3D add-on for parametric engineering. Gravity and vertical point loads of 5,000 kilonewtons were applied to the analysis model, considering the base points as supports locked for torsion and rotation, rigid nodes, concrete material, and circular cross-section diameter of each bar. The analysis resulted in a maximum displacement of almost 65 centimeters, which demanded an optimization process using Galapagos evolutionary solver in order to minimize this result. For this single objective optimization process, the system's displacement value was assigned as the fitness function, and parameters of the behavioral system that control the agent's speed, force, velocity multiplier, and polar change were assigned as genomes. Likewise, parameters of the structural analysis model that set the cross-section dimension, limit distance, and snap length were also assigned as genomes. And here you can see the three design procedures: agent-based modeling, structural analysis model, and structural analysis result, happening concurrently during the evolutionary optimization process. It is interesting to notice that from the fifth generation on, the column starts to get a stable form. After running a couple of generations, one of the most adapted design iterations was this one, in which you can verify that the system's displacement bound values are closer when compared to the values from the non-optimized model, and this iteration resulted in a maximum displacement value of half a centimeter. In the end, the evaluated curves were meshed and smoothed together as a single continuous geometry using Weaver-Bird's Catmull-Clark algorithm respecting the resulting cross-section diameter. In conclusion, it was possible to devise a biomimetic computational design process in which the system's structural efficiency emerged from the simultaneous association of behavioral patterns, structural analysis, and evolutionary computation. It draws attention to performance-based design approaches that emphasize material systems in form generation processes. And it's also a work in progress design methodology in which some aspects need to be improved or adjusted, such as the Sigmergy algorithm implementation, Verdes merging strategy based on spatial proximity in order to perform the structural evaluation as a single system rather than as a group of 20 subsystems, or even reconsider the structural analysis method using finite element analysis on the meshed model. It's important to either reconsider the concrete material due to sustainable concern, or keep the concrete material but understand the best way to have a next to zero environmental impact manufacturing process, perhaps using biodegradable formworks, robotic aided 3D printing, and so on. It would also be interesting to make a comparative study between digital stress analysis and a physical stress analysis on a one-to-one proof-of-concept prototype. It's also interesting to point out that this is an isolated element out of a complete structural system, and the implementation of such design methodology in a structural system would probably require further design and analysis strategies. And that's it, guys. Thank you very much.
Andre asks Diogo, do you already have ideas on how the urban scenario may change with the inclusion of the already existing technology, and how architects may have to consider it?
Can you hear me?
Yes.
They are not transparent, so we don't see them in most of the places. This is out of the sight of the citizen. So I think one very important scenario that should be promoted by us, architects, designers, and also politicians, of course, would be for the people of the cities at least know which data and for what is being used. So more transparency would be one of the scenarios that I would suggest. And of course, most important thing, and here the one more, the work that is being done at UC with Professor Alberto is very important, is education. So designers and students that want to be designers should be from very early stages involved in understanding all these processes with data, with biodigital developments, these transformations between organisms and artificial constructions. So they can participate in these discussions and don't let this process being led to corporations that slowly are taking over the world, like Google, Apple. So this is my short question to this. Of course, I'm happy to share my email and continue this question with Andre if you want. Okay.
Thank you very much, Diogo. Now, we will continue directly with our fourth session due to the fact that we went a little bit overboard with the presentations. So right now we will have a keynote lecture by Aref Maksoud, and I will prepare it soon for everybody to see.
Hello everyone, First, I would like to thank Alberto Stevens for inviting me for the third time being here with you in BioDigital conference. It was my pleasure being again here in such an amazing conference. My name is Zarif Maksud and I'm assistant professor in the University of Sharjah, United Arab Emirates. Today I'm going to lecturing about the digital revolution in the academic process or in the architectural teaching methodology and process. Well, speaking here about the biodigital architecture as a revolution in the academic teaching or architectural teaching, I would like to explain here comparing between some of my students' works in designing skyscrapers, recently using Grasshopper or recent softwares and technology, Maya Max and so on, and also the Bahari Tower in United Arab Emirates, explaining or showing that the world of design teaching has dominated in the culture of parts. Professors, designers, students, architects have been trained to think about their design in terms of a discrete parts made of homogeneous materials. But at the end, the final design is made of parts assembled. It wasn't assembled, as I said, but we know exactly that the nature, if we're speaking about digital, the bio-nature design, the nature doesn't operate it that way. When we think about the nature, about the organic plants world, you see that the wholes that are made not of assemblies, but of, let's say, heterogeneous parts that constantly, continuously vary their properties. For example, the skin, stiffness, and its color, etc. and so on. So moving from homogeneous to heterogeneous, trying to unify between or between structure, skin, and materials, or to combine structure, skin, and materials together. So we as a teachers, professors, designers, aiming now to move beyond the age of a machine. When then we will find ourselves stuck between two representation of the world. The representation of two-dimensional of the edge of digital world itself, and the representation of the biological or the natural world made of codes. And actually, as today's professors or teachers, we are attempting to integrate between the materials, digitals, and the natural domains or biodomains in order to create products, designing and creating buildings, cities. We could think in this way as the dichotomy between the world of culture and nature. As a designers, again, teachers, students even, not only teachers, we must today bring into account not only the digital but also the biological. So in this sense, we have to operate in the intersection of material, structure, skin, material, physical and digital, biological. These are the different fields inside we operate. What I mean here in like a computational design, material engineering, manufacturing and biology, nature, structure, skin and materials should be in our mind from the early beginning, in the early stage of the design process until the end. Well then, let's try to simplify the idea, or let's try to organize the project concept, ideas, products in order of complexity, explaining the meaning at the same time, explaining the meaning at the same time of the design within nature. Like we can classify them or let's say organize them like inspired by nature, project inspired by nature, ideas, biology, informed by nature, engineered by nature, designed by nature, and designing nature. From the nature-inspired design to design-inspired nature. Let's start from the first topic, which is inspired by nature. Here I would like to explain about the MIT research by Neri Oxman, the dress for Paris Fashion Week. I think it was in 2012, 2013, I'm not sure. It's inspired by human skin. Instead of generating assembly made of parts together, a continuous skin design that can vary porosity, the length of the part, the direction, their material composition to provide comfortable, wearable, and structural skin at the same time that could filter the air and potentially sweat. Oof. So again, Neri Oxman, she did it and has a shift skin with a single system rather than assembly of parts. That was really a revolution in using the materials with the as a structure on the skin. At the same time, using a digital machines and digital materials rather than generating assemblies, she generates a continuous skin, which was really fascinating us at that time. How can we implement such principles into an architectural scale project, into our designs? And this is the most important part. We should think or get advantage of such research from MIT and Neri Oxman. So let's compare here, or actually here I wanted to focus in on the three-dimensional space. And since nowadays we are using high-tech 3D printing technologies and robots, as I mentioned before in the previous slides, in most of our research and project, we should know well that biology doesn't print stuff, but biology grows it. And this is very important idea about the growth, which mentioned before by MIT and especially by Neri Oxman. Biology doesn't print stuff, but biology grows it. So the MIT here, we can compare between two projects explaining about such idea. The MIT Silk Pavilion, the dome is not made of parts, but while Buckminster Fuller did, it would made, or actually it made of a single fiber that could vary its property locally as a function of structure and environmental performance. One of this dome made of 1,000 parts, and the other is made of a single element, the MIT ones, I mean, of course. One is sympathetic and the other is organic. The most important part here is one designed for a nature and the other is designed by a nature. Well, as a conclusion, for the previous speaking or speech about the growth and biology, the split personality of every architect, designer, or even students of us operating nowadays or today between machine and organism and between assembly and growth. And here I would like to explain about EcoCity, which is one of my research in a MagLab as a director of a MagLab. Unfortunately, I don't have enough time to explain about the project, so I'll leave the video explain it, but I would like here to uniting these views and moving away from assembly and closer more in this project to the growth. Somebody could ask me why now this kind of project, why not 10 years ago we didn't see such a project, or 15 years ago. We are living in a rare time in technology, and the four fields I mentioned before in different slides, that giving the architect or a designer or even student the access to tools we have never think or had access before. These fields again are a computational design, allowing us to design a complex form and shapes with a simple codes nowadays, such as using grasshopper or definitions or even the second field also additive manufacturing, which letting us to produce parts by adding materials rather than carving it out. Material engineering, which now letting us to be or let the design behavior of the project and the high resolution. Synthetic biology or the biology itself, enabling us to design a new biological functionality by let's say by adding a DNA, and that's what we saw before in different projects. Now I will let the video explain a little bit about the EcoCity research project. Moving to another project or other research project done by my lab, MagLab. Before I want just to ask a different question. Does advanced technology help our students to think better? And does technology improve our skills to design and do experimental study better? In this project, I shall not try to answer these questions or this research project, which is called Dragon Blood, but instead present a possible structure through one or through this research project to analyze the influence of technology in the design process. I would argue that the use of technology doesn't suitable the moment of innovation. Yeah, but it contributes for the exploration of solutions or different solutions that are beyond what one had started at the beginning. So Dragon Blood or this kind of a research, a parametric model related to algorithmic thinking at the same time with architectural education or any architectural education, advances in technology here used or nowadays, let's say, not just only in this project, nowadays the application of the digital technology are not only powerful devices constituting the main tool for designing, modeling and manufacturing architectural forms. As tools are so powerful, of course, efficient enough and a manifold medium of thinking about the field domain of their applications, about the project resulting from their use, about the subject itself, let's say, who choose to employ and who legitimize them to, or as expressive sign, manifesting a certain way of conceiving, let's say, or reconceiving, thinking or rethinking, contemplating and experimenting. While also speaking about the new forms, unseen forms, experimenting with architectural design with my biodigital students in 2017, I think. Here the teaching architectural design is always, let's say, strongly related to experimentation. Not only experimentation with the forms to be created, with the tools to be exploited, but also with the means to be implemented, with the materials to be used, with the ideas to be formulated, and with the values to be expressed, with the principles to be forwarded. And this kind of photos are just a proof of what we are discussing during this kind of biodigital master program with the students. It's also related to the great extent to the experimentation with the forms of teaching, with the teaching strategy itself to be implemented here with the students in designing or generating such new forms or the unseen forms, with the learning outcomes to be achieved, with a value to be appropriated by the students themselves. Actually, for new, let's say, or speaking about the unseen forms, or sometimes this kind of form experimentation is aiming at the further development of an already implemented pedagogy in the framework of particular approach to architecture and architectural design. While the character of the experimentation is not the same when we, as a students, architects, or teachers, are experiencing new understanding of architecture, and in another way we could say, like, we are considering other than the already established values, principles and priorities is creating architectural forms here. So going more or going back to the unseen natural forms, what did this unseen forms gonna look like? Again, would they surprise, delighting us? If so, then how could we go creating something really new? And what do we mean by new? There are two rounds of discussion for this. One, focusing on the cognitive aspects of the design practice with the parametric and digital tools, and the other emphasizing whether or not parametric design are supportive in three perspectives. On this perspective, these two discussions are already closely related and also overlapped in some ways. But overall, they show, let's say, honest, let's say, description of how parametric design were used in parametric architectural design courses for teaching and workshop studios. This project I'm going to explain later, related to my courses in University of Sharjah, or in Arab International University, or even in Universitat International de Catalunya. It's going to explain a lot about what I'm saying here in the previous slides. Parametric design and digital fabrication era, I would like to explain here about the searching for innovation through teaching digital fabrication, one of my projects done in 2020. At university, at the Sharjah University, with undergraduate students. Here they use their digital fabrication in this course, or in this, let's say, as a part of education for the architectural students, has become a common skill in many schools, also not just only in our School of Architecture in Sharjah University, but also there's a growing demand for computer-aided design, CAD skills, computer-aided manufacturing, CAM logics, programming and fabrication knowledge in the students' education. The relevance of fabrication tools now for architecture and design education goes beyond more, and can pursue innovation the digital age has radically reconfigured the relationship between conception and production, digital and physical, creating a direct digital link between what can be conceived and what can be built or produced through file to machine, file to factory processes of computer numerically controlled CNC fabrication, or using digital or using robotic arms, or however there has been very little written about what students are actually learning through the digital fabrication courses in the universities, and the relevance of the skills required for innovation in such a field of digital fabrication. Well, let's simplify the process of the natural creatures and life in the solution. We know that life is the solution, but establishing a rule, establishing a link, we have to establish a rule, establish a link between property of the element, strategies of the design, doing some kinds of minimal processes with simple rules and simple operation. For instance, in the scale of architecture, such as a column or a wall installation, playing with the beauty and technology in the column or in the wall, and that's what we try to play with our students in University of Sharjah College of Engineering. So we try to play with beauty and technology, doing this kind of parametric wall with from more than 3,000 unit or blocks, and at the same time for 7 meters long and more than 3 meters height. It may be considered as a fact that computer now, or in computer-aided design, it's a part of the work as a method or provided by digital technology, was the main revolution in architecture practice of the end and the last century. But here in this workshop, at University of Sharjah, which is called Robot Challenge, we overriding the ancient practice of drawing, the integration of new digital technologies provided a different manipulation of the architectural images projected, as well as the introduction of new dynamics into project practice. However, the implementation of digital technologies in a such work or such project practices and environment is not exclusively the case of architecture. The main instrument in digital technology, the computer, today, and well, the tool in any professional environment, assuming itself within the panorama of contemporary Western society or as a first class need. In the terms of architectural or biodigital architectural education, the most interesting question here that beams or parameters places on our profession of are exactly those will be the architectural education and profession as we know it will be able to adapt itself to a digital world. Will it be or will it evolve beyond recognition, or will it becomes extinct? So I think we need to look more in our research and our project. In another project here done in University of Sharjah, United Arab Emirates, where I was directing a course related to parametric design digital fabrication, we discussed, or I discussed, the methodology, educational process and design outcome of the studio course for parametric design digital media, from design to production, from digital to physical. This course took place at, as I said, in University of Sharjah last year. The students participate in the course working in teams to produce a series of models, digital models, which could be later developed into a full-scale furniture piece. The course aimed to offer an experimental learning opportunity, showcasing the entire digital workflow employed for furniture design, from design to production, as I said, from digital to physical. The out, of course, depending on the different softwares, mainly on Grasshopper, we arrive to such forms fabricated from or with the usage of the CNC and the laser cutters. With the, let's say, the design methodology, employ digital design strategies linked with the material constraints, optimization and adaptation of the design for digital fabrication equipment. This education experimental led us to the production of a full-scale furniture prototypes, which was digitally fabricated and is currently on exhibit at the main hall of the University of Sharjah right now. Finally, there's an important, this is my final slide, and there's a term I would like to discuss about it, it's change of focusing or change of focus. So what I proposed in these lectures, actually what I discussed as a conclusion in this lecture is a change of focus in architectural computing education. The focus has to move from the procedural domain-oriented pattern to, let's say, or towards, if you could say, a personal-oriented approach. The new education paradigm in architectural computing that should be focused on the constant development of the person itself, architect, designer, students, whatever, not just tools or methods. Will enable more paths of development, better designers. Better means more conscious, intellectually flexible, self-actualizing professionals, and so on. That was my presentation. You like it, was not bored for you. Thank you and appreciating your listening. Thanks a lot.
Presentation. Thank you very much. And we will continue right now with Tarciana Andrade. That we have a video from her with her presentation. Oh, you're here as well. Hello. You can say hello to everybody. Okay. Now I will put this back and play the video.
Good afternoon, everyone. Thank you for your presence. I'm Tarciana Andrade, a design PhD student at the University of Lisbon. And today, I will present the paper Overview of the NASC Movements in Plants, a data collection for developer-responsive facade. Let's start. We've divided the presentation into 4 parts: introduction, methods, discussion, and the final considerations. The focus of the paper was on plants. Lopes and Eimer consider the plants similar to buildings, as they also cannot move to escape adverse environmental conditions, and this served as an inspiration to design facades. Our object was the NASC movements of plants. And what is this? NASC movements refer to non-directional mechanical movements as a response to external stimuli, which do not depend on the direction of the triggering stimulus, and they are mainly reversible. Here you can see an example of the NASC movement. In oxalis triangularis, it's a response to induced transition from light to dark, as would happen between day and night. The paper aims to conceptualize types of NASC movements and identify different organisms that present such movements, and their strategies, morphological, psychological, and behavioral. We conduct a systematic literature review using Prisma methods. We consider the following databases: Scopus, Web of Science, and ScienceDirect. We consider the period between January 2008 and January 2020. Some of the terms used in search were nasty, chemonasty, nicknasty, photonasty, and the others. As a result of the search, we found 303 records. After we eliminate duplicates in the paper outside the scope, we arrived at 60 papers assessed and eligible for research. This was possible from a quick search of the term nast and movement, in agreement with the analysis of the title, summary, keywords, and discussions. Like this, the data collection presents the 90 types of the nast movements and 27 organisms between individual plants and the identification of the plant families. For each organism, we try to identify what's the adaptation of the analyzed organism. Why does the organism need this strategy? How does the organism develop this strategy? An example of the rhododendron cautobias that present leaf movements induced by low temperature. In this temperature, leaves droop and curl. After, the organism information was recorded in a data collection record table that identified photoprotection strategies and the potential adaptation of the leaf morphology, among other characteristics. 90 types of the nast movements were identified and conceptualized. For example, tigmonasty was a type of movement with the most records, almost 45%. This type happens in response to the contact of an object, as found in carnivorous plants or Mimosa pudica plants. This is the Mimosa pudica. It's the organism that attracts most research attention in tigmonasty movement, which are responsive to vibration, shock, and touch. The puvino is the organ present in the Mimosa pudica, responsible for the movements of the leaves and the leaflets. The direction of the nast movement is directly related with the asymmetry of the plant organ. Thus, it's possible folding and unfolding leaves, raising motions of petals in light-dark transition or by temperature. These movements are usually caused by turgor pressure. Turgor pressure is the variation of the large internal hydrostatic pressure inside the cells. It involves the swelling and shrinkage process of the cell and the tissues. We performed a qualitative synthesis of some organisms in order to highlight the main characteristics found in the scientific papers, and we made the schematic illustrations. With these organisms, we hope to inspire architects and designers to develop responsive facades. Because nature-inspired projects have been validated and intensified the use of the biomimicry as an approach to solve design issues. We present 3 examples of facade design inspired by the nast movements of plants. The first is flactofold, inspired by the carnivorous plants, and their flower and the flactophyme inspired on plants. On flowers. This design proved technical solutions and optimized by nature itself, providing reversible movements, responsive to environmental conditions, and exploration of the research on materials as shaping memory alloy and the glass fiber reinforced the polymer, for example. Future work will intensify research on biological organisms and materials with nastic properties to rethink responsive facades. Here you can see the main reference of the presentation. Thank you so much for your attention. This presentation, are there any questions? For further information, please contact me by email. Thanks for listening.
Thank you. We will continue right now with Cesca Laila Suarez. I know she's also present here with us, and I will start her video right now. So,
Hello, Biodigitals. Good morning. My name is Cesca Laila, a PhD student in the Design Department at the Universidade Federal de Pernambuco from Brazil. I will present to you the work entitled Case Study on the Development of the Buga Fiber Pavilion 2019, Analysis on Biomimetic Materials and Digital Fabrication Aspects. Keywords: design, biomimetics, biomimetic materials, digital fabrication, and synthetic fiber composites. This is the study pavilion. It was developed for the public musical events in the city of Heilbronn, Germany, in 2019. It's part of one of several successful pavilions developed by ICD, Institute for Computational Design, in partnership with ITKE, Institute of Building Structures and Structural Design, both from the Stuttgart University. The project was made possible due to the research of European groups. The biological principle analogy is based on the system composed of natural fibers, such as chitin, cellulose, and collagen, which have thicker and more rigid filaments, and others that are thinner and more elastic, associated with strength and flexibility. In this way, the trusses of the artificial artifact imitate this characteristic through translucent fiberglass, in which black carbon fibers are placed only where they are structurally necessary, resulting in components adapted to the load and yet with a different aesthetic. The production was carried out by the German company Fiber. This image, with the types of fiber composites available by this company, demonstrates the versatility in application possibilities through the use of carbon fiber, fiberglass, which can even be translucent or colored, flex fiber, or even basalt fiber, which can be used alone or in composition between them. In this image, there are details of the design that corresponds to a section of a dome. This dome is configured by several losanges, and with each edge corresponds to a component. It's possible to observe a radial symmetry that allows 7 different components to mirror and repeat, totaling the structure in 60 components. It's also possible to see the order of placement of the fibers in the component. First, the translucent glass fiber, then the black carbon fiber. Altogether, 150,000 meters were used. This part shows the innovative aspect of this institution in digital manufacturing through computer simulation for the placement of fibers. There are also pictures that shows this placement using high technology promoted by the programming of Kuka's robots for the execution of previously simulated components. The pavilion has 400 square meters, 23 meters of free space, supports 7.6 kilograms per square meter, about 5 times less than a steel structure. In a test, each component supports about 25 tons. The diagram represents the methodological approach used by ICD-ITKE, called co-design. Represents the integration in continuous computational feedback between architectural design, structural engineering, and robotic fabrication, which means design and engineering methods, the manufacturing and construction process, and the materials and building systems generate data among themselves, allowing everything to be controlled by computer, and therefore that the changes are adjusted in sync, favoring the development, simulation, and execution of the project. In this image, it's observed that the project designer generates data allowing simulations of engineering analysis on the computer. In these pictures, it's possible to see details of the stages of assembly of the components and details of the interior of the pavilion. Details of some views at the top with geometric designs like a flower, details of illuminated top view, details of views in perspective, and details of the location in the Park of Heilbronn. Once again, this view of the Buga fiber pavilion in used. Note here that the translucent glass fibers were useful for the lighting effect. If it were completely all carbon fiber, this aesthetic and functional characteristic would be lost, in addition to making it more expensive. In the conclusion, the analogy with the efficiency of natural fibers resulted in a net effect with a greater innovation factor through new and more effective materials and construction process, lighter, articulated, flexible and high-performance structures, and also through the use of technological tools that enable the translation of more organic forms, facilitating the design through software and computer-controlled machines for the constructions, evaluations and manufacturing of models more aligned with sustainability, thus expanding the potentials for new and different applications. Thus, it is observed that even with a personalized manufacturing project, which recently would have necessarily cost much more, making it impossible to scale it, this project shows several advantages of the economy through its components, whether in the agility of its elaboration, in the assembly, or in the lighter weight of the structure, which brings optimism in the endeavor to make the extraordinary more accessible. Any questions, please contact me through the email. I will reply as soon as possible. Thank you for your attention. See you soon.
Yes, can you see it?
Yes, we can see everything, Judith.
But I cannot. Yes, you see it clearly, yeah?
Yes,
okay.
Clearly, yes.
Okay, fantastic. Thank you very much. Well, thank you to the organizers of the Congress, first of all, and the team that make it possible. This presentation has been done by Professor Alberto Estevez and I. So we have been always interested in the origins of biodigital architecture, and we try to find different works of art. I am art historian, and Professor Estevez is architect, but is also art historian. We have some contributions about Gaudí and Dalí, and as some of you know, I teach in the master's and first classes about them. So this time we will talk about some important surrealist painters as Max Ernst and Yves Tanguy, or the symbolist painter Buchling, for example, and the metaphysical painter Giorgio de Chirico, or before all of them, Hieronymus Bosch. El Bosco, Hieronymus Bosch, in his paintings, as this The Garden of the Earthly Delights, we find a fascinating architecture. Some images take us to a fantasy world with invented architectures that seem to have emerged from nature. That are mostly round, as you can see, curved, with cavities and amorphous volumes. He also invented animal figures and scenes with men and women of great imagination. So it's a very evident for us surreal metamorphosis years before of the beginning of surrealism, of course, in 1924, because El Bosco, as you know, is from UC 1419 is this painting. Also, Giorgio de Chirico was a great influence for the surrealists, but he also received influence from the disturbing symbolism of Arnold Buchling. So some examples here, for example, in one element that is the cypress. The cypress tree was an important element also in Dalí's paintings, as we will see. It's a very tree tall, as if it wanted to reach the sky, and always green, yeah? So this is a symbol of eternity, and for this reason we find them planted in cemeteries. So it seems very natural to find this tree in Arnold Buchling's enigmatic Island of the Dead, where a boat, if you see, arrives with one of its new inhabitants of the Island of the Dead, accompanied by the same death that is dressed in white. If you see on the right of the PowerPoint, you can see another figure, white figure, in a painting of de Chirico. So these two figures are very, very similar. So we can see this enigmatism in both artists. Also, in this work, Villa by the Sea, 2, on the left, we can compare with, again, de Chirico on the right. These two black figures that you see, and also in the left one, you see again the image of the cypresses, no? This time inclined by the force of the wind, this raging wind that pushes them hard. But again, no, we have a woman dressed in black, seems to be waiting for something. So again, this enigmatic view, so typical of this symbolist, and that will be also very, very typical in the metaphysical paintings of de Chirico. Then Dalí arrives here. As you see, on the left, we have again this Island of Dead, as we have seen before, for comparing the cypress tree. Yeah, as you see in the second image, ossification of the cypress. This is a work of Dalí. He likes cypresses because of a childhood memory, and they are present in many of his works. So in this one, it's for us special because if you see, the cypress is like a solid building with an interior space, with a hole, no, with a cavity, from which a white horse emerges, almost out of control. Also on the right, or in the center, you see again, strange cypresses that appear in a painting of Max Ernst, that it's another very important surrealist painter. In here, in this title is Solitary Tree and Merit Trees. These trees are personified and he turns them into architecture also. And of course, on the right, we found another building very famous, that is Gaudí Sagrada Familia. And in the center of the old facade that he made, we found again a cypress tree. And this is a gigantic cypress in the center of this old facade, as it has never seen before in the history of art and architecture. So it's quite surreal also to find, and made around 1910. We find other pieces, 10% genetic architecture. For example, in the collaboration of Dalí and Alfred Hitchcock, the director of cinema, for the movie Spellbound. We see these rooted architectures as the chimney above the house that you see on the left. No one could design this better than Dalí, because in this scene of the film, Gregory Peck, that was the main actor, he recounted in front of Ingrid Bergman the dream that he had. So it's a landscape of a dream. So for this reason, I say that no one better than Dalí to explain that in images, right? This was in 1945. Apart from the chimney with roots, we can see also on the left a rock that is half a rock, half a face. And also we have trees that are emerging from that head. On the right, we have again a Max Ernst painting. And it's true that his work seemed to be alive, yeah, in Europe after the rain too. Everything is crowded with natural elements, mixed, as if they have to grow out of control, no? With eyes and mouths that are confused in the scrap. And I have to introduce another painter, that is Yves Tanguy, another surrealist painter. It's interesting to compare these landscapes with those of another, with the buildings of Antoni Gaudí that you have on the right, La Pedrera or Casa Milà, as you want. Tanguy used to pile organic forms, pile up organic forms in infinite landscapes. On the right, we have made the comparison. Here you have La Pedrera from Gaudí, and at the bottom, we have here the comparison, as you see, the elements of Yves Tanguy in order to compare that, yeah? And in here, we have, we go to the Baroque, we go to 17th century in these two paintings that you have above, the one on the left and the one in the center. The first is by Francisco de Zurbarán, and the second is from Juan Sánchez Cotán. They are two Baroque Spanish painters, 16th century. And the last one on the right is by Giorgio Morandi. It's an avant-garde painter, very linked with futurism and also with metaphysical painting. These three paintings had one thing in common. They are still lifes, no? They are objects represented or fruits represented. Below this, you can see some metamorphoses, yeah, in microscopic structures that had been inspired by these paintings that you have, made by Professor Estevez using the scanning electron microscope. Returning to Gaudí and Dalí, we can compare again Casa Milà on your left and Casa Batlló, and his organic forms that we find also in Dalí. No? For example, in the center, you can see this soft architecture. Remember that Dalí said that the architecture of Art Nouveau, and of course the architecture of Gaudí, was soft and eatable. Dalí was fascinated by melting cheese, and he liked very much undercooked omelets and stuff like that. So for this reason, he found surprising when he saw the buildings of Gaudí, the way in which Gaudí's stone is melting into these fluid curves, especially when the avant-garde architecture of the 20s and 30s was the contrary of that, no? It was, of course, rational and orthogonal, no? The influence of rational functionalism. So these cavities and organic masses that we found in La Padrera, we can find them also in these paintings of Dali. For example, this Birth of Liquid Desires that you have in the center. And on the right, you have a view of Casa Batlló. And if you see these columns very thick, very thin, sorry, these are like crutches, like sticks in the painting that you have on the right, the Spectre du Sex Appeal, also of Dali. I have to explain you that Dali was very interested in DNA from the very beginning. When it was deciphered by the genetist Francis Crick and James D. Watson in 1953, Dali painted the chain of DNA in many of his paintings. Well, here we have also some paintings of Tanguy, one painting on the left of Tanguy, that seems to have been the inspiration also for some other projects. For example, the landscape on this landscape series of Alberto Esteves in the center, and also this landscape, we can say also, of pieces, this production from a digital design and production of the pieces from a radiolaria and a hyperboloid, thanks to, again, Alberto Esteves and Pablo Vaquero. No? So we have different proposals that we can see like inspired in these landscapes of Tanguy. And let me finish then, these are also some landscapes influenced by that, and let me finish with this image, again with this influence, Chirico to Dali. We see how Dali takes from the first, the arches on the left, as you can see, and the view to the horizon, and he painted on the right a sewing machine with umbrellas on the top, something very strange, but that makes a direct reference to Isidore Ducasse, the Count of Lautremont, who in 1890, very, very early, 1890, wrote a fortuitous encounter of a sewing machine and an umbrella on a dissecting table. A very enigmatic, again, sentence that was taken by the surrealist as a new paradigm for his art, for his ready-mades and his objets trouvés. So we hope to find more examples of proto-digital painters and artists for the next one, surrealist or not. So thank you very much, and if you have any questions, I'm here to answer. Thanks.
And now we will continue with Pablo Vaquero and Efimia Giannopoulou and Alberto Esteves. So in a small moment, we'll show their presentation.
This is Kalaya with which email?
I had no idea. Okay, so here we go.
Hello, my name is Efimia Giannopoulou, and I'm presenting together with Pablo the article of this conference. In this presentation, we introduce a unified force-driven design approach for generating complex geometries, especially for the purpose of additive manufacturing large-scale physical objects. And it's about a typological search of furniture that configures architecture and design with the tools and possibilities of the 21st century. Those have been developed in the Institute of Biodigital Architecture and Genetics in collaboration with Numena. So design for manufacturing involves simultaneously considering design goals and manufacturing constraints in order to identify manufacturing problems while parts are being designed. This should involve designing and optimizing a product together with its production system. And specifically, responding to the challenge to design for additive manufacturing rather than 3D printed design, the fabrication method and materiality establish the generative design constraints that inform the geometry. This research is trying to bridge the gap between rapid prototyping and mass production, taking into account all consideration, requirements, and post-processes for this transition. The objects, especially designed for 3D printing, could not be mass-produced with other traditional technology because basically of the economical cost of small amounts of products. By physical testing and computer simulation, we examine how the causes and effects of additive manufacturing limitations could be integrated inside a unified design workflow as driving forces for large-scale thin cells and hollow structures. The radiolaria and hyperboloid series of furniture are presented here as an outcome of this research. Here are some of the issues that have been examined inside the articles that are driving the design process. In most rapid prototype systems is the weakness of the stereolithography files produced by softwares, and especially the approximations of the curved surface of the layer with a uniform thickness. Here the focus is in the slicing process, which produces overhangs and gaps, especially at the saddle shaped areas of the main body of the thin cell. Adapted strategies have been proposed by many researchers, but basically they are post-processes focused on improving the manufacturability of an existing geometry rather than introducing a new design approach, especially for 3D printing. So inspired by natural phenomena such as minimal surfaces and capillary bridges between particles, the hypothesis is that using dynamic relaxation with particle spring systems and applying different warps and wedge forces, it's possible to interactively control the geometry as one continuous element module in equilibrium, and to adjust geometry and overhangs, balancing internal structure, economize material and traveling time at the same time. The goal is to The term thin cell is used here to describe a self-supported structure of thin wall curved surface with near zero mean curvature. This type of structures have many advantages, like minimizing the amount of material and achieving surface continuity, which increases structural behavior. Programming the curves of the thin cell as network structure gives the advantage of considering them as structural elements and at the same time as tooling paths.
The proposed methodology consists on the feedback between three different stages: mesh relaxation, mesh construction, spring-based dynamic relaxation, and tool path optimization. This animation shows the single arc relaxation in the final slicing method optimized. And an initial model was adjusted for three different module typologies. One with one module, the radiolarias tool. The second, the radiolaria bench with two modules, and the hyperboloid chair with three modules. The conception of the initial module is constructed based on the connection of a sphere, 11 external polygons, 6 lateral hexagons, 6 triangles, top and bottom hexagon. The hexagon and the triangle's polylines are treated at the same manner. First, the connection is made by making a surface between the triangle, the projected triangle, and the sphere, and the scale twin curve, half of the distance between them. See figure 1. In order to find the spring segments, the surface is converted to a mesh of 4 by 8 hexagons faces. The quantity of mesh divisions of 4 in one direction is the same for all of the polygons in order to keep the same continuity of all the meshes, but the opposite direction varies according to each type of polygon. The edges from every face are extracted on two sets of lines, the rings and the and the perpendiculars. The rings are the wraps and the wraps are the perpendiculars, but one of them is selected in order later to apply the strength and accomplish a pinching approach behavior on the relaxation. All of these sets of lines are converted to springs with the same strength on the wraps with a zero length to keep the minimal characteristic. The wrapped forces are different for each mesh type, so the diameter of the mesh of the polygon depends on the quantity of wrap divisions and the strength of the springs in the figure 2. Every model typology has different geometrical and dynamical goals, but most of them have 12 anchors per module. This single module has an extra goal. This is the gravity in order to have the top and the bottom particles in the z direction for two purposes. One, to allow the top part for the comfortable sitting, and the second to 3D print the bottom part more easily. The final relaxed model is later subdivided to 2 times to keep up mesh continuity and have less strength on the anchors to make and also to make it stronger. In the figure 4 you can see the the, the mean curvature where the pink area has less continuity and red has more mesh continuation. During the dynamic relaxation process, the spring strength is in all reds is the same that allow maximum surface continuity between the parts, but the reps strengths are different in every generated geometry in order to control the various aspects of the manufacturing process. The mean curvature analysis indicates the location of the most continuity, figure 4, which is exactly the location of the anchor points, here in the pink areas. In general, the method of slicing and sending 2G code to the printer has a very generic parameters, most but much for but not much for variable layer height. 3D parts, 3D paths, curved paths, there are custom fields and other most commercial and open source slices like Cura and Simplify. Especially for large 3D printed structure, it is crucial to optimize the traveling time and the printing time. For now, the best solution that we have been keeping trying to do is the single path with no travelings, but this limits a lot the design. For each experiment, the parametric programming of the toolpath was different, but in general, the mesh was divided by different type of slicing by the inclination of the mesh face according to the set value. Each of the selected mesh was treated with different layer height. So here in this image we can see that there is two type of slicing: the blue one that is 1.2 and the black one that is 1.6. So we have divided the in sections. So the section A has the 1.2 to allow more seating, to have more curvature in this horizontal area, and 1.6 to support that, and also to keep more surface continuity with the top 1.2, and the support of this top is 1.6 and everything else is 1.6. Only in the blue areas where there is more horizontal faces of the mesh is 1.2 to keep more smoothness on the curvature, and in the pit 1.6 only to support. The proposed method consists by adjusting different values of the sprints in strategic locations, the sprints selection. It is possible to interactively control the reps and the wraps, tensile forces, and adjust the shape to bridge the gap between the criteria and the cellular areas. Consequently, it minimizes the contour gaps, like in this area that is the problem, and then it's optimized like this by the selected springs, and also for structural performances, and also to have an equilibrium between the surface continuation and the fabrication efficiency to adjust the tool paths in the several areas, the bridges between this and this. This is the final. In order to close the several areas, there were many different attempts of empirical tests. Like one of them was to add offsets before, inside, between this in the selected areas to moderate the staircase effect. and to reduce the gaps. Another one was to connect some lines between the holes. But the one that was most successful was just adjusting the springs, like it's appearing here. This is before, this is after, this is before, this is after. So in the case studies, we have this experiment has a different, so the same relaxation method. In order to have a more sitting area in the top, we have adjusted the gravity for these springs or for these vertices of this mesh, and in the bottom is more hollow, so there is more space to print. The second experiment has two modules, and it has a similar relaxation method, but the gravity has been applied in the top. This object was printed sideways, not like the previous one. And then it was and the springs was all of the springs were adjusted to be able to lift the bottom part and have the gravity adjusted for the sitting area. The main body of the shell was divided in many sections, and the shell is only one. There is some internally structured support to support without completely supports. And the last experiment was made of three motors, section with both sides, and it has the same relaxation like the other ones. It has some pull to curve goals with no gravity. The spring strength, quality were changed depending of each mesh, and it has been printed sideways. It has three modules, 1, 2, 3, and it has two layers.
So this article presented an integrated design methodology, especially for 3D print large-scale objects that could be extended to architectural scale also using similar emerging technologies. By acknowledging current limitations, it demonstrates how those could be the driving forces inside the design process. Having actual control of those technologies, the designer, with the expertise, knowledge and education to support it, does not only need to depend on the manufacturing skills, and could also expand design for manufacturing systems. Thank you very much. For any questions, please contact us.
Okay, thank you very much, Pablo, Femi. We will like to continue with Nadia. I know that she's here and she will present live.
Yes, I'm here.
Hello. Sure, I will stop mine and turn on yours in a bit.
Right.
Okay, stop share.
There, does everyone see my screen?
Yes, we can see it.
Perfect.
Wait, hold on. Give me 1 second to put you here.
Great. Good afternoon, everyone, and thank you for being here to listen. My name is Nadja Godilier, and I'm a PhD student at the GSA laboratory in Paris. I'm here to present my paper, Evolutionary Tool and the Practice of Architecture, from Appropriated Typology to Becoming the Black Boxes of Computer-Aided Architectural Design. So the focus of my PhD is a contribution to the history of the computational turn in architecture, and I'm focusing in particular on trying to understand the technical and epistemological biases of algorithmic design tools. In order to do so, I have devised a methodology that is interested in three aspects: socio-historical, technical, and epistemological, and that draws on the science studies methodologies. My PhD work has highlighted three dynamics in the development of the computational turn: appropriation, democratization, and rationalization, all three conveyed by the development of algorithmic tools in architecture. Today, I'm going to focus on evolutionary design tools as a case study for those three dynamics. So very briefly, the corpus of projects I've studied comes from the AD magazine and the Comingcad Acadia database. And if you look at morphogenetic processes in these databases, as they were called before, or as we call them today, evolutionary design tools, then two typology are particularly predominant, L systems and genetic algorithms. I identify as algorithmic typologies specific structure of algorithms found in projects of the computational field and characterized by sets of rules. Those typologies usually eventually evolve to become ready-made tools. A brief definition of the two typologies I'm interested in for this paper. L systems are branching systems, mathematical structures developed in the 19th century. Their current form was developed by Lindenmayer in 1968, and they are most of the time used to simulate plant growth in other fields. Rules include the initiator shape, the generator shape, seed placement, and branching rules, angle, length, and number of branches, as you can see on the diagram on the right. Genetic algorithms that you can see on the other side of the diagram are based on the principle of Darwinian selection. They are a very popular method of optimization in diverse fields nowadays, and their rules include the computation method, the gene pool, the fitness function, and the individual selection. If looking at the chronology of development for evolutionary design tools, then you notice in pink in the present slide, pioneers of evolutionary computation stemming mainly from biology and computer science, two fields that have worked very closely to develop these methods from the 50s to the 70s, culminating in the publication of a couple major books on the subject that have contributed to define evolutionary computation as a field of research in itself. In black, you can see mainstream evolutionary computation framework released in every major programming language in the 90s and the 2000s. In green, you can see evolutionary design in architecture that also started in the 90s with a regular development since and activity both in academia and in the industry. They are accompanied in blue by the apparition of many ready-made algorithmic tools since the 2010s, the tools in which I'm mostly interested in the current presentation. If analyzing the different users that you see in the database for evolutionary design algorithm, you can identify a taxonomy of users characterized by their educational background, their professional environment, their programming skills, and the use made of evolutionary tools. If looking at understanding biases, then two things among those are particularly important. First, the ability for the user to either develop tools and algorithms, or the ability to only use ready-made tools, ready-made algorithms provided online or in open source. And second thing, the use made of evolutionary algorithms. So first, whether it's in academia or in the industry, and second, whether it's for formal and architectural research or for performance optimization. Three categories stand out: skilled practitioner, both in architecture and in engineering, mass users, and software developers. This constellation of users and the computational field in architecture at large constitute what Bruno Latour identifies as a socio-technical network. So Latour identifies the idea of socio-technical networks, and you can consider the computational field, and in particular evolutionary tools, as sub-socio-technical networks. These socio-technical networks are made of institution and practitioner, project, tools, and algorithmic typology, and all those things intertwine into the historical development we know, in particular for evolutionary design tools. So displayed here is the core network of evolutionary design tools with major clusters of developments, and the line indicates connection at large between those clusters and players. So you can see academic clusters, such as early research at the AA, first application developed for build project with clusters such as Arup or Bollinger and Broman, and major software clusters such as McNeil and Autodesk. What is important to note is that compared to other typologies, the core network of evolutionary tool is characterized by an equilibrium between those three kinds of players. Furthermore, the core network of evolutionary design tool is characterized by the phenomenon of appropriation. A mastering of programmation, a bias awareness, and a conscient ideological positioning result in the capacity to implement tacit knowledge or intuition that is at the core of architectural practice into explicit algorithmic structures. And this is this idea of implementing intuition or tacit knowledge that characterizes the capacity of appropriation of a given algorithmic tool. Now, while the computational field has grown in the past years, we've seen many new users and many new tools appear, both professionalized resources from the software industry and open source plugins. With democratization, the interface becomes an especially important feature of those tools, given that it's the first access to the algorithmic structure, the algorithmic typology the tool resorts to. In order to analyze the different interfaces that evolutionary design tools provide, I've relied on the notion of thickness of interface as used in UX design to qualify the distance between what a user can perceive and manipulate of a program through its interface and the actual structure of the program. As an example, I've here shown the scripting structure of a custom algorithm written by EasyCT in 2007. It's a genetic algorithm that has for objective an equal repartition of light throughout the space it generates. It's broken down in the different layers of its interface, and you can also see pointed out the different layers of interface when you can access the rules that characterize the typology of a genetic algorithm. Now, if trying to achieve the same algorithmic goal, but with ready-made algorithmic tools such as Grasshopper and its plugin, rather than by scripting directly an algorithm yourself, then the structure will change into what you see now. So you can see that while the precedent custom algorithmic structure had 5 layers, this one has 7 layers with 2 double layers. But on the other hand, the previous one necessitates the resort to 12 software, whereas this one only needs to resort to 3 softwares. The second important thing to note is that the rules in the custom algorithm can be accessed in 2 different layers that are both scripted layers. And in the ready-made algorithm, you see 5 layers with 3 different types of interface, user interface, DLL, or scripted. Meaning that in the first case, you only mobilize 1 level of competence, even if it's a high level of programming skill, whereas in this one, in order to access all the rules, you have to mobilize 3 different levels of competences. Now, if applying this method of analysis to a larger number of recent evolutionary design tools, the thickening of the interface becomes very obvious. And the second thing that becomes obvious is this separation in 2 parts of algorithmic structures in recent algorithms. With the first part, with the user interface that's easier to manipulate, that only enables the access to 1 series of rules, and in deeper layers, access to other rules. Basically, this means that it gets harder to grasp the full structure, it gets harder to control fully the structure if you are an unskilled user. And we've seen that many more unskilled users are now part of the field. So as mentioned, the appearance of interfaces easing off the use of complex algorithmic structures is instrumental to the democratization of computational design practice. But I also have the consequence of diminishing user skills necessitated and to grow the distance between practitioner and the technical structure of algorithm, therefore encouraging technical biases. Furthermore, in the case of evolutionary design tools, you can notice that the intention carried by tool makers does not always fit the intention of tool users. And this separation, this thickening of interface, doesn't always allow the user to take control again of the tool, thus encouraging epistemological biases. In particular, while in the first period of evolutionary design, as practiced by the core network, innovative ways of using those typologies, of hijacking the rule structures emerge, most of current design tools are only used simply in performance optimization. One could nevertheless ask what an optimal architecture is and whether it's only reaching top performance in measurable physical phenomenon or if there is more to it. In general, we can see that current evolutionary design tools result in a rationalization of architectural practice, neglecting the tacit dimension of it by favoring optimization of explicit and known recognized physical models, thus encouraging evolutionary design tools to become black boxes in computational aided design. I'd like to conclude the presentation by asking whether we should focus on the democratization of our tools at all costs, or whether we should interrogate again if we would rather encourage appropriation or rationalization, and how we design interfaces in order to guide the user either towards replicating dominant approaches or towards controlling the approaches they'd like to implement. Thank you.
Thank you very much, Nadia, for the presentation. We will now continue with our final presentation for this session, which is Viviana Hernandez. And she will present through a video that she sent. I know she's here with us.
The current demand for the inclusion of computer-aided design and manufacturing in academic courses is increasing. Consequently, schools of architecture are adding to their curricula elective courses in an attempt to give the students general knowledge about digital tools. Resultantly, students use them merely as a representation tool in last stages of their design studio projects, leaving apart the potential that CAD/CAM systems represents for the creative process. As an effort to include CAD/CAM systems as part of the learning process, an educational program based on practical workshops combined with theoretical framework has been developed in Bolivia. The workshop program aims to become a new strategy to incorporate novel methodologies to traditional academic programs at architectural schools. The objective is to provide not only a general understanding of the technology itself, but its application in practice along a process which includes three main interrelated aspects: material experimentation, digital design, and manufacturing process. This paper outlines the pedagogical approach and technical outcome of a series of workshops carried out at undergraduate level: digital crafts, digital systems, and responsive systems workshop. First, we describe a construction of knowledge methodology based on design, experiments, and learning by doing. Then we evaluate results as a function of developed skills, and as a conclusion we propose the revision of areas of architectural syllabus in the light of advances of new technologies. Our strategy was to place digital development of medium-scale prototypes resulting from a material experimentation process. Contrary to the traditional teaching that overvalues the teacher, the process promotes a collaborative learning process involving tutors and students organized in teams. This method provides the possibility to acquire theoretical knowledge about complex geometry concepts and practical knowledge about material properties that leads to an exploration on digital processing. The learning program proposed a 6-day workshop conceived as a research project based on the growth and Wang's theory founded on experimental research. This theory considers experimental strategy as a research process for design. That is, with the aim of develop a design result argued by different steps appropriately applied to a particular question. This method presents 5 characteristics: an independent variable, material behavior; the measurement of the variable, performance assessment by the application of external inputs; the designation of a unit of assignment, test device; the use of comparison groups, experimentation over different materials using the test device; and a focus on causality, catalogs of measurable results and prototypes. The proposed methodology considers material behavior results as the main source of information as an input for the workflow. What the materials allows in terms of physics performance become the characteristics of the whole future system developed in the next phases of the workshop. The workshop intends to apply this principle to the projects, guiding participants to choose one example in nature with characteristics of proliferated skins, differentiated patterns, or responsive cells. The next 2 phases about digital systems and manufacturing process are developed in parallel and will be the path to create a material system, a system that involves material characteristics, geometric behavior, manufacturing constraints, and assembly logics within an integral computational model. The workshop is based on the idea that morphology is not an independent variable, but is an intrinsic characteristic on a system as it is in nature. The process of morphological generation is developed through the setup of a computational model, affording further differentiation that remains coherent with the behavior observed from physical experiments. Through a fabrication integrated design process, the students are able to deal with a variety of processes between design conception and execution. Each team must control different variables, which include cutting depth differentiation, labeling process, and assembly process. As a result, the creation of a material system instead of a digital system by itself promotes an understanding of form, material, structure, and behavior, not as separate elements, but rather as complex interrelations. Natural systems generates a dynamic process driven by the ability to adapt themselves to external constraints. Informed by this behavior, the workshop developed two types of approaches. The first one relies in geometric adaptation, and the second based on responsive differentiation. During the workshop Digital Crafts, participants design and manufacture component-based physical models. Due to the geometric constraints of the proliferation environment, a double curvature control surface, components must adapt themselves geometrically at a local scale. In this sense, geometric differentiation is an adaptation strategy that responds to a morphologic constraint and has impact on the materialization process at a higher scale. The workshop Responsive Systems focus in the development of a responsive skin that reacts to different environmental impulses was generated based on photosensitive components. This workshop expanded upon the concepts of adaptation as a domain in which design can exploit environmental information and embrace a model that produces a feedback loop between the environmental characteristics as a sensorial interface and the architectural response at a component level. The obtained results represent a multi-step and highly iterative process which goes from digital approaches to the physical materialization, back and forth. Material System Workshop demonstrates that new technologies applied in design learning practice have the potential of eliminating the separation between form generation and materialization processes, the major gap in traditional learning methodologies. Although understanding material behavior as a design tool opens up the possibility for architects to reconcile designing with constructing, the skills needed to instrumentalize such behaviors are far away from the standard syllables taught in architectural schools. Developments in the digital tools available to designers require a more complex design thinking approach, from a linear deterministic design process towards an algorithmic thinking to engage design problems, leveraging in this way the full potential of computational design. On the other hand, it is not only the way architects think that becomes challenged. The same proposition could be made for the way architects represent design, where a conventional dihedral description of a shape does not account for temporal, dynamic, hierarchical, associative, or responsive properties of a material system. The digital age has radically reconfigured the relationship between conception and production, creating a direct link between what can be conceived and what can be constructed. The workshop achieves to create this relationship by valuing the generation process instead of showing only the product. It is necessary to consider the design process as a feedback progression in which each participant develops a research strategy instead of following a list of steps. Another outstanding subject extracted from these experiences is about self-learning method, which provides students with the strategy allowing continuous learning of digital technologies in architecture, even beyond the educational program. Although 3 workshops have been developed addressing different subjects, the methodology allows to apply the 5 characteristics from growth and one theory to diverse topics. Constructing upon this flexibility, a future experience could be developed in an interdisciplinary context in order to test the proposal and prove its application capacity to more collaborative learning. Thank you.
Thank you for the presentation, Viviana. Right now we are at the end of session 4, and we can have a break and also have discussions. If somebody wants to say anything or ask questions, we are here. If not, we will meet again in 10 minutes.
10 minutes. Thank you.
We are back. We will follow up with a keynote by Gonçalo Castro Henriquez. And I presume he's here. I will see right now what we have for him so we can start the 5th session.
Hello everyone, it's good to be back.
We will start soon. All right. So I will share the screen. I don't know. I'm still sharing. Okay, good. So we can start right now.
Hello everyone, it's good to be back home at the week. Congratulations for the 20 years of the digital biodigital course. Thank you, Alberto Esteves, for the invitation and for everything. My name is Gonçalo Castro Henriques, and I'm talking from Rio de Janeiro. So welcome aboard. My lecture is called Network Design Exchange. So I will talk about how to integrate and share information. I will start by my European experience, and then since 2015, when I moved to Brazil. Well, when I finished my architectural degree in Porto, there was a macro segregation in construction. Architects, contractors, scientists, and engineering, they were working separately. And there was this promise of the information technologies and the digital to integrate these players to work more closely. Also, in a micro level, there was also a segregation in architecture between the projects done in academia that tend to be developed in conception and then put into practice in construction in a linear fashion mode. Also, the digital promised to integrate this in a process with computer-aided manufacture, computer-aided engineering and design, and to promote an asynchronous process where you could start in any part of the process. So my experience, I started in Porto, and then one important decision was to do a master in Barcelona. And guess who received us in Barcelona? Alberto Esteves, a pioneer and founder of the course, here with me, and José Pedro Souza, a close friend. Well, after the master, I started experimenting in academy. I didn't have a position, so I started teaching seminars and workshops, and also connect with the industry to do research, to do technology transfer, because there were no labs available at the moment. So, and to find projects in practice where we could test and advance this application. So here we see some of the workshops and the generation of form, the research of the manufacturer with the additive, subtractive, and transformative processes done with industry, and in the practice of some small projects to test this design. So back to Porto, I invited Branko Kolarevic, Bernard Franken, Marta Malé, José Pedro Souza to bring these new digital technologies and this attitude to the local students. And actually, we did the first Rhino scripting workshop in Portugal. And at that time, the students, so they wrote an algorithm in the left, in the text mode, so they will have design results in, you can see in the right. And this was the project was to design a bridge. Here we can see some of the parametric bridges they designed. And then this idea of bridges was also tested here in Slovenia, but back then we start to use Grasshopper visual programming that will make a big change. And actually, this is in São Paulo at the Mackenzie, at the Sigradi, and it was the first Grasshopper in workshop in South America. Here we see some of the solutions the students developed for the local courtyard. And then this resulted also in this other opportunity, an invitation by Mauro Chiarella to Argentina, to Santa Fe, where we worked with the undergraduated, postgraduated, and professionals of architecture to develop solutions also in the mixed analog and digital process. And then back to Porto and to Brazil again, there was this opportunity in the Sigrade at Ceará, an invitation by Daniel Cardoso, and a partnership with the local industry, and one of the students was in this industry to fabricate the solutions. So the participants, they had the opportunity to develop the full process and design three different installations for this event. And this was a big help to put the discussion further in the Congress. Also back then to Porto, another opportunity was this Future Tradition seminar organized by José Pedro Sousa, and where I teach a workshop with Tobias Schmid. Here we can see some of the experiments. Well, and at that time, the application of the manufactured techniques was difficult to assess. We didn't have so much labs, so I started to experiment right in the master in this Art Week. Here, in one project. This one is called Integral Envelopes and was developed with Achim Menges. He did teach at the week. Was not so famous, but now we see the result of it. And here some experiments with the concrete at Faculty of Engineering in Porto. And here using traditional wood building techniques in Helsinki to design a wooden sauna. Well, back then I won my first international competition for a small pavilion in Ireland. Of course, all the fabrication was done in an industry in Porto for wood. So a wood furniture company, and I had to go to Ireland and to assemble all the structure with a local team. And this was a landscape that integrated the vegetation and all the design in an experience. And then I won another competition for an installation in a garden called Honeyscape. And the idea is this installation will change its light and shadow during the day and offer protection and rest for the participants in this space. Well, back then I started my PhD workshop, PhD research with José Duarte. I was still in Porto, but the collaboration with the Lisbon University. So I developed this responsive system. The first, the jackfruit and the durian were influences in these first ideas. And also, of course, the dynastic movements of plants to daylight. And here are some of the process. And here is the simulation and the test to start a full-scale prototype with OSB in Faculty of Engineering. Here we see some of the installation that Faculty of Engineering. Also, this was automated partially. And then the simulation of the daylight influence. Here is the resume of the system function. There is a shared user and computer input. You can see publication about this if you want to see a little more about this control of the looks, illumination, and visual contrast inside the pavilion. And this pavilion was also assembled and to represent Lisbon University in Florence and Beyond Media. And well, and then I started my overseas experiences in Brazil. So there was an invitation from Andrés Pássaro to work in LEMO. LEMO is a laboratory of models and digital fabrication, and is a very horizontal structure where all the agents contribute to an emergent result. So when I went there, there was this summer workshop where the students fabricate this project developed by Clarice Rose, that it was her final project. And what was curious is that the students, they didn't know how to program, but they already knew about the digital fabrication. So this was a workshop with all the students to build this project. And here we can see some of the results of this house, wiki house system. And then here in another final project by David Mendonça, we adapted the algorithm for curved geometries, and we fabricate the project in his final graduation project. Then and a lot of activities working appear in LEMO. This is a workshop coordinated by Maria Angela Diaz, and here with the Spanish architect Andrés Pastor and all the team. Here we are testing helicoidal surfaces from mock-ups, and then here we see the environment of the building of the pavilion, helicoidal surface butterfly gallery, and here are all the satisfaction of the team and some of the results of this pavilion. Another experience was this partnership breakfast between Brazil and Germany with Tobias Wallissen, an architect from Stuttgart. And the idea here was to combine a German technique with a local Brazilian material, in this case the bamboo. And then we did the other way around and went to Germany and test indigenous typology of occas in Stuttgart. Well, here in Rio we can see the environment of the workshop and some projects from the participants, and tests of the assemblage of the structure. And here we can see the grid shell, an elastic grid shell from the ground, raising up with all the participants. And we learned a lot with this process, with this bamboo. We are now researching more on a material level, but it was really a nice experience. Well, another experience was a technology park, an invitation by Leonardo Melo, here with Adriana Sansão and Andrés Pássaro. We developed with undergraduate and postgraduate students different solutions, 5 groups. One was selected, the one with Isadora Tebaldi, that is here on the forefront, coordinating the assemblage of the tornado. And this tornado pavilion, this is a passage in the technological part to protect with shadow this tropical, very intense sun, and for the passengers to rest and find some peace. Of course, we didn't have all these tools that for fabrication, so we had to make a mixed technique without CNC, imagine, so to make this possible. So this is a group work, and here we see, of course, the group. And what we do have is regular workshops every year. This one is called Defying Gravity, and we tested different responsive solutions for design with the participants. Here we see a little of this environment with Arduino, with sensors, and the satisfaction again of the group. Well, we got involved in a movement that is called Homo Faber between the Fab Labs in South America by Sperling and Herrera. And this was also an important connection with the Sigradi community. And this also gave us some ideas about how to evolve the network in a more broader range. So we know that there will be a conference of ECADI conference in Porto, and I was together with Sigradi, and so we challenged ECADI to make a joint conference in Porto, and José Pedro Sousa accepted this, and this was actually a long negotiation process to do, because people were not so comfortable, because it was the first time two major associations of digital design will happen at the same time. So we did it. Architecture in the fourth revolution was a conference in Porto in the Faculty of Architecture. Here I am with Jose. We chair this event, and these are the publications. But these publications are important, and we must be thankful for all the authors. But what was also very good is we could join both organizations and work together. And as I said, this was the first time, so it was a long work, but it was very, very nice at the end. All came together. And so there are many challenges to balance these network connections. So there is kind of between culture and the environment, between agent and system, between bottom up and top down, between material and digital, between tool and process. So this also affects the design and the technology and all the environment. So these are different things to balance. So this network exchange I've just shown you or share with you. The results, we can see some in the academia, workshops, conferences, stimulating all the students with this in digital revolution. Also in the industry, before the Fab Labs, we work more with companies to do technology transfer and joint experience that will result in some research projects. Well, in the Lamo examples, I've shown you some pavilions as the Wiki House, on surfaces, the grid shell, also some initiatives as the Homo Faber, the Fab Lab in Latin America. We did this joint conference, ECADI, Sigradi, that was a great organization, and we do regular workshops, applied research in the network. Well, our intention is to be the lab as a facilitator of knowledge, a catalyzer, sharing a network force. So to have applied innovation and a social contribution. So thank you very much for your attention. We'll now go for the session, so we can talk a little more afterwards. Thank you very much.
Thank you very much, Gonzalo, for the presentation. We will follow up with Joel Ong, who will be presenting here online. I think he's here with us. Joel?
Yes.
Hello, welcome. I can hear you perfectly.
Thank you.
I will stop my sharing and, oh, I can see you.
That's perfect.
Oh, nice weather back here. So, okay.
So I will share my screen, and then we can get started.
Perfectly.
Okay. Are you able to see this?
Yes, we see it perfectly.
Okay. So greetings, everyone, and thank you so much for having me here. I want to say a special thank you to Alberto, who's really been a big motivation and inspiration. And of course to Brascan as well. Thank you so much for all your administrative support behind the scenes, and thank you very much also Gonzalo for this really amazing presentation about how you can synergize research activities, the institution, and also students, which is some of what we really hope to do here as well at York University in Toronto. I especially like the visuals of the Tornado Pavilion and the Durian. I'm originally from Singapore, so that's almost like our unofficial national fruit. So that brings back some really nice memories as well. So my name is Joel Ong. I'm an assistant professor in computational arts at York University in Toronto, but I'm also the director for Sensorium, which is a research unit and a research unit entitled the Center for Digital Art and Technology, where we really focus on multidisciplinary approaches to digital culture today, which may include the intersection of computational and engineering and architectural systems, but also in social systems and cultural systems as well, and how the digital plays a role in mediating some of the, it's very, very current. I mean, some of the social and maybe social-political conditions that we live in today as well. I want to preface this talk also to say that I'm also the director of the AMPD Makerspace, which is our school's DIY makerspace, and so a lot of the tools and technologies that are incorporated within my work fall within these fabrication and kind of maker ethos of continual experimentation and failure and troubleshooting and then failure again, and we all know how that goes. But prototyping will be something that I want to emphasize my work is. On that note, I want to say that this project entitled the Frozen Sound BioArt in the Environmental Microbiome as Database is a work in progress, and I want to credit the people that I'm working with on this. Sensorium, obviously, as a research body. We also work with Professor Mark Gordon at the Air Quality Research Lab at York University, and I'm also very closely working with the Gutman Laboratory in Pathogenic Genomics and Evolution at the University of Toronto, where we look at the evolutionary characteristics of atmospheric microorganisms. So this project actually explores a hybrid biological and technological approach to the controversial topic of climate geoengineering by adding poetry to the DNA of a bacterium that is implicated in cloud seeding. That would be the Pseudomonas syringae, so as to speculate on possible biofutures where clouds and rain are user customizable. That's a bit of a mouthful, but I hope this will be a little clearer as we go along. Now, I want to say, because of COVID, a lot of the initiatives that we were planned to happen over the last 2 or 3 months were not able to happen. So a lot of this is kind of speculative research for the future when research laboratories and collaborations resume. But I want to talk about very briefly about the motivations for this project and why we're actually interested in it. One is, obviously, there is a current kind of turn towards the meteorological and kind of revival and interest in the climate, in the weather, and not only from a global perspective in terms of climate change and climate mitigation, but also on a personal level, like how does the weather affect you, or what are the aesthetics of the experience outdoors in a very personal kind of sensorial context. These photos that I have over here on the right are actually taken from this new Facebook group that you guys can go ahead and join. It's called The Sky Over Corona. And it basically just shows people just taking photos of the sky above, above them. So you can see all these different countries and different aesthetics as well. It's really beautiful. But it kind of speaks to this desire for us to look beyond what's actually happening on the ground, kind of looking towards the air and the sky as some kind of vestige of freedom, perhaps, or some kind of metaphor for maybe a more calm or a more beautiful place of being. So in responding to the meteorological turn, I'm really interested in this collision of literary, philosophical, aesthetic, and computational modes of understanding the atmosphere. I'm interested, again, in these kinds of elemental metaphors of freedom, of beauty, that transition between disciplinary boundaries. Anyone, an artist, scientist, or engineer can understand the allure of the wild, for instance, the beauty of clouds. And in terms of looking practically at the situation where we're facing, looking up at the skies, and it's not just like a patch of beauty and this is wildness in its epitome, quite the opposite, actually. The air itself is almost as synthetic, one might argue, as the very things that we engage with on a day-to-day basis. And the latest move, I think, to accentuate this point is this idea of geoengineering that focuses very much on how we can see inorganic particles into the air in order to mold it to a climate that we desire. So how can art be an aesthetic catalyst for this? Right. And on the other side of it, I really am interested in exploring the emergent material and sensory matrices between digital and biological. And clouds are great because they're a great case study of liminality. Da Vinci calls these like bodies without surfaces. And the idea that, we don't want to engage in models of individuation, again, reiterate these kind of traditional classical narratives. But instead, like all the other speakers today, we want to think about generative and involving kind of allopoetics that considers the bodies as composed of gradient forces. Like how does the environment kind of act on it and what shapes and forms do you? So clouds are amazing that way because, they're basically a visualization of wind or environmental factors. So what we engage in is co-cultures of cloud-inducing assemblages. We don't want to just do mimetic architectures. We are interested in architectures that are created with biological and maybe inorganic materials in some kind of a hybrid form so that they're intrinsically responsive. So we have a triptych of approaches. We have the field studies where we do environmental sensing, we do capture with weather balloons, things like that, looking for microbes in the atmosphere. We also have in silico analysis, so we do metagenomic sampling of samples in the ocean, and that's Niagara on the right here, falls, and we do some modeling and parametric design. And also we're interested in how artificial intelligence can kind of factor in this. That's a little bit new, and I'll talk really briefly about that in a couple of minutes. The in vitro section is kind of what's the most interesting at this point, where we can induce ice formation using some of these bacteria or bacteria assemblages that we have designed. So the idea of bioprecipitation in the atmosphere obviously is not a new thing. People have known about this since the 70s, but organic particles account for almost 20% of condensation nuclei in the atmosphere. So if we pitch that up, it just basically means that 20% of all the clouds that you see, or 20% of the cloud mass in total, is actually formed by the aggregation of ice around organic particles. So cloud seeding is interested in throwing up more inorganic particles like silicon or sulfur into the atmosphere. And we're asking, is there a possibility for us to be working with these organic materials already present in the clouds in order to meet the requirements that we need for climate geoengineering? And of course, through an artistic process that's kind of outreach dependent, we also want to contribute to the awareness and conversations and discourses between the institutions, public policymakers, and the general public. So in the lab, we do some of these like really simple, like high school type experiments where we use bacteria to generate ice. And there you can see here, these are some of the early things that we did. And then we started doing more interesting type modeling processes. On the left here, this is a YouTube video. This is a historical YouTube video of ice nucleation. And on the right, we do a little bit of simulation based on the formation of icicles in this lab called the Icicle Lab at the University of Toronto. Okay, let's keep moving. And what it ends us up with, one aspect of it is in public presentation. So this is a couple of experiments that we were showcasing. These are parametric speakers that are actually moving in tandem with the formation of the cloud. And parametric speakers, as you know, I'll just stop that on that. Parametric speakers, as you know, kind of direct sound into certain locations in space. So they kind of activate the architecture in a way that when you're standing right next to them, you don't hear the sound from the speakers themselves, but you hear them at their positions of reflection. So if it's piping up into a space that's about 50 feet above your head, you will actually hear it as though there were a speaker 50 feet above your head. So that's a nice way of kind of generating the kind of inside experience where you're standing next to it, but you feel sounds moving around you all the time. And that's what we wanted to create, a kind of artificial synthetic cloud that's made of a soundscape around your body, wherever wherever this is installed. The artificial intelligence part of it, right now is it's basically just a way of us creating raw materials for inclusion within that DNA. Right. So right now we're using a generative adversarial network to train phrases on key text by Jorge Luis Borges, who wrote, most of you know, who wrote really about the universe as a kind of never-ending or infinite library. So there's that kind of idea of an archive, and what we're basically doing is we're finding what are the best phrases that the machine learning algorithm comes up with, and we're putting them through a blast kind of cipher to see what is the best kind of phrase to be uptaken by the bacteria. And so in so doing, there's also an artistic interplay of these machinic and bacterial forces where we create some kinds of constraints for them to kind of coexist and co-create certain kinds of designs. In the near future, when everything opens again, we intend to go back into the icicle lab at the University of Toronto with Professor Stephen Morris, and he's been creating these really, really in vitro icicles. This is a icicle machine with no insulation, and when it's insulated, basically it looks like this. And what it does is it's basically a way where you're dropping water, you're just dropping water and creating the conditions around it such that the icicle forms around that. Right, and that's totally what we're thinking about in terms of gradient forces and in terms of the object or the form of an object as a visualization of its environmental interactions. So this is a quick video of some of the random icicles that he has from the Icicle Atlas. You can see it's really beautiful, it's really stunning, and it may be a very monolithic form again, but this is something that requires a lot of focus attention on the environment around it. And so what we're thinking of doing is seeding the environment with different concentrations of bacteria and different genetically modified versions of the bacteria that we're thinking of so as to co-create new and different structures. In our studios, I guess right now, some of the things that we're doing are simulation of various kinds of cloud morphologies. So you have cirrus clouds over here through chemical crystallization methods. On the right here, you have it with potassium nitrate, and on the left here, you have it with monoammonium phosphates. And this is being done in collaboration with a master student, Stefan Nerda, from the Daniels Faculty of Architecture, Landscape and Design at the University of Toronto. So, so that is my presentation, and I invite more questions. Thank you very much. This picture over here is an artist, Australian artist, Patricia Piccinini's sculpture called Eulogy, where she kind of talks about a future where we are going to be forced to engage and live and care for these new biological creatures that we create in the lab. And I find this particularly poignant because of the ambiguity that surrounds releasing genetically modified organisms into the atmosphere and having them kind of coexist and co-create the metabolic structure of an environment with us. So thank you very much for your time, and I look forward to the next presentation.
It was a lovely presentation, and we're very happy that you were here with us for the first time. Hopefully for the future conferences you'll be present as well. We will push forward, and at the end we'll try to have some conversations based on everything that you presented. I think there is a question, but we will take it at the end so that we can move on with all the presentations. So thank you again, and we will move on with, we have yet again Yomna and Alberto that are going to be presenting here. We will start in just a moment. Yes.
Hello, everyone. And I will do this presentation. We was preparing this not because COVID, but now maybe becomes a special moment because we will speak about one bridge that we was designing with Jomna and for the Sagrada Familia. But before making a kind of explanation and synthesis of the meaning that Sagrada Familia have done by Gaudí about the apocalypse. So we are in apocalyptic times. And first, you know, maybe the Sagrada Familia is now remains to build the central towers, and the main facade is not built there. And the main facade needs a bridge, and the bridge that was designed by the collaborators of Gaudí in Gaudí's times, of course, have nothing to do with the geometries, ideas, morphologies of Gaudí's Sagrada Familia. Was not time to do a real, a properly bridge. And now we are presenting a bridge as Gaudí maybe want to do if he is alive now. 145 years after the first stone that was in 1882. As you see, the bridge that was designed in his times is a very conventional bridge that needs to go over the street Mallorca, and, but with conventional staircases and yes, two symbolical pieces, that is a torch and a water. You will have properly written all in the article in the book, so I recommend you to read this, because now I will only explain fast, so some minutes, some little things that comes to mind. From one side, we was making this photomontage as Sagrada Familia, the holy city of Jerusalem, that is the main piece of Apocalypse, this book of the Bible. And from one side also, the holy Jerusalem, or the celestial Jerusalem, the heavenly Jerusalem, or the new Jerusalem of Apocalypse, is a kind of symbolic city that is designed by God directly. So this is the reason why different artists in all the history of Christianity are doing different versions in paintings, in drawings, and also in little sculptures maybe, of this representation of a city that have 12 towers and different characteristics described in the Apocalypse of St. John in the Bible, the last book of the Bible. Here we are now researching some symbols that Gaudí is introducing in Sagrada Familia, a lamp as the representation of directly the way that is described in the Apocalypse, this new city designed by God. And also one of the main things is that the Sagrada Familia have 12 towers around, so it's the only one church in all Christianity that have 12 towers as described in the New Jerusalem of Apocalypse, but also with this very original and inedit, never seen in the Christian art, tetramorpho. That is the version of a very conventional Romanesque and Gothic description of Apocalypse, of God, and around these four apocalyptic figures that Gaudí is translating in an architectonical way, in a very spectacular way. Well, other little or other little symbolistic, but I have not now time for explaining all. Only you read better in the article. Only, for example, one curiosity is also how, for example, in Apocalypse is described around the throne was a rainbow, a halo in other translations, as brilliant as an emerald. And it's exactly what you can see in the lights and colors in the inside of Sagrada Familia, that now is closed, so it's a pity, but when it's again open, you can confirm all the meanings of Apocalypse that I have take for you in the article, also the suites, the angels, all these things, these words all are taken from the Apocalypse, the reptiles as animals from hell, and also little things as the angels with this incense to God and take it also to the earth. But very interesting also that the names of the 12 apostles are written in every one of these 12 towers, exactly as described in Apocalypse, etc. It's a lot of descriptions that Gaudí is taking it, also inspired in Apocalypse, in this new heavenly city, and also the number 7, the number 12, the number 3. It's a lot of enigmatic symbols that is around everywhere. And also, of course, the main facade that is dedicated to the second coming of Jesus, that is in the final times, in the end of the times. So the dedication of the whole Sagrada Familia at the end is really what's happening in the main facade. That now it's not built. And it's in this main facade where we was proposing to the director of the Sagrada Familia this bridge here. So we need first to take out some houses that was not legally built, but okay, was built in the 70s. But now they are thinking that they need an entrance, and they will take out these houses. And we was proposing this bridge with the meaning of the of this this important sentence that is in Apocalypse as the river of light that it's coming from the throne, from the center of the Familia. So we give this meaning of the river of life around from the tree of life. So different meanings taking it from the Sagrada Familia, but that we can suppose that Gaudí will agree to introduce also these other symbolistics from Apocalypse that now it's not not taken and it's not introduced in the Sagrada Familia project. And we was making this as also a kind of atrio in the front of the facade of Sagrada Familia, of course, with the digital tools that allows us to continue the morphology and the forms, the geometry that Gaudí used in all the Sagrada Familia. But also with this comparison with the atrium that exists in the crypta of the Colonial Way, because it's maybe you have seen this model of the sales that Gaudí was doing for this church of the Colonial Way, in parallel when he was designing the Sagrada Familia. So we was understanding that we also in a translucent concrete as also this kind of river full of light of life. We can build in the front, making ramps until the main facade, as Gaudí was also in little scale doing for the Colonial Way. But also with different references that now exist in Barcelona, for example, the references of Enric Miralles in the Parc Diagonal Mar, and also the references of Tapies in the Fundació Tapies that was making this kind of forms that reproduce the original model of Sagrada Familia, and these fences of the balconies of La Pedrera directly from Gaudi also, trying to make a kind of vibration, a kind of continuation. Of course, in a material that now it's possible to do, this translucent concrete, maybe why not doing with alternative structures that can be, because our forms are exactly this, are possible to build in this way, but using the digital tools, so also allowing us to do it in with digital fabrication. And this is the section that you can see the ramps and going to the main facade. So thank you very much, and better read more precisely in the book. Thank you.
Thank you very much, Alberto, for the presentation. We will move now on to Severi. I know that Severi sent us a video, so I will prepare it. Hello, Severi, I see that you're here with us as well.
Yes. Let's watch the video.
Okay, so in just a second. Okay. Okay, perfect. So we start now.
Hello, I'm Severi Viroan, architect from Finland, and I'm going to talk to you about pattern continuities. This presentation we are only on a plane, not in 3D, so only 2D, and I'm using very regular tessellations and polygons like squares, triangles, and hexagons. The most important here maybe is the naming system I developed. So a letter A, B, C means a color, and in this case on one edge of a polygon. So like this first square, or 9 squares actually, at the left top is A, meaning that the one edge of the square is A, one color, and the next edge after the hyphen is also A, like same color. To AB means that the one edge is white and next is gray, and AB means first half of the edge is A and second is gray, like B. And but at the next edge of the same square it's opposite, it's BA, and so on. So ABA is like white, gray, white, and if the next edge is BAB it means gray, white, gray. Symmetrical, it means that one edge is symmetrical, so they can be combined from the polygons can be combined freely, so any edge is compatible with any edge, and the shape inside one polygon continues in the next one, and they make a bigger pattern. And so these patterns continue from polygon to polygon. Here's an example I saw in the book Inside Smart Geometry, and it was an article written by Neil Katz, and he was presenting this kind of a polygon with 3 stripes, 2 of those crossing each other, and with just this one hexagon you can make quite nice spaghetti. It's the same hexagon, but it's not in a random angle. It's always in a controlled angle, except in the bottom, very bottom, where rotation is random. So the first try here is what kind of other kind of combinations of these 3 stripes we can do. So the one stripe is always connecting 2 edges of a hexagon, And these are the 5 different ones you can make. And on the right you can see what kind of shapes they create, or patterns they create when they are combined in certain rotation angles. And on the very right they are in random order, which is always most interesting, I think. And if we combine, just like if you have 2 different tiles, or at the bottom here we have 5 different tiles, and in different angles, and on the right they are in a random angle. Same picture as previous, but this is colored, and I have colored these spaghettis or long stripes always with the same color if they are exactly the same shape. They are not the similar tiles, but they are the stripes are creating similar stripe. So you never know where is the other end of a stripe. It's going to be very short or long, or what. What about if we don't let these stripes cross each other? The crossing makes it kind of a 3D, but I wanted to push it more into 2D. And here is a similar. But what about if instead of crossing the stripes, we'll let the stripe fork, so the shape inside the hexagon in this case, and we can combine the edges with this kind of shapes in 28 different ways. Of hexagons with the yellow background, they don't have dead ends, so they don't have these half circles where the pattern would kind of stop continuing. We can also discuss about the random rotation. So we have 28 different hexagons here. So should we first have a random hexagon, and after that random angle or rotation, or should we use these different 138 different variations? Here is one example of ABA hexagons, all in random angles, but they are going from number 1 to 28 from bottom to top, and in the middle also the hexagon itself is random. Same idea, different version. Also kind of a 3D version of these hexagons, ABA hexagons, same one from the top. And here's kind of a application of the hexagons where I made a present to my friend for his magazine having 30 years anniversary. Here is 1 year ago competition proposal for mural for Vare Aalto University new building. Yeah, this I won the first prize, and this was realized. But what about other shapes, like other polygons? Here are triangles, same ABA triangles. ABA triangles are made kind of a 3D. They could be like this, for example. And ABA triangles from the top. ABA squares. And ABA squares in a 3D view. ABA pentagons. And I also, because you cannot make a 2D tiling with pentagons, so I had to do 3D in this case. And then we add one more color. So we have these 28 different hexagons, but what about if we add another shape inside that one shape, or several shapes if there are several, and we end up having 255 different, and you can also see the triangles and squares. Example of ABCBA hexagons, but using only the stripe style of hexagons. opposite example where there are no stripe type hexagons, they are just hexagons with fork inside them. Some more examples. ABCBA triangle or square. What about the future? A bit more interesting are actually these asymmetrical edges. And for that we have to use the chessboard coloring, AB square. And if you go to hexagons, here is ACBC hexagon. And we can join the edges in 4 different ways. And here we can see the ACBC hexagons color faces. Here are all ACBC hexagons color faces, different rotations. Here's a bigger shape made of ACBC hexagons. Some more ACBC hexagons, but now they are combined. I was just trying to find what kind of a spaghetti these bigger patterns they create. One more example. And this is also same ACBC. And then I want to know what is the logic here, which polygons you can combine and which you cannot. For example, here you can see that ABBAB hexagon is impossible. If we add to the same shape one more color, then we can have coloring for this system. And one more example, ABACB hexagon. That was all today. Thank you. Hello.
Thank you.
Arne. Hello, Arne.
Hello and hi from Mexico. You can also run just my recording that I did a day ago.
Perfect, we will do so.
Thank you.
If I can find it.
Everyone, my name is Arne Restinschak.
Okay.
Everyone, my name is Arne Restinsch. I come from Latvia and Estonia and from Biodigital generation 2008. All right, so straight jumping into the action, the research of the parametric tiling takes me to see that in the traditional contemporary world we have all these huge large format materials like sheet metal, we have the marble, granite, some extra big size pieces, but then when we come to standardized items we end up to the tiles, the ceramic tiles that are square, triangle, hexagon and whatsoever, and they usually imitate some sort of natural materials. So what I found out is that we can relate to Escher in terms of continuity to find the best pattern that would continue in a never-ending way. So from other side, we do have in the 2020 all those home like artificial intelligence speakers and gadgets that should make our lives better. But if you look at the price, it's like $300 and above. At the same time, we also do have the Arduino that you can buy for like $2 US. The price here, this is Canadian dollars, 281, so it's $2 US. And in the context of doing a research, well, I'm also building a house here in Mexico. This is the first zero energy building. And in this stage, when I had already got quite far with the shape and mass, I had like 3 things that were still not designed, like the actual huge window and the sauna, Finnish sauna by the way, and also the solar and hybrid wind energy farm on the roof. And I ended up that it has to be something like sauna, of course, because of the Finnish and Estonian traditions. We like it very much. So looking at this space that I had, I also was doing a little homework, making a router, like a router that is 1 meter 20 by 2 meters 40 surface of 3-axis router. That is open source project that I built myself from some parts that I bought online, and this is the Maslow CNC open source project. So the sauna starts to get the shape, and I'm figuring out I need the floor, right? So here are the floating shelves, and we get to the point that I'm also teaching in University of Monterrey. And I'm teaching there several subjects, like from design to also some advanced material subjects. And in material subjects, we do touch this field of making the patterns, of repetitive patterns that do have some black and whites from cellular automata inspired designs, and that should have some sort of parametric patterns, and also that they could be treated in all sorts of technology. By the way, University of Monterrey has lots of laboratories for doing this sort of work. Like we made water jet cut stone samples, and then we made some steel samples, we polished them with hand, do some laser engraving, work with the CNC with different varieties of wood. And I figured out that I could also do a mixed technique when we are making molds for casting pieces of concrete, white concrete. And finally we get to the resins and casting molds that would be very cost effective, like you only need one mold and you can reproduce it and use it for 100 times. So my students were doing these little samples, meanwhile I'm doing the big research I'm showing you in a moment. So then we get to the encrusted pieces. This is like a feature that you fill the engraved part or emptiness with some color tonality, and I came up to this feature that the deeper you cut, you can use the pigment and play around with the tonality. And at some point, well, at the end of semester, we also do play with thermoforming. And finally, when you look at these, like the students have a great portfolio of really interesting samples that are mixed technique obtained pieces that could assemble in a very beautiful interior. So when we put these things aside, my own research takes me a little further. And my own research takes me to the point where I am still needing to make my sauna floor. So long story short, the dimensions were already fixed. So I measured it about 2.60 meters wide and 1.50 meters deep. And I tried all sorts of geometries, like starting triangles, squares, rectangles, pentagons, hexagons, etc. But somehow the triangle seemed the most interesting for me. So in terms that it should be wasteless, if you look at this image, you could put in 12 triangles where 2 of them just have to be cut in half. I ended up that I could get really wasteless design if I do keep to that triangle, but I make a parametric pattern that has the feature that when you rotate it around 120 degrees, you would end up to something like this. Okay, so what do we see here? We have the normal gray concrete that is mixed with regular cement and sand. We do have the black concrete, which is basically the same but with the black pigment, natural pigment, and we have a white concrete that is using the marble sand and white Cemex cement. So taking these pieces around, obviously I need quite a lot of them, but keeping in mind the zero waste principles, I came up to the need of making a very economic mold. So for making this mold, I would need to cast some pieces 36 times, others also 36 times, and last ones, the middle triangles, just 12 times. So 1/3 of each, so 12, 12, 12, and 12, 12, 12, and 4, 4, 4, each per white, gray, and black pieces, so a totaling of 84. Well, so here is my little plan to make it. The largest ones are actually 57 centimeters long. And I had to calculate it all to inches because my Maslow CNC runs in inches. So the scrap CNC goes in place. I cut out some pieces and these little ones afterwards. Then to make the mold, well, while my students play with little molds, I play with big molds. Look at this video. I made it very short and quick because when you do work with rubber, the silicone has to be cured in within mixed and cast in 2 minutes time. So here's a quick time lapse. And totaling of about 3 kilograms of the material, I ended up with this huge mold, and then these little molds. The little ones were filled with resin, epoxic material, and integrated with some encrusted LEDs. Playing around with a lot of tonalities, I end up with some Arduino like flame effect. The problem with this one is that it shines straight into my eyes, so I do a little adjustment, turning them 90 degrees down, so the LEDs now are shining inside of the piece. Imitating the fire, I end up doing this very beautiful like burning effect that is actually a red light. And the red light is having really beautiful research that the red light wavelength is actually giving you mitochondrial function improvement for the cells, meaning you get a lot of more energy. And also is said that it would help some other skin benefits like damage caused from sunburns, and in Mexico it would be really actual, important thing. And further and further is a huge amount of health benefits that the red light gives to your body, increasing the age-related issues and so on. So here with my little kids, I start casting the concrete, figure out that I need a stronger reinforced cement and some metallic mesh inside, because otherwise it would just break into the parts. So taking it all back and placing it into the sauna design, which is still the work in progress, I am planning to finish this project pretty soon. And what is the most important, I'm getting to really close results of the zero waste, zero energy, and most important, like a huge amount of health benefits. So there's a little review of the work of mine where it involves the parametrics, the maker's movement, and the zero waste energy and material principle, and also really great health benefits. So next time in Mexico, I welcome you to the very first net zero energy building here in Monterrey, and also to the very first Finnish sauna, I think, in Monterrey in general. So thank you very much, and see you soon.
We will continue now with Mauro Costa, which is the last paper of this session. And right now we will play his presentation. Hello, Mauro. Nice to have you here.
Hi. Well, can you put the video, please?
Sure. Right now.
Thank you so much.
Pleasure.
Hi, everybody. The title of this presentation is Mixing Realities to Envision Learning Our Evolutions, Revolutions, Software, Hardware, and Humanware. And the authors, me, and Mauro Costa Coceiro, it's my name, from Santa Cruz Project, from Center for Social Studies, University of Coimbra, and Brime Silva from Digital Lab, his studio, and also student in the University of Coimbra. Well, to start, I have to say that it's almost impossible to ensure that education that we are promoting today will be valid within 20 or 30 years from now. And we can only suspect that the interaction between human beings and digital systems will be closer and closer. This way, creative technologies will provide interactive experiences where contemporary events will be fed by digital information in order to amplify certain aspects of present, past, and prospective realities. Thus, our aim is to retrieve examples of architecture and design, what we consider to be one of the oldest tangible human extended phenotypes, where combinations of art and technology can manifest scientific and aesthetic principles of what we used to call biologicals. For that, the authors propose some methods to raise our physical, cognitive, and emotional aptitudes, envisioning the revolutions in the way we teach and the way we learn. Here we have to say that Each conceptual model describes a little part of the whole reality, and different experts have different models in their minds. This way, academics with similar backgrounds are exposed to similar postulations, narrowing the chances of the new paradigms to emerge or to be explored. This is one of the main reasons why we had this idea to aggregate the work of two authors, me, and that, well, these two authors are almost from opposite academic experience, professional and academic experiences, and nevertheless with clear similarities in the frameworks and similar struggles to be accepted in orthodox scholar and market domains. Thus, here we present a common ground from two different backgrounds. Following this reasoning, both authors revise some of their works, bringing to evidence their biologic and technologic mixed common ground. And both authors also exercise their perspective views in order to make a picture of what biodigital future of architecture and design can be. So, starting with software, we might start to say that after the introduction of the concept of shape grammars by Steiny and Gibbs in 1972, a series of experiments were carried out exploring their potential not only in education but also in the project practice. Shape grammars can be defined as a process consisting in the appliance step by step of a set of rules to generate a formal language. When modeled in 3D, this formal language can be like a spatial shape grammar rather than a textual or symbolic grammar. So we might say that algorithms that can assume a deterministic or exploratory characters are used. In other words, they can be analytic or even generative. As an example, we can show the collective housing project of Oliva Creative Factory that was developed by Brime Silva, my colleague that unfortunately is not here. And here we cross the barrier from shape grammars to game engines, where the dissemination of those game engines, Unreal, Unity, etc., made architects begin to see these software tools as privileged vehicles to communicate their ideas, mainly because game engines proved to be accurate simulators of realities, improving the skills of their users. And an example of this is the work done with the Monastery of Santa Cruz, Manga Cloister in Coimbra. Here, a 3D digital reconstruction powered by Unreal Engine 4, reveals a sequence of images of an interactive model. Now, talking about hardware, in this field, we can highlight three major areas: digital fabrication, interactive design, and machines that make machines, let's say. The first example we have to show in this area is a temporary stand for Maison and Object Fair in Paris. Here, the main idea starts from the geometric evolution of a vertical wall that gradually transforms into an horizontal spatial structure through a double curvature surface. The latest accelerated transformations, based on intimate connection between digital information and perceptual abilities, disconnect us to realities that go far beyond our natural senses, giving way to new prolific fields such as augmented reality and virtual reality. In this field, the main example we have to show you is the Santa Cruz Project Workshop, with the title A Space and Time Travel in AR plus VR Technologies. And this is something here I have to thank to Rui Lobo, the coordinator of this project, Miguel Alberto, Antonio Monteiro, and also Pedro Andrade, at least, Mariane Pereira also. This software or this process, let's say, was developed in 2019 to the EKD and Sigradi in Porto. Here, the real environment of the Álvaro Siza Faul building, Faculty of Porto building, and gardens, is mixed with another elements from another city, the Coimbra Santa Cruz Monastery. In this exercise, we used the virtual reality Turing test, inspired by the imitation game of Alan Turing. These images now are based on a 3D survey of a human-scale statue of Odart that is present in the Museu Machado de Castro in Coimbra. And this digital reconstruction was used to make a schema of the minimum captures needed to provide a full immersive VR 3D environment. Initially, we start to simulate our mixed reality environments with 3 degrees of freedom, optimized to basic VR headsets like Oculus Go. In the second stage, we start to use engine games to simulate 6 degrees of freedom, according to the possibilities that new head-mounted displays have right now. So, as a conclusion to this presentation, I just would like to say that digital technologies are responsible for a shift in our education paradigm. Definitely, we are in the ending of the industrial age of education, and we are making the transition to a different educational system based in the mixed or virtual, tangible interactions with the world. This way, we start testing what we called a tangible VR book that was developed by Jorge Ribeiro and Jorge Cardoso from the Computer Science Department. The observer can access the virtual book by picking up a physical one, which can include different types of media beyond static image and text. For example, a video or audio can be activated when the page is displayed and disactivated when the page is hidden. This provides users with a more instinctive interaction, and so they can be rapidly transformed through those immersive environments. So I hope you enjoyed this presentation, and thank you for your attention.
Well, thank you all. If you have any question, please send it to me by email. I put my email in our chat, but also the paper has my official email, so feel free to pose any questions or keep talking about these issues that are important to all of us. Thank you, everybody.
Thank you very much for the presentation, Mauro. Right now we have a couple of minutes for further discussions based on this session. We do have one question from Pablo Vaquero for Joel. I will try to share the screen a bit with you guys so that we can see Joel. Let me see where Zoom is. Okay, so stop sharing. Maybe I can see you all. Okay, I see you. Hold on. Okay, perfect. So the question is, have you ever any experience adding structural behavior to the eye simulations?
That's a great question, and it's a very natural progression, obviously, because as we're talking about the dynamics of clouds within an atmosphere of constant change, the icicle is quite the opposite of it, which is like a very kind of ossified, individual, if you want. So yes, and definitely more in the future. I mean, one of the really simple experiments we've been doing is just taking real-time wind data and generating flow field patterns from that would then animate the way that the icicle is forming computationally. I think what we're doing right now is we're kind of waiting for real tests to occur in the icicle lab, where we're actually able to simulate these wind conditions physically, so that we can then manipulate a physical form. And that I feel is a really interesting experiment as well. So those will probably happen concurrently. But I want to say also that we're interested in the overall ideas of climate modeling as well. So at some point we may consider introducing larger scale climate models into this. This obviously is very, very far ahead, and I don't think we're there yet intellectually, but we will lean on research when the time comes that have already been working on these. Thanks so much for the question.
I think he would say with pleasure. Thank you very much for the answer. And now we will move on to the session that will conclude our whole conference. We will have a keynote lecture by Pablo Lorenzo Eiroa. He is here with us and he will share his screen soon enough. Pablo, are you here?
Yes, you hear me?
Yes, I hear you. Lovely to see you.
Right.
Welcome back to the week.
Likewise. Thank you, everybody. Thanks for the invitation. I just finished. You see the PowerPoint, right? Okay. You hear me also? Okay, because it says muted by the host. I don't know why. All right. Okay, cool. So Pablo Lorenzo Eiroa, I'm an associate professor at New York Institute of Technology, working in New York. I'm developing a new MS in architecture computational technologies with Maria Permelini, who is the dean, and Tom Berber is the associate dean. And I just finished a workshop I was saying yesterday with the BioDigital Master Program here with Alberto. I want to simply introduce you to some of our current research. My research has different aspects, and I want to show you briefly what we do in my office and also as a professor. But first, I want to introduce to you some key concepts in terms of why we are doing what we are doing. First, I want to introduce the problem of algorithms. We are all working with algorithms. Our cell phones have 200, 300,000 algorithms running real time. And, you know, of course, the issue of the signal and the Boolean logic of algorithms to me is something that has been fascinating me since I was probably 6 years old. I had the opportunity to study computation since very early in my education, and I went through many different programming languages. And I want to thank actually my professors at the time. But one of the issues of computation is predetermination, the fact that the program is done before the project. And I'm trying to deal with that problem in a critical way, thinking that the relationship between deterministic operations and the emergent logic of a project could be feeding into each other. For that, I just want to mention what's going on today on the other side of algorithms with machine learning, data mining, big data, because my presentation is going to be basically about working with big data processes. The big shift around 2010 was not to imitate the brain any longer in machine learning, but to actually think of algorithms or meta algorithms in order to advance a certain kind of autonomy in terms of algorithms trying to optimize each other in order to make a certain kind of prediction decision. And they gave me 20 times, so I'm going to be a little bit perhaps superficial on these issues. I have several articles in academia.edu where you can search the articles that I wrote, but mainly I wanted to present to you the shift since around 2010, between 2005 and 2010, in the relationship between the weight of algorithms in relationship to the amount of data that we are processing, the data that we are gathering, and which are the structures through which we gather data, which is one of the issues that concern me the most in terms of surveying and in terms of developing tools to acquire data. So in that sense, around 2010, there were increasingly complex algorithms, while the amount of data being processed was kind of small. And that equation started shifting in sciences. The relationship between theory and data balance started shifting Because of a cognitive problem, right, in statistics and in different ways of analyzing what's going on relative to our prejudgment or anticipation of the problem by developing algorithms. In other words, if we are developing an algorithm, we need to have a thesis of what the problem is and design the algorithm in order to match with that thesis. That is becoming actually problematic because in a way, the determination of the problem becomes part of the solution. So in other words, you search for what you want to search, and therefore you have the solution that you're looking for, which is actually, in scientific terms, a little bit problematic. So in that sense, since 2010, there has been a shift in the theory data balance, and now we're working with a lot of data and actually reducing the amount of algorithms that we're using or the complexity of the algorithms in order to address the Simpson paradox of 1973, in which because of the difference between data sets, the result of data, if they're studied alone versus if they're studying in group and collide and organize with each other, the actual result flips, right? So in that sense, to me, what happens is that there has been an emergence of a different type of problem in architecture, which is what is forensic architecture, what is a survey as a design problem. In that sense, to me, what has been happening all over the world in mainly schools of architecture is that the new technologies are providing architects or actually all the disciplines. Computation is becoming a common new plateau across disciplines. And new technologies are providing new lenses to look at the world, right? And therefore they transform the disciplines. But what happens with new technologies? Can architects participate in terms of the development of new technologies? And what are the new emerging disciplines in that sense? And I'm interested in intervening at that level. I've been working in terms of signal, like my projects try to address computation and also the structure of the project at the signal processing level. In that sense, I base my investigations in terms of digital signifiers or the theory of signs. And I'm working with the fact that actually, if the language exists before the project, right, which is a linguistic problem that Derrida identified, means that the sign produces signification independently from what it is being described. In that sense, I'm interested in producing new signs, producing new conditions that would actually produce new types of architecture to try to address this formulation, a certain kind of relationship and cross-relationship and feedback between form and information. In that sense, since perhaps the after the Second World War, architects became concerned about predetermination and started working with post-structuralist agendas in which the reality came beforehand ideas. But unfortunately, that way of understanding displacement or the critique of a predetermined structure did not really enter in computation until late. In 1970s, hackers mainly started addressing the fact that we could be in a dystopian future as we are today with Facebook and Google, in which the predetermination of certain linguistic apparatus, such as a certain type of algorithms, would actually start structuring the world in a very top-down way, right? So in that sense, I would argue that architects that they claim that they are working with forms that are complex and forms that are post-structuralist, that they are negating tabula rasa, in themselves, the algorithms that they're dealing with are not really such, but the algorithms that they're dealing with are actually tabula rasa kind, they're modern kind, they're bifurcating linear algorithms that are predeterminating the logic of the projects. In that sense, as we move from left to right in computation, I'm interested in working with algorithms that or type of computation, symbolic computation, mathematical computation, different types of computations that would address this problem and therefore start developing structures of computation that in themselves are non-predeterministic. In that sense, on the right, all the way to the right, I'm working with, of course, simulate different types of computational simulation because of the mathematical problem of simulation, which is an emergent system that unless you run it, you cannot anticipate what's going to happen. In that sense, simulations are non-reversible they are non-reducible, right? So in that sense, I'm interested in that problematic relationship between architecture and computation, dealing not only with the structure of the projects being emergent, looking emergent, but actually the coding at the coding level have a different kind of structure of organizing information. In that sense, we're working with blockchain, not top-down algorithms, but collaborative algorithms in terms of trying to look for different type of connectivity and different type of processing information in which that becomes a problem in itself. I am interested in problems of origination as well. This is a 3D scan that we did with Graciano Valenti and Andrew Saunders. Andrew Saunders mainly is a research by Andrew Saunders. He came out with a book lately, which is a problem of survey in architecture. And I'm interested in how we start a project and how far can we take origination in terms of design. That's why I'm interested in the form of the algorithms, how algorithms work, how computation can become other than algorithmic, and also thinking about the survey mechanisms that allows us to look at architecture in a different way. I also work with computational design using mathematics, sometimes trying to critique the form of the software, and also at the material level, trying to avoid linear translations between the digital and the analog, but thinking that there is a cross relationship. And we also develop computational robotic machines, not only digital robots, but also physical robots that they would be able to build architecture in a different way. This is a robot that we finished in 2018 that was part of the Venice Biennale, and it's a site-specific robot. It can be adapted to any site, anywhere. Mathematically speaking, could be scaled to any scale, and it works with a cable-driven technology. So, but coming to the problem of this presentation, the interest is what is the political dimension within representation? How can we originate new discourses and new paradigms in architecture? My career started with this project in Buenos Aires, Argentina, and the Rio de la Plata, looking at sedimentation and understanding with a group of architects how we could use sedimentation to actually balance nature and produce a self-balancing mechanism to think about the environment not as a restriction, but actually to work with environmental forces to actually construct the design of the project. In that sense, we work with geology and meteorology. This is 1998 to 2001, very early on. And we're thinking already about architecture as a form of structuring reality, but working with environmental process, reading environmental process, mapping environmental process, deviating environmental process, and eventually processing environments, what I called eco-induction. In that sense, the results of the park are quite impressive in certain areas because the form of the landscape becomes emergent for dealing with forces of sedimentation and the winds, the dominant winds. So since I believe that there is no information without representation, that means that every software we use, every machine we use, if we do not code it, if we are not responsible for it, that means that there is a relegation of authorship in a collaborative environment, of course, but a kind of unbalance between the design agenda and the role of the architect. And if we do not enter into this, I would argue that architecture is going to simply become obsolete. In that sense, what I was referring before, the relation between big data and algorithm is changing. So therefore, we're also creating our own repositories and gathering data, thinking that we are in a new type of renaissance, and thinking that we can design the parameters and not the objects or the design itself. In that sense, there has been an evolution of drawing and representation in architecture that you are all aware with. I'm not going to go through that, but I'm going to lastly show the application of these theories in New York City. New York City has a very conventional code, zoning code, which is actually based on a lot of type of commercial pressures, I would argue, more than actually architectural planning. Of course, the ferries examples of 1930s are exceptional, but other than that, the zoning code has created a lot of exceptions. So therefore, in my research as a professor at the Cooper Union before, and now at New York Institute of Technology, we look at ways of mapping to activate an architectural agenda. This is a drawing that is doesn't have any design, but the design of the representation of the territory engenders an architectural concept, which is to connect Central Park to the periphery of New York City by just simply mapping and understanding flat zones. These are other examples of a studio in UPenn in which you can recognize the islands within the island of Manhattan in relationship to a topography which has been progressively kind of hidden by the logic of the grid superimposed on top. And on top of that, you can easily identify that the social housing where poor people live have been placed in flat zones, right? So there's a lot of very interesting information that you get by just simply observing, mapping reality from an architectural point of view, creating your own data and not depending on governmental data. That to me is essential in terms of politics of big data, that we resist this mechanisms of data gathering. We resist, for instance, zip code, right? Like mailing codes to create data to me is very problematic. The way data is being gathered is very problematic. So architects, I would argue, we need to enter into that territory. We need to participate on the agendas of the government. And here there are examples of students dealing with the density of soil below grade in New York City and thinking how you can react to that in very specific terms. These are a project, and I'm building a library and a data set in order to produce the last project that I'm going to show, which is a new zoning for New York City. These are flat zones. We also model the behavior of sedimentation at the molecular level, thinking and understanding how that sedimentation happens along the different rivers around New York City, and thinking how one could intervene by understanding the dynamics and the fluid dynamics of the different environmental processes. This is on the upper side, Manhattan, on the lower side, Queens. Queens is basically a delta that has been covered and in a way obfuscating the natural environment. So one of the ideas is to recover latent ecologies, to recover what the grid has been placed under pressure, and to reveal those as opportunities, and actually instead of building, to actually deconstruct the built environment in relationship to the emergence of a different type of environment. We look at thermodynamics at the level of heat island effect. These are students that they work creating a skyline of thermal temperature over New York City, creating with our own data. And you can see here, these are progressive sections. This is a blow up of the thermal readings, right, with the different gradients over the skyline of New York City. So here are the thermal readings in plan. And we are thinking about creating corridors, wind corridors, to accelerate vortex and therefore alleviate the heat island effect in New York City. We're also looking at wind patterns of all types, different directions, different times, and also continuing the previous project, coordinating thermal readings with wind patterns to be able to create different types of environments. In parallel to my research at the university, in my office earchitects.net, we actualize this research in the form of very particular projects. This is a proposal for the expansion of JFK Airport, looking at the dynamics of the delta in front of the airport. Lately, we have been working on a big data model, articulating all these data sets and incorporating all that information and thinking about a different prototype for New York City, not only as an imaginative process, but actually as a real implementation project in terms of working with the government. We actually presented this project to the Department of Transportation in New York City, thinking that we can model all the environmental conditions and create an interface. We're actually working on an interface so that the municipalities could have this information real time. Every time there is a building going up, that building produces an environmental effect, and that effect should be following a globally coordinated problem, right? A globally coordinated information system, so that we have more information in terms of how we continue growing or how we actually deconstruct our cities in order to create a continuity between the different cities and the continuity between the city and the environment, right? And these are some of the images of the interface that we are developing. We have a quite impressive team with researchers, and we're actually working on it every year, and we're actually going into a research grant. So the idea is to coordinate globally all the cities and think about how the growth and the deconstruction of the city can activate latent environments that then will build up as a global ecology, right? So that there is no fragmentation between center and periphery. We're also working with transit systems. We also presented this to the DOT. And we actually came up with the conclusion that the most optimized delivery point in New York City would be this one, which 2 months later became the Amazon very famous controversial problem of setting up a delivery system for New York City there. I don't know if they look at our algorithms or not, but probably the city validated that decision by Amazon in relationship to what we presented. But basically, these are loops that are optimized in relationship to the 3 bridges and reaching out to all the different areas of New York City. We also coordinated that to be able to do mega blocks, such as what Barcelona is doing, to alleviate the traffic, and that we place it in relationship to the environmental simulation, so that if you do one thing alone, right, it doesn't really help. You need to work at different levels. You need to attack the problem from as many points of view as possible and create an emergent new model in which all this information is cross-related real time. We're also 3D scanning the city of New York. We are also looking at what's happening at the digital level with the city of New York in terms of Facebook, Instagram, and how people interact physically and digitally. And we're actually creating a kind of ghost virtual city of New York for a video game project that we're working on. So just lastly, I just wanted to say that finish with this phrase, that I would argue that architecture has related its cultural project to technology. That is true, and we all are for technology. The problem is how how much authorship is architecture engaging in terms of what's happening with the current revolutions. Are we just simply using tools, or are we expanding our discipline in relationship to new tools? And what is our relative authorship in cultural authorship and technological authorship in terms of expanding the realm of things that are happening? If you're interested in what I'm presenting in academia.edu, Data and Politics of Information is the last paper that I presented in terms of these issues. Thank you very much.
Thank you for the presentation. This was an honor for everybody to be here at this conference. I can now show everybody here. Everybody will be visible on YouTube, and I will make myself visible here if I can know how, because I am not a fan of Zoom. There you go. Well, everybody, the rest in the classroom will be visible on YouTube. We would like to thank you all for being here and for helping us make this happen. And hopefully we can do this again in the near future. And maybe we can do it live and not through webcams in Zoom. So I would like to congratulate everybody for their wonderful theses and papers and all the presentations that were wonderful. And through this, we have concluded. We also have Alberto that's going to be here. If you can just, if you take the, no, okay.
Thank you, Drago.
Hello. So thank you very much for all your presentations. And it was a pleasure to see a lot of friends making presentations so advanced. And thank you also to Dragos, that is the big organizer, and really have do a great job organizing this. And so, for next time again, okay? Bye.
Thank you, everybody, and see you next time.
Thank you, Dragos. Thank you, Alberto.
Thank you, Dragos.
Cheers.
Bye-bye, everyone.
Bye.
Amazing job. Whoa.
Thank you. Thank you.
Great job, Dragos.
Bye, everyone.
Thank God.
Bye. Okay. Now.
Bye, everybody. Bye, Mauro. Bye, Gonçalo. Hey, tudo bem? Yeah. What?
Too late. Okay, so.